deep learning, so like building on what Alberic did yesterday. And then we're going to talk about both processing images, so that's called computer vision, and then processing texts in AI, that's called natural language processing. And lastly, we're going to talk a bit about generative AI. So let's talk about the origins of deep learning. So everything started actually with the perceptron, and the perceptron is an architecture that is quite simple. The main point of it is that you see my mouse online. Okay. So the point of the perceptron is that you have this input that you have that could be like any sequence of numbers, or like it could be anything, and then you're going to learn some weights, so like m times. You're going to sum those weights, and then you're going to apply on this an activation function. This activation function is going to be nonlinear, and it's going to be important later. So this was introduced in 68, and it's like this simply goes to this simple formula. So like you're simply summing up like linear equations, like and then you're just putting a function on top of that. And the goal of this is that we're learning like a function that is in this case y, and that could be referred to yesterday, you know, when you were learning with the exercise the gravity of the moon. So in this case, you're not simply learning one parameter, but you're learning many. Then what happened is that like many years later, actually, like someone introduced something that's called like the multi-layer perceptron. So before it was one layer perceptron, and this time we have like other layer, at least one, if not many. So in this case, basically from the graph from before and this one, the biggest difference is the blue lines. So each line represents a parameter that you're learning. It's a bit in the same fashion. You've got those inputs, those weights, also like an activation function here, and then you again got weights. So you simply do this process like over and over. And we basically know from math that by doing this, you're going to be able to approximate really well sort of any function. And so that's the biggest point of the MLP. And we also call this MLP for multi-layer perceptron, and we also call it sometimes like a fully forward network, or it's like sometimes we might use this as simply like some basis stacked linear layers. So this is the basics of deep learning, and this is how we first created it. But then what happened is that we sort of realized that like for some very specific type of input data, such as like images, those MLT were not very efficient, and so we needed to come up with like new architectures. And so like this is why we came up with like an entire field that is now called computer vision. So learning has really been like evolving, because at the really beginning, what we first thought was that like, okay, you have this input image, we're gonna extract some features, so maybe the outline of the core, like different features, and then from this, we're gonna create some sort of decision rule that's gonna tell us whether or not it's a car. So for example, I could say, okay, if this object that I see as outlined and I can identify 4 different wheels, and it's an eye-moving object, then it's a car. Like high-speed moving object, it's a car. So that was like really like the beginning of learning. Then we went a bit further, where like we started to think, okay, like from this input we can extract those features, and then instead of making all these rules by hand and just like writing them in code, we can maybe just have a classifier that learns from the distribution. So we're like, okay, maybe we can have like a small classifier that detects whether or not it's a car. And later on, we actually thought that like if we just extend this classifier, and if we don't actually like extract those features and then give it to the classifier, but we let the classifier find those features representation, then it's going to work just as well. And this is actually called deep learning. And this is like an end-to-end learning. And most models that we're going to talk about today are end-to-end learnings, including the CNN that I'm going to introduce right now. So I'm going to try to make this session a bit interactive. So like that was just the basics that I just wanted to lay down. But now like we're going to try to get a bit with your intuition. And the point is really that you guys get something out of this. So instead of simply getting math formula, let's try to make this interactive. So let's say you have this very nice image of Harvard, but you see you have like all this noise. How would you actually get rid of those pixels? Someone in the audience. Denoising. Okay, but how would you denoise? Like that's the question.
That would be to I mean, that would involve looking at, the matrix or the matrix form of that picture.
Okay.
And, using NumPy to take them out. So.
And take them out. Yeah, okay, but how do you take, the part that I'm wondering is this takeout part. Like, how do you take it out? Yes?
Can you get a fresh image without noise?
No, because otherwise it would be simple. Like in this case, I just give you this one image and I want you to take the noise out. I think yeah.
I guess it's a little hard, Cody, but if you kind of know ahead of time, it seems like there's only like 4 or 5 colors that are recurring.
Mm-hmm.
I don't know exactly how I do it, but some form of like identifying areas where you have a cluster of like just that color and then removing them, although I don't know how you would replace it, but that sounds like another step.
Exactly, I'm like, that could completely be one way. Another very simple way of doing that, I'm gonna break it up to you, is what if actually we would simply replace the pixels that we have for one value with the neighborhood average. So basically we're gonna slide a bit like a window like I'm doing right now, and we're gonna look at the average values around, and I'm simply gonna average them. Therefore, when I'm gonna be in a square where there is like a green value and I'm in the sky, well, like most values around me are blue, and the green value in the middle is gonna be averaged out. So then you'll have an image a bit more blurry, but you got the noise out. So how does this look like actually? So let's actually start with this. So like we've got this image f of x. We now want to get the noise out of it. So that's now g of x. What would be the value here? Knowing that you're simply doing an average. 0. Okay, great. Then what are we going to do after this? We're going to slide to the right. Exactly. So as we slide to the right, what is going to be the value of this one? 10. Exactly. Next value? 20. Next value? Okay, really good, guys. Okay, so like now I'm going to speed it up because okay, let's see it faster. So is there something that you're noticing right now between the first image and the second one? What are you noticing?
Smaller.
Exactly, it's smaller. It's actually the biggest point. So what happens is that like those exterior values, like when you go from these exterior values, like they're not then represented. So like you actually lost 1 pixel on the left side, 1 pixel on the right side, 1 pixel from above, 1 pixel from below. Now you went from 10 pixels to 8 pixels. But maybe it's not really what we wanted because we said we simply wanted to take the noise out. So now like how like is there a solution to this problem that you could think of?
Solutions to this problem.
Yeah, so how could we have values here on the sides?
Copy from the first image.
Okay, that could be a solution. We simply copy it, then we maybe have noise on it, but that's a good option. And if you also want to take some noise out of it, what you could do is you could do what's called padding. So basically you could make the first image a bit larger at the beginning. And by doing this, you're gonna lose 1 pixel on the left and right and up and down, but you really made the image bigger for that. So you sort of like accounted for that. So I mean, so this is one thing exactly. So now like let's look a bit at another representation of what we exactly did. And let's say like, okay, we're now like computing is one of these values. What values would you need to fill in this filter that we just now have, that is of size 3 by 3, such that we get this neighborhood averages? So said differently, what values would you give to those letters A, B, C, D until I? Knowing that you just want an average. Almost there, yeah. Like, because right now, like you're summing everything up, so maybe you want to normalize. So like maybe you want to, as it's like, what do you do in an average? You sum all the values, and then what is the next step? Exactly, divide by them. So by how much should I divide here? 9, exactly. So actually, like it's you're right, like it's full of ones, but then I do have this 1 9 in front, and actually, this is convolution. Well, like what I'm literally showing you right now, this is literally convolution. So we have this image, we have a kernel that would determine its size. We have some parameters that go from A to I. And the entire point is now we're simply going to learn those parameters because it's going to help us to learn a significant representation that's going to be helpful in the future. So this is sort of it. And now the question is just like, okay, what value should we give to like A, B, C? Or said differently, like how does it impact an image depending on the value that you learn? So let's do a bit some small examples. And let's say, okay, here, like let's practice with some kernels. What happens if so now I have this function f, I'm going to multiply it by this kernel h, and then I'm going to have like an output image. So it's another 3x3 kernel. I've set up the values in such a way, like I just have a one in the middle. So what it's going to do is that, like, as I'm doing a convolution, I'm simply going to slide this kernel every time on it, and it's going to slide like this from left to right. So my question for you is, what would you expect to happen here on the right side? What should the image look like?
It should be very bright and negative.
It should?
Very bright.
Okay, why do you think that?
I'm saying for one.
Because okay, but let's go. Actually, it's really nice that you're pointing this out, because actually, like, what it's going to do is that, like, every time this kernel is going to move. So like I'm going to multiply 0, 0, 0, 0, 1, 0, 0, 0, 0. I'm going to take all the input values here, they're all 0, and I'm going to simply say, okay, so what is the computation? And then I return the value, and then I'm going to slide. So like when I'm sliding here, I should return like, what am I going to return? Let's say like I have a pixel that is right here. So I'm returning one like here, and I'm returning like pixels just around it. And I'm simply multiplying by 1. What should I get? The same image, exactly. Exactly the same image. Exactly. So this is exactly what you get. Good job. Okay, so now what happens if now like my 1 is shifted to the right?
Shift the image to the right? Or
Okay,
to the left?
you want to do something. Exactly. You're going to actually shift the image to the left. Because what's going to happen is that like when you're going to be at one of these edges, when you're going to be a bit on the left, you're going to take a value from the right and you're going to use it for the image on the left side. So what you're actually going to happen is that like you're going to see that the image is going to be shifted. It's not super visible, but basically you see from here that here you had a bit of an edge, and now you see like the entire image shifted a bit to the left, and it's now like touching the padding zone. Okay, so now like let's do a bit of a more complicated one. Okay, yeah,
Why
go
is
ahead.
the one on the right for the image feels bigger?
Because okay, like that's a good question. Thank you very much for asking it. So the point is that like let's say that like I'm gonna put this filter. So like I'm gonna literally put this filter right here, and so like I'm literally a bit on the left of the edge of the Eiffel Tower. What's gonna happen is that like if I would simply multiply by 1, it would look on the right, it would see nothing, so it would just be like, okay, this is blank. So like this is just 0. So this is just the sky. But now, as I'm having a filter with like this one right here, when I'm now gonna be here, what's gonna happen is that it's gonna find the value on the right, because it's gonna be like, okay, I'm averaging. So it's gonna be like, okay, I'm gonna take this one value from the right while I'm on the left, and it's now gonna use the value on the right to shift it to the left. I hope that's clear. So now, like, let's take another example of this Eiffel Tower. And let's say, okay, like now I'm going to apply this new filter that is -1 on the left, 1 on the right. It's a bit, like, feel free to say anything, like, don't worry, like, it's not super intuitive. So, like, what would you think is going to happen? It's okay to do mistakes. Okay, like that actually, that could be, because you could say they compensate. So now try to think, okay, when is in which scenarios is nothing gonna happen, in which scenarios is maybe something gonna happen. Like when you're, imagine this, like when you're moving on this image, as you're moving on it. Maybe that's not very clear.
This is really taking the pixels at different places of the images. So the one is taking a pixel on the right,
Yeah.
and the one taking another pixel on the left.
Exactly.
And then we're combining the values of different pixels. So what should be the values of this pixel to be completely cancelling out and
Mhm.
zero value?
Exactly. Exactly. Okay, so like if you've got, so exactly, so if you're somewhere where you've got the same pixel here and the same pixel here, exactly, like it's gonna cancel, it's gonna be up to 0. Okay, so it means that like if you're either like in the background, same color, it goes to 0. And if you're inside the Eiffel Tower, and this is again the same color because you're inside, again it goes to 0. So what are the cases when it's not the case? Because we said outside and inside.
On the edge.
On the edges, exactly. So actually what you get is you get the edge, so actually what you get is that you get like an edge detector. So now with this -1, you're able to get like every edge of the Eiffel Tower. Simply by this, like we simply multiply this, like we simply use this kernel as a basis. Okay, so now that we played a bit with like shapes, let's now say, okay, like what do you think is going to happen when I'm going to multiply this one image of those like sunflowers with this one kernel that is like round? So imagine that blue is negative values, red is positive values. What is this filter going to detect? How do you think is the image going to look like when I'm going to put it on the right side? It's super easy, like just like the most obvious answer.
Flowers will be red.
Sorry?
Flowers will be red.
Exactly. Flowers are red. Basically. Like you basically seeing that like you identified, depending of the size of this kernel, you identify like some flowers. But what you're also seeing is that like the flowers at the back are not really well identified, right? Like those flowers, it almost looks like noise. Well, here it works. So like one question that you could think about is like, okay, maybe we could simply take a smaller kernel. And if we take a smaller kernel, like what's gonna happen? Well, like the one at the back are working really well because you're seeing that like now they're well identified. Like you're seeing that basically like those ones, I'm sorry, yeah, red and red is not super easy for the audience. So like here you're seeing that those ones are really well identified because they're the one at the back because the kernel is smaller. But those ones now it's identifying sort of like many small ones. So now this filter is not really working. So a solution that you could think about is maybe also like playing with the input image, but actually like it just means the same. Like if you make the input image smaller, you're just making, relatively speaking, you're simply making the kernel larger in a certain way. Okay, so let's take a bit of a funny example. Do you know this guy? No. You don't? Okay, exactly. Have you found Waldo actually? Like, can you find them? It's hard, right? Like, it's not that easy.
It's really hard.
Yes, it's really hard, but like, what could be like a nice way actually to find them? Maybe a nice way would be, okay, like actually, like if we use this normalized kernel, it's like which is like literally his shirt, and that is like really in the right direction. Well, maybe we could find him like maybe it would be easier to find Waldo. And so like let's say like we literally like so right now we're not learning this filter, we're like simply like taking it exactly like we took them for the Eiffel Tower. And we're simply saying like, okay, now we're gonna take this filter and we're gonna like do a convolution on it and we're gonna scan the image. And when it's gonna find exactly this pattern, you're immediately gonna see it. Can you now find Waldo? Where is Waldo? Knowing that this is the representation that I just mentioned.
Yeah,
Exactly.
right, yeah.
This is Waldo. So now you see that like the filters basically like reacted really well to it. You also see that like it reacted to like someone else here that probably also had maybe like the same shirt, but this one is good enough that you know for sure that it's him. Also, you just check here and you're like, okay, Waldo is here. Okay, amazing. So basically, what we've seen now with the CNN, which is like, with this convolution, is that those kernel weights are simply like features detector. And this is maybe like the most important slide about convolution. So like kernel weights are features detectors. And so learning those weights, like those A, B, C, D parameters, is exactly the same as like learning these features representation. And this is what convolution is about. And this is also what convolutional networks are about. So now we've basically mentioned convolution and went like extensively about it. Now we're going to build a network using this operator, exactly like before we had the perceptron or the MLP with these linear equations. So we have this input image, and what we're going to do is that like we're going to learn some filters. Yeah, and like so we have this, and like so we have this main image. We're going to learn multiple filters. Okay, so like those filters will be learned exactly like what you learned with Alberic yesterday, meaning that you have this gradient descent algorithm that's going to optimize them, and it's going to learn different ones. For now, let's stay on the basics. So you see like, actually like, what would you think is this going to detect, and what do you think is this going to be helpful for? Like those specific patterns that you see. Like you said, maybe they have a direction. What would you say you learned?
Which color is negative, which color is positive?
Blue is negative, and red is positive.
So like the intuition that we're taking away from the blue and the red is anything that's red when that is dark in the original image, that's getting activated. And
Yes.
anything that's blue, if that's dark in the original image, that's being punished. Like that is lowering the activation.
You can think about it this way, yes. Like as you've got like a big delta between the blue and the red, doesn't really matter in which direction it is, you're gonna somehow identify this pattern. So here basically, as you see, like you've got like a vertical line and you've got like an horizontal line. When you apply those kernels to this image, what you're gonna get is this. So this is maybe detecting some edges at some point, because it's simply looking at, I don't know, like some round behaviors. Okay, sure. And these are the two most important ones, because you clearly see the vertical lines and the horizontal lines. I think the horizontal lines are extremely clear. But so again, we have this input, we learn those filters exactly like before. We now apply our convolution, and now what we're gonna do, is that we're simply gonna like exactly a bit like we did like for the perceptron. We're now gonna apply some nonlinearity, like the tannage that we talked about yesterday. And what this means is that we're gonna filter out the blue values. So now like we basically this different representation allow the model to focus on key representations. So the vertical line, the horizontal lines. And then what the convolutional network does is that then we're going to apply some spatial pooling, which is a fancy word for saying we're making the image smaller. We can do this in various ways, but we're just making the image smaller. And then we're giving this representation to the next layer. So the idea is that now we have like multiple representation of the same image as input. We're now combining them. And you now give this information to a new layer to try to make a good decision about what is this image, like what are we seeing? So one of the first actually like network of doing this is called like LeNet by Yann LeCun, who is now like head of Meta. And basically here the point was that like, so this is the full network. Convolution is seen here as an operation. You see that there is one convolution, a second convolution, and then full connection. I'm gonna go a bit into what this is. Don't feel too worried about it. So here we see that those convolutions are 5 by 5. Again, we've just seen an example of 3 by 3, but convolutions can be as large as you want. They can also be 1 by 1. And then we have this convolution with some samples making the image smaller. And we then again, and again do another convolution, where then we're basically going to make those full connections, so like those linear layers that are introduced in the perceptron, and basically then we're going to go to this output. And in this case, LeNet was used for determining classifying digits. So that's why there are 10 classes, because that's why output is 10. Because basically the idea is that you go from an image of a number, of a digit, and you want to know, okay, which number is it from 0 to 9? Actually, now that I'm thinking about it, because I'd like to show, how can I,
You want it on the website?
yeah, exactly.
You could like stop sharing and just slide it. This should be like a separate disk.
It's just right here.
Yes, so if just go now, should have it here now. Yes.
Okay, amazing. Good job. Okay, that's perfect. And then if I do, okay, then you'll teach me how to do it. Okay, go to the other one. Okay, so, okay, maybe you're not seeing so well yet, but it's gonna become clearer very soon. So, basically, give me a digit from 0 to 9. 4, okay. You took a hard one to do. Do you see this? Okay. So first, this is my drawing, and this is the first guess of the network. It means that, thank you very much. Yes, okay. So it means that the network is now guessing that this is actually a 4, which means that I probably did a good job at first writing it, and then also at training this network, which is like 2 good news.
Very beautiful form.
Thank you very much. So, like here, you're actually visualizing that, like, so those are different filters that we've learned, exactly like in the windmill example. So this is like, we had 3 examples in the windmill. Here we have like 6 of them. Sure. The size is 5, meaning that like when I'm looking at 1 pixel here, like when I have 1 pixel in this convoluted layer, it's actually referring to yes, you see like 1 pixel here is referring to like 5 pixels, I make 5 by 5, so actually like 25 pixels over there. Then we're applying this, also for the people online, then we're applying this pooling, which is just making the image smaller. And as on this pooling, we again apply convolution. When you do a convolution of 5 by 5 on an image that is like twice smaller, how big is the convolution now? Like if you look at this. So like, let's say we make the image twice smaller. And we now do like a 5 by 5 convolution on an image that is twice as small. How big is the convolution, would you say? Like, how much is the convolution seeing? Sorry, maybe that's a better way of putting it.
5 by 5, and double it.
Exactly, you double it. As you make the image like twice smaller, the 5 by 5 is now seeing like 10 by 10. And actually, like that's a big point in convolutional networks that I want to get through. Because the point is that it's a notion called receptive field. That's how we call it in the field. You don't need to remember this name. But it's just to say, okay, like the deeper we're getting into the network, the more you're seeing global features. And actually, it's something that you can really easily observe because like here, for example, like what do you see on this? Basically, what you observe in these kernels, you see that like you have very local edge detectors. So it learned here two detectors for the 4, here a bit the same. Here it learns some detectors that are like more vertical. But this is still just like edge detection because it's only seeing edges because you've got this tiny thing going for it. It can only see, okay, here there is a positive value, here there is -1, that's an edge. And then the further you're going in the network, you're seeing that like the patterns are becoming much more global. Like now it's actually learning something that you can't really understand, but it's going through the entire image in terms of activation. And then the way you can see this like linear layer, that like you have this 2 linear layer, is simply of saying, okay, this is simply a matter of like, you're now answering like about like 100 questions of yes or no. So now that you've identified local patterns and now you've identified global patterns, we're now simply going to answer like 100 questions. And depending on this question, you're able to say, okay, this is this digit or this is this one. Is this clear for everyone? Okay.
So, where does it start?
Yeah, sorry. Yeah, I thought it was clear. Exactly. So it starts from the bottom and you're going down here, where at the end you've got these numbers from 0 to 9. And then basically at the really top, so actually we can move in this, but it's just a bit hard to move in this. So that's why I'm like, I don't know, give me a second.
Yeah, I see.
Yeah, like, but here basically what you're saying is that here you get like values, and here, for example, you see that for 4 you're getting, I don't know, okay, like maybe there is, okay, exactly. Here the output is, oh, what is it for?
0.89.
Okay, I don't know, yeah, exactly, but like, but basically the point is that like, okay, maybe there is a problem with this representation, but the point is that like, for the digit that you want, which here should be definitely 4, so I don't know why it says 5, sorry?
It's 0 in next.
Yeah, so 5 is actually 4 because 0 is unit 1. So I think, so that is
Okay.
correct.
Okay. So, okay, so I'm like, so okay, so here you've got like, okay, so you've got 5, so then your output is like, you've got like, as it's a max, you say like, okay, here you've got 0.8, and your other values are even like negative, so you simply take the max value, and like, so you've got like, you now have like, you now make predictions for each one of these digits, each number is this prediction, so like you're predicting like 0, 1, 2, 3, 4, and here actually you say, okay, this is the prediction for 4, and this is the maximum value, so this is the prediction that we're now gonna settle for.
Going to check it for 1. I will check the 1.
To check the one.
For 1.
It says, yeah, because it says 1 is your, like, the second most likely guess.
So second.
So it'd be unit 2.
The number 1.
Yeah, I'm not fully sure, but like I think there's maybe indexing. Yeah, I'm not sure, but okay. But the point is simple. Yeah, like this is, and like the point is really about the receptive field, and that in the end you simply make your classification, and then you're really happy. And what's really cool is that like what we're gonna see now is that like this network can actually scale. So I'm gonna go back to the slides. Can you help me with that?
By the way, we're gonna build this network in exercise soon. So all this information in.
Yeah, actually, like this could be actually very helpful. Wink, wink. For like tomorrow. This like,
Where's the presentation? Where's your presentation?
uh,
PowerPoints?
yeah.
Yeah, I think you can just do.
If I just present, it's gonna switch again. Can you click here? No,
Current slide.
just yeah. Okay, really cool. Thank you very much. It's all right. Okay, so we've now like visualize this network in a fancy way, which is fun. Okay, great. So now I'm gonna go a bit deeper into the technical aspects of the network. So okay, so basically, so this was the first time where I mentioned was really like groundbreaking because it was the first time that we're able to make classification of images. So it was like really fun. And then like what people has done is that like they've basically been trying to improve this network into making like, and so like they came up with different tricks for that. And so one of them is, for example, to simply make the network much deeper. So here, for example, like, so this is a network called AlexNet, which was also very influential. And so basically here you see that you have like one, so each one of this visualization is a convolution. And so you see that you have 1, 2, 3, 4, 5 convolution instead of simply 2 from before. And then we also have 1, 2, 3 dense layers. So what we call dense layers is also like linear layers, convolution, feed-forward network. Like those are, sorry for that, the field of machine learning, we use many words for saying the exact same thing. So like that's, yeah, we're just like this. And so that's 8 layer. So like that was one of the key innovation of AlexNet, simply making it bigger. Another one that Alberic mentioned a bit yesterday was that instead of using this very nice and very smooth sigmoid or this 10H, people like the AlexNet team actually came up with this ReLU also operator that then they started to use, which basically means that like before 0, you basically like at 0 value and then you go up. So it's like, that's why it's like max of 0 than X. And it has many advantages. It's much more like efficient. It converges faster when you learn. You know, like this. I don't know if you remember. You know, like this curve that you just plotted yesterday of the loss. Well, those converge faster, and so if you converge faster, it means that you can use less compute. So like, so it's just great. So you're just very happy to have those things, and also there is no vanishing gradient, which is something that's going to be a bit more important later on, but simply means that when you have a deeper network, basically this gradient descent algorithm that we did, it's going to become harder and harder to actually solve this problem because the weights of the really early layers is really far from the output. And so when you actually want to change the very early on weights, like the gradient is going to be so small that we call it like a vanishing gradient. And so we're trying to have like, we're basically trying to come up with functions, and we're trying with many tricks, because it's a real problem that we have, to actually solve this vanishing gradient issue. So to make the output relevant for the early layers. And the reason for that is because we know that deeper layer work better. So it's like, okay, you want deeper layer, but you've got the vanishing gradient issue. So you're like, okay, like how can I do a trade-off of that? So that was one of the innovation. Another one was normalization. And what came with it was much more filters. So basically, instead of having like 3 or 6 filters, like the windmill was 3 filters at the really early layer, and Le Net, the one that I presented before, it was 6 for the first convolution, and it was a 5 by 5, but you were making 6 independent representations, so 6 different weight matrices that you had. Well, actually, like they also invented something called normalization, and like, okay, it's a bit like things sometimes get complicated, so like I'll just get to the main point and I'll go in detail. The main point is simply to say you've got all these different weights, and like if you simply learn like the same filters every time, it's really not useful. So basically you force the network to learn different filters. That's simply it. Because when you want to go from 5 layers to like 100, you need to somehow force this network to do this. So it's something that here we do simply by we're simply gonna like average the values of, so let's say that those are classifiers. This is X and Y. So this is like again the same input that we had before. So you have like first filter, second filter, third filter, fourth filter. Let's say we take the second filter. Okay, let's say we take the first filter, so filter 0, and we take like X0 and Y0, so we take this 1. What we're basically gonna do is we're gonna say, okay, we're gonna average this value with like the previous filter, which in this case doesn't exist, and the next one. And so you're simply gonna compute this number, which is gonna be a bit of an average, and it's gonna force the system to learn different representations. So it's one trick that they used. Yes?
Normalization, is it same thing as scaling, like in terms of normal day-to-day activities?
So normalizing helps you to scale.
So it's not the same as scaling.
It's not the same as scaling, but it's like as you're scaling your network, you want to have a way of normalizing.
Are you talking about scaling the image or the
Ah.
No, you see, he changed the numbers from those big numbers to smaller ones.
Yeah. It is a scaling operation of the image indeed.
Okay, that's what you mean. Yeah.
Scaling and shifting.
Okay, yeah.
Normalization is scaling.
Yes, so usually you scale down to numbers around 0, small numbers, and also you're shifting to a mean around 0, so no biases.
Yeah. That's simply one trick. Another of those tricks is called like pooling strategies. So the thing that I tell you not to worry about before when we said, we're gonna make this image smaller by subsampling or by pooling, now comes sort of handy, because before you could have simply made like an average. You simply say, okay, I've got all these values, I make the average of this. Okay, I've got like 36, 80, 15, and 12. What we basically came up with as an operator is like max pooling, which is like much more useful, where basically you simply take the highest value of each one. And the reason why it's helpful is because you simply get like the most prominent features from it. And so you actually want your network to learn from the most important features. So that's why we use like max pooling in general. And the reason why we're also just using like pooling in general is because you reduce the dimensions, as I mentioned before, so it's much faster to compute. And also by doing this, so it makes you much more efficient. And also by doing this pooling, one of the key things is that you can actually reduce overfitting. But yeah, that's maybe the evidence for what you know. Another trick that was handy is called like dropout. So the idea is that if you have so actually like let's jump into this overfitting issue. If you have this, let's say you have your network, and let's say like you train on a very specific distribution. If you simply now have like an element that was out of your distribution, you could give a really wrong answer. And so that's called like overfitting because you're trying to fit too much to the curve, and just having some errors actually may be beneficial for your system. So you sort of want to force your network to not be too close to your data point, because it may be that your distribution is skewed, basically. So what you do is that, like, in your network, you're simply going to randomly, and this is decided by a rate that you define, you're going to randomly drop some of those weights, and like, so drop some of those neurons, and then therefore like the weights in red that you see. And what this does is that, like, your network will have to basically learn like a redundant, because those weights like are going to be dropped out at random positions. So what this means is that, like, your network will need to do sometimes without some very important weights. And so what you do is that you're making simply like your entire network useful. And so you also create some sort of redundancy of information. And redundancy helps you to generalize. This is something that we've basically seen. Also, like, all these features and tricks, I think it's also really close, I think, to what John Jumper was saying yesterday. It's a very like empirical, like machine learning is a very empirical based science, if you could call it that. And so it's just sometimes like, okay, we're just like trying something out. We see that it works. We see that it generalizes well to many networks, and then we're just like calling it something. And we're like, okay, like now let's use this. Sometimes there is a reason for things, sometimes there is not really. It's just like an intuition of a researcher. Data augmentation is also something that LexNet use, which basically means that, like, to scale your data set and to have much more like images, what you do is that, like, you take the same image, like you take an image and you apply some sort of transformation. So it could be like you simply crop the image and you can like rotate it a bit, horizontal flipping. You can also play with the colors and like color jittering. And yeah, like, it's just that, like, if you increase, you may have heard that like data is the most important thing. And so, like, if you find tricks here and there to actually make your data set much bigger, it can be extremely like helpful. So this is like one of the key elements that you again may be using tomorrow. And then LexNet also uses GPU, graphical unit processing, processing units, and it was indeed spinning up training by parallelization. No need to dive in this. And they also are the people that came up with the idea of like scaling up also not only the parameters but also the data sets, going from like, let's say, 50,000 samples for the digits problem to the problem that we're solving. They went to like 2 million images. So it was a big scale up. Another key network is called ResNet, which also implemented like many things. And the coolest thing of them all is really this residual connection. So the point of this residual connection is that if you have this in a standard network, you simply have this input X, you have some weight layer, you have some activation function, you have another weight layer. And then this representation, you could call it like f of X. And then you apply another activation on top of it. What we basically understood is that, like, if you add this skip connection, so if you add the same representation X, but you added like later to the same network, it allows your model to learn this G of X, which is actually like easier to learn for your network. And so what you'll do is that then you'll simply like sum G of X and X, and G of X is just easier to learn. So that's why like it's simply better, and it allows you to make deeper network to actually do this. Because again, it's one way to diminish this vanishing gradient issue that I mentioned before. Again, as we're talking about making things bigger, the ResNet is actually 18 layers, and that's only one of them. So this one is called ResNet 18. But I think they even made the ResNet of like 120 layers. So like scaling is really like becoming like a huge thing now. So that's why like we really needed this residual learning trick. Lastly, batch normalization. So the idea here is, again, simple, is that like if you actually don't use, so what you do in batch normalization is that every time that you have some input data, you're gonna have like multiple parameters. So like this could be one parameter and this could be like a second one. And the idea is that you sort of want to standardize your parameters in such a way that like they're not evolving like in this weird space, because otherwise you may be You may be going out of range when you try to gradient descent. So the idea is simply like to normalize these parameters of your model. So like let's say this is one parameter and this is the second one. You simply want to standardize it in a way such as like the mean is 0, the variance is 1, and you simply do this for every data point that you get. And this is what we call batch normalization. And this is actually, again, extremely helpful for reducing the vanishing gradient and also reduces the exploding gradient. Exploding gradient is, some of you had this yesterday in your practice. It's like, it's simply when your gradient is becoming like, it's coming close to infinity. Because as you make all this multiplication, and like it goes to too much, like to a number that's too high, and then your model can't really learn anything because you're changing too much the values because of it. And that's actually it for computer vision. So now we can take a small break. And then after the break, we're gonna go about how to process text. So basically the building block, a bit of like like networks like GPT and things like this.
So, question on observation. We have about 5 cats lined up over here.
Yes.
And I want to speak a video, so, but I'm far away from them, so with the Fuji, I think the last Fuji is playing. Then this guy, sorry, he comes closer to them and takes a picture of them each cat takes a picture of each of the cats. And that one is very cool. But the one I took is very, I want to give me each of the cats inside a blurry image, and I want to make it very clear to see.
Can you repeat the end of the question because I'm not sure? Okay, like so you've got one blurry image and the other ones are not blurry.
Yes, but with the non-blurry one, he has the single picture of each cat. And the blurry one is just one picture of 5 cats inside.
So I understand like the setup. What's the question?
Yeah.
So the question is, how can I make a blurry image? Based on
Okay.
Yeah.
So like actually upsizing an image, like adding information to it.
improving the.
That would be like a stable diffusion problem.
Yeah, exactly. So actually, like, I really see where your question is coming from, because I first introduced convolutional networks as, okay, we have this image that's blurry, and like, let's use convolution to take the blurring out. So it's not really why we use convolution. It was more a way for you to understand how convolution works, because then you understood the sliding window. So it was really like the basics of that. But in reality, you wouldn't use convolution for these blurring images. You would actually use a method that I'm literally going to introduce, but at the end of the second hour. So like at the end of the second hour, indeed, like Casper mentioned the model that we're going to use in the end.
So this is powerful, So this, in what you just thought, is the general idea.
Exactly. So now you learn like literally like now you're supposed to have understood a bit the general idea of convolution, and I hope it was clear. My hope is simply that you got a bit the intuition of what convolution is doing.
Yeah.
That's really the main point that I want to go through. Because like if I just show you the math, you can read the math in yourself. You can all read math, you can all read like you can all make basic calculus and linear algebra, like so that's why I made like many examples. I hope it's helpful. Did you understand everything? Do you have any question? Maybe something that was skipped or a bit too fast or?
Would you, like, just out of curiosity, if you had like, you wanted to denoise the image, would you put it into like a variational autoencoder and then like sample it like that? Is there like a difference in like which one's more effective?
Okay, so I'll literally go on this at the end of the other hour, because then we're actually going to talk about generative models. So we're going to talk about auto variational encoder, like VAE, diffusion models, GANs. But yeah, like you really get the point of VAE and diffusion models basically.
But there are always many ways to do this kind of
Yeah,
thing.
exactly.
So actually you could, like the early days, you could just do supervised learning. So you add noise to your image and
Yeah.
you just train directly to remove all the noise. And you can just have just a single model convolutional, resonate, whatever you want, MLT even, doesn't matter, just process it, try to predict it, and you get some result from it. Now people use more advanced technique, but you can definitely do like a little bit of exercise today, you can have fun on your own tonight, try to do it. It's not so hard, like you get a lot of images, you have noise. And here's when you put output.
This is not part, with the noise removal. I'm talking about, you see, random forest is this. Can you use that?
You need random forest to get away with noise. So like you could, the thing that random forest is not really made for image data, I have to say. Like, so I wouldn't necessarily use random forest for images, also because you've got all sort of problem with like spatial representation. So like, let's say like, how can you, this pixel is on the left, this pixel, like, okay, how, like, what would be learned for like, again, like, random forest would be, how, like, to make, like, it could learn it, but it's hard for it because, okay, like, a random forest, you're gonna have, let me actually write it down, so don't be,
Because I read one,
okay, so let's say like, this is basically what you get, okay? And like, and it's like, this is your image with many pixels. And the things that like, in the random forest, you're gonna like give this every time. And like, so then you're gonna have like this representation. But then what you're also gonna give is like, you're gonna take this, then you're gonna take this second row. And then you're simply gonna like pad them one next to each other. And the things that like, then it means that like the random forest needs to learn that like this element is this one, you know? It's on the left side of the image. So it's gonna be hard for your random forest to learn this visual representation, basically. So that's why like, I'm pretty sure if you can solve it with random forest, I wouldn't be surprised if you can. But I would say like, I wouldn't use that. I think I would use indeed, if the example they really wanna like actually the method that you mentioned, which is, you see that there are always 5 colors that are always redundant. You create a data set where like you add noise with these 5 exact colors, you train your network on this, and then you're gonna solve your problem with your actual image. This is something you could do. Or you could use diffusion, or you could use, it's like there's many ways of getting to the same answer. Or you could actually use CNN and do an average. Like you're just gonna lose some resolution. Like it's, yeah, exactly. You could use simply like a simple convolution, not even a CNN. Because CNN is for convolutional neural network. Convolution is simply one operation. If you do one convolution, you're gonna be fine. It's just that now your image is gonna be a bit blurry. If you use a diffusion model, normally you're supposed to get a better sense of, like your image is supposed to be more realistic, right?
so, do you think sometimes you use the nearest nearby, to balance distance?
I mean, like,
I think we saw certain limitation that it was, but.
I mean, you know, like it does like nothing to do.
Yeah.
I mean, it's like, it takes you like 5 seconds.
Yeah, very easy.
So it's like, if like we're in a meeting, you're just like, you're like, I have noise on my image. I'm maybe not gonna learn, I'm maybe not gonna like train an entire neural network for this. I'm just gonna be like, okay, you know what, like I know that like nearest neighbor is gonna work. So if I do like if I just apply convolution, that is simply doing an average, I take a 3x3 convolution, boom, I know it's gonna work for sure. So actually, like if it would be me, I would maybe just, because I know it's you literally do convolution times something. You don't do any learning the weights. You simply initialize the weight to like it's a 3x3 by 1/9 each weight. Boom, you know it's out. No worries. You have time, now we can start in like 5 minutes. Yeah, if you want to grab water, coffee, bring it back from like.
Does it happen with condition? Yeah. Then, start in 15 maybe. And I send the schedule. We're gonna see the size. So I mean it.
What is your name?
Thomas.
Thomas.
Nice to see you again, Casper.
What's your,
Good. So, for this group, like fairly decent, I took a machine class a couple of years ago, that was like, meant to also do like a little bit of like biology intensive. It never really ended up, because that was like 3 or 4 years ago, and I never like applied it afterwards. Like I was like actually figuring like found like full project, like final project notes, which was cool.
but this,
But other than that,
your ideas about private.
yeah, the project that I'm working with now, I feel like has that opportunity, so like, sort of the bare bones of it is looking through the genome for specific spots that a protein is editing for over others. And some of the information I would have is like, whether it's what transcript it's in, or like what features that, edits that would be within like an untranscribed region or something like that. And then, because of this now, like, no one really knows how to mechanism works, there's like some like very light, or should I say very broad rules people like they can apply to, but kind of find those. If you don't know at all what you're looking for, like machine learning is like a good tool for that.
Yes.
And then eventually like you probe the black box after to figure like, if I can't figure out what it actually is using to identify these sites.
Like, so, those redness, like, are they software? It's actually, like, it could be actually. So, okay, so the way, okay, like, I'm just gonna, maybe like, if people are interested in it, I'll just be here. Like, if it's interested, you can listen, otherwise it's okay, I'm just answering the question is, so for Zoom, the question is like, those methods are represented, LeNet, ResNet, AlexNet, are there like models? Are the methods?
Yeah.
Are there software?
In my head, that's step 2, step 1, it's just like,
So-
getting something to work that
Basically,
is memorable. Cause I feel like, the answer is probably some form of like categorization
and so
my
like
brain
people are
can't
trying
do
to
that,
address it
there's all
versus
these problems they have, but.
for example, image classification. When they do, they're gonna come up with some tricks, like actually like AlexNet, LeNet, whatever. And so they come up with a very
Did you,
methodology. And then
are you from,
they,
like
and
now, or
that's
like, is that what you did your
even
previous
like
degree?
open source the
I
code.
remember you said.
Then you open source the code of what they do. And now it's very common that like as many people train neural networks, so you can find like common libraries, like in Python, for example, where you're gonna be able to find any of these models, and you can directly like pull them up, and you can actually use the models like right away. So for your own modes, for your own problem. So some of them will be like PyTorch, or TensorFlow, like so. Like
Yeah,
I
that's
know
the thing I
someone
really
like
regret,
PyTorch.
is not having like a stronger computer science background.
Maybe it's like.
I feel like as a, my undergrad did
Yeah,
mine,
so
I feel like I know like
in
a lot, like a little bit about a lot of
I
stuff.
just want to use the
Like I understand the conversation is happening, but then sometimes I feel like I can't really shoot as much as I'd like.
Yeah, you can do
So
this.
like half understand what's going on.
What you can also do is that you can also like, I think that you can probably find a building block somewhere, like the general
Like
library.
Stack Overflow is
You
my
can find the entire code.
absolute savior, like I'm gonna look up every single time I do something.
I'll find it.
Like I'm good at like the creative parts of the code, but then there's just like actually.
But actually the code is actually pretty simple, like when you think like, okay, it's like.
Yeah, John first talking was like, wow.
You simply apply one function
Yeah,
to
so
the
did
next.
you like take
in a
any
forward pass,
classes
and
at
then you
all
go
into
back
bio,
class,
like
you then try
post high
to say,
school?
okay,
Okay,
I'm
so
gonna
all
apply
like
gradient
self-taught,
descent to learn the way to an optimal way. So like, so
I
this is
can't
just a
imagine,
general
like,
idea.
as it is now,
And
like, a lot
then
of women is like, they're all bi people, and I feel like I don't know what the hell I'm talking about.
Just like the math that you're saying, it's just like, okay, well, like here we have like a linear layer, then I apply like a redo, then I apply some pooling, then I apply this, then I apply, and I'm now going to do this like 20 times, and that's like a resonance. Like I'm going to do 18 times, and resonance. So I mean, like,
It's like a module inside.
exactly, it's a module. Actually, it's the keyword that I could have told you.
I was just wondering what's.
It's literally like a module. So you can create your own modules based on those modules. It's like, and that's really what the growing is like you like, for example, like when you try to make, okay, so for example, Alberi in this lab, he's making RNA prediction. So he's trying to predict a bit like AlphaFold. You have an input sequence, and then you try to predict the structure. When you try to do this, well, like they actually use they use many building blocks that have been built for other purposes, just like evolution, such as like, so it's like you reuse modules, you modify them, and you use them for very different missions.
Like people here use, like is that, I'm trying to think, is that a thing?
Okay, so Harvard is really bad with this. So it's called O2 and it's always down.
Basically, yeah.
And like always under maintenance.
Yeah.
So I like don't even remember how to get it.
But by the way,
anymore
just in
because I
case
just
I'm
couldn't get it.
not if you don't
Yeah,
want
so
to
is it like a
code
hard
everything,
or like for everything?
you can, for example, there is Class.ai,
Really?
and it's like you also have libraries, and like here, like you're definitely gonna find like every, like the most common.
Even still though,
people
that.
in your network, like your network that you want to train and use.
No, I was like.
Like it's
I
just
saw
another
trying
library
to
just
get
to
my
like,
uncles on the festival that they
I was trying to get it right.
I mean, whatever, but like that.
I found
Like,
like.
what's
So I agree.
that?
Like like, you know, autoplays or like.
Visualize.
Yeah, we bought like, instant pots. To like use it too, because the others are always running it, so they use it.
That's what it is, adapting.
I'm sorry.
So that was for this.
They're like your improvement because you're fancy auto please.
Okay.
They were great, but you can only do a liter at a time.
Yeah, I was thinking like how those things are on all the time.
Yeah, it's really bad.
Okay.
That's sad.
It's like the area.
Like, was there any question in the chat that way or?
The way they built it is like, water tank that runs.
Do you have any question in the chat?
And so.
Is there, yeah, I'm just talking to the chat. Yeah, if you have any question online on Zoom, really feel free to ask them. If there is anything that was maybe sped up, or was too fast or anything,
I
like,
wasn't sure if that was actually.
please let me know.
No, I think it's.
You know, we're gonna start soon in about like 1 minute. I also ask the physical audience whether they need that with something. But yeah, I'm like, but yeah. So like, I'm like, it's cool that you like take interest and like, thanks for asking questions. That's great.
Wow.
Like really, like, it's much better to ask questions and then like, you actually. Yeah, and also, you know, if you have a question, it's probably because like I didn't explain well something, or it's not clear. So it means that other people probably have the same question as you. So like really feel free to ask more.
But not to me, I asked her about the community cluster in the building and that's the golden answer.
Yeah, and also thanks to that guys for participating in answering questions and trying out even though sometimes it's scary. But like,
Happy to contribute.
My one neuron is firing.
Was everything clear or like, okay. Okay, great. Was there anything?
I think I don't understand like 100% the idea behind like looking at like the kernel and being able to tell like what feature to predict. Like as well, like I think I get it like very broadly, but when it comes like the really complicated one, like the circular detection, I guess like I didn't really get that one as much.
The one, the visualization, right?
Yeah, like once I got to the flowers thing. That like I understood it in terms of like, oh, like I kind of know what this looks like, so I can know like what it's looking for, but I'm sure that's not always the case. I don't really feel like I have the best grasp on it.
Yeah, I mean like it's it's more just those visuals are more like to give you the intuition. Like it's and also it's like you never really have to like actually okay like very funny thing. It's like I've almost never seen those kernels. I'm only outputting them for you.
Yeah,
just so you know.
So it's like I understood this in the paper,
So
but I don't actually care.
if you ask the test, like maybe he's like, okay, like let's ask Andrea a question. Andrea, have you seen one of the kernels that I've displayed? Like you train CNN, right? Okay. Have you watched the kernel that your model is learning? Like in the last year, have you watched one?
No.
Okay, in the last 2 years?
Maybe the understand where in class.
Okay, within class, exactly.
Okay, makes me feel better.
So it's not like so you never watch them.
I'm gonna write a passage today.
Exactly.
You were finding yesterday,
Yeah, everything's a rite of passage.
Exactly.
It's like manually writing once so that you never have to do more.
Yeah.
Okay, so yeah, like so then if you just get the idea that you're just learning those weights that then represent some sort of feature like Waldo, and like if you learn this striped t-shirt, then you're able to like identify Waldo. It's the same. It's like okay, you know, if you learn these features that is called wheels, well then you know what, you're able to identify cars or motorcycle, and then if you're able to identify doors of cars, then you can identify that it's a car. So it's like 4 wheels plus doors in the car. So that's a bit what your model is trying to learn. And that's also a bit what the model is trying to learn in those residual connections. But yeah, like there's some part that I went a bit fast on them, so those, because they're not super, like all those small tricks that I mentioned, it could be useful for you, so it's good that you know they exist. But like,
And knowing the exact how they work isn't too useful right now.
yeah, exactly. Yeah, so I'm just outlaying that.
So in architecture, like a layer of the neurons will obviously have like different weights and biases, right? But is it like kind of standard that within a layer, all the neurons would be identical, like in terms of like sort of like the like they're like what they're going, like all of them are gonna be like addition, for example. You're not gonna have like half their addition, like half for multiplication in the same layer.
Okay, like so I'm not sure you're working the like because you're now like
Am I not, I'm misunderstanding.
because now you think that the operation is in multiplication or addition, so I'm not sure.
I'm not saying that's what I do, but like, so like a layer is made up of like many neurons, right?
Yeah.
They all have like different weights and biases,
Yeah,
but they're all similar, because they're all maybe like giving like a convolution of like 3 by 3.
Yeah.
Like, will all the, like, is it kind of standard that like all the neurons that we're doing a 3 by 3 convolution, you'll have like half doing 5 by 5? Like,
I think the question is, in a given layer, does each neuron have the same activation function?
Yeah, exactly.
yes,
Okay, so-
that's what I'm asking.
Okay, so the activation function that you apply on them, yes, so it's like you have this input, so it's like you have x, the vector, then you apply the same function on x, so it's like you have f of x, okay, like this thing, but the x values, so x0, x1, x2, xn, are very different from one another. And it's actually something that you sort of try to push into the network. You try to force the network to a bit of, to actually make big differences. It's one of these normalization tricks that we have, but like there is so many that sometimes I just say, yeah, this is normalization. And yeah, like if I do that something is like I use like a keyword that's supposed to be obvious, don't worry, like it's not, like maybe it's not obvious. Like, tell me if you don't understand better. Okay. Any question in the chat? Because we're just answering some.
Yeah.
Okay, now it's good.
Wait.
Okay.
They said you're muted. We
Oh,
can't
it's
hear you.
just responding to my message from 1 hour.
Okay. Okay. Okay, great. So is it fine for everyone if we start again? Okay, we took a bit of a longer break, but I think this was well needed. So, is everything okay? So. Natural language processing. So basically, like, we just now want to make prediction, but about text. This is what we call natural language processing. We also call it like NLP. This is what LLMs are about, like large language models. Okay, like just as a starter. So there are many types of sequential data, and if you would make like families of them, you would have actually like 4 families basically. One is like 1-to-1. So like let's say I don't know, you have like any sort of function that like you just have a score to it. It's like you have some sort of input. So every time red is input, green is sort of like hidden layer, and then you have in blue the output. And the question is, okay, it's like here you have 1-to-1. So that's the key family. So here it's like simply like say like a scoring function. Like doesn't matter what the function is. What you can also have is an example when you have like 1-to-many. For example, you take one image. Let's say you take like you take an image of an animal, and then you're trying to know, okay, like of which animal is it? So then you try to make a classification. So you have like many classes that are like the prediction that you want to make. Many-to-one could be so you have, for example, like a text, and you want to have some scoring about this text. So the input data is many because it's some text that like could vary in length. And then one could simply be, okay, like give it a positive or negative like value. So it's like a value that goes from -10 to like 10. And it's like, how positive is this sentence? Is it like, hey, that's great? Or is it like, oh, that's very sad. I'm sorry for your loss. And then you've got many-to-many, which is actually the problem that we're going to tackle, because actually, like, could you think of an example of many-to-many problems that you have, where the input sequence can vary in length, and the output sequence can also vary in length?
To refine text.
Exactly, like modified text. So you've got a text as entry, which is like varying. And then you've got a text as output that is like, it could be much smaller, it could be bigger, you could ask it to write it more, exactly like what you do in GPT. You could also say, for example, translation. Sometimes in some languages, like you're gonna have more characters or less characters. That's one example of it. Okay, so now that we assess that like natural language processing is a problem of many to many, like translation, let's look at this, let's look at a sentence. So the students, after reading the book, was well prepared. Let's say that you would like to translate this sentence to like another language, like let's say Spanish. Would you use feed-forward network for this? So like a linear layer or an MLP or like perceptron, like whatever name you want to call it, but like yeah, let's call it feed-forward network. So would you use such a network for a sentence like this? Feel free to answer, yeah?
Really?
Okay, like it's maybe not what I would do. Like, but I'm like, why not? You know, it's like so me, I would actually say like I wouldn't use it. But then the answer is like, why not? You know, like why I'm like, why wouldn't I use it? And like in the fully connected network, what is, I don't know if you remember, I'm like I can also go to that slide. But like I don't know if that works if I click. Yeah, exactly. So in the MLP, for example, this is a fixed length. So it's like, you know, it's like we have this input that is a fixed length, and then again I've got another fixed length here. So, and let's say I would even have multiple classes, it's still like everything is fixed. So for a problem that is about sequences where the output may vary, would you actually like use a feed-forward network?
Is it no, because you don't know if the translated word is gonna be the same length, or even if the same number of words are gonna be there?
Okay, so that's exact. So that's one part of the answer. That's one part of the answer. Another part is also that then like, okay, let's say that you have a task with 5 words, and then like we're in a language where like it's gonna be 5 words in English, it's gonna be 5 words in French. Well, let's say the sentence is exactly the same amount of words, like simply in French. Well, the thing is that then do you need to have a question for you? Do you need to have a network for every length of sentence? Like, is it what you're gonna do, or?
It's not what I would want, no.
Okay, if you don't want this, is there maybe could we do a way? Like, could we find a way of? I'm like, do you think that it will work basically if we would simply pad zeros? So I don't know if you remember it for the image, you know, but like we added like pixels around it that were initialized at 0. So it's something that we've seen for convolution. So like, would you maybe do that for with a feed-forward network? Like, if you think a bit about it, do you think it would work or maybe not? What would be your? If you just don't know, you can also say you don't know. Yes, yes. Go ahead. Yeah.
Sorry, like if you made filters, like you would have to make a filter for each word maybe, and then like translate that into the word in the other language, but that seems extremely inefficient.
Yeah. So let's still go back to so you would do padding. So like what I mean by padding is like so let's go like thanks a lot for your question, because I think that I was not clear about something. So when I mean padding, I mean like okay, so this is your function, and I'm saying like okay, you know what, like here you have like 3 words until x2, and then you say okay, like then would you add them, like if you want to use one network but for also like a much longer sentence, would you simply initialize all the other values at 0?
Oh.
That's what I mean. So thanks a lot for your question, because I was not clear. So would you basically put, like if you want to use one network that is a feed forward, you have a really long network, and you say, okay, this sentence is only 5 words long, so those 5 words I give them values, the rest I put zeros. Do you think that would work?
Well, what about the output layer though? Like the output layer is still fixed, right?
Okay, you could also pad the output layer. So it's like you could have like again here, and you just teach the model to give you back zeros when the sentence is over. So you could also do this. But do you see the problem that then we're sort of having like, I'm like basically you're gonna have a network that is gonna be extremely wide, and that you're most likely never gonna use the other weights. And also it's like if you learn a sentence, let me go back to the Yeah, and another problem that you have also is that like outside of having like this very wide network, your network is gonna be very much overfitting on like, okay, if I learn that like I don't know, the cat is soft, or like the cat is black, if then I'm changing the arrangement and I'm saying the cat of Michael is black, and like then it's like, okay, but now like I just changed like some sentences, and like I just changed the word location, and now like the network maybe won't work if it's not been trained on this specific sentence. So like, so the problem of this is that then it basically means that like for each, like using a fully connected network for this would mean that like you would need to have like infinite amount of data, which is not really feasible. And also it's like you would need to basically have like data of every potential sentence that has ever occurred and will occur. So that's too much of a problem. So because of this, we're like, okay, so too bad. We just learned about like feed-forward network. Okay, like we just learned about deep learning. We know that we can approximate any function. I would like to, I think that like mapping, like finally Indian, like translation is a function. I go simply from like English to Spanish. It's a function when you think about it. Like why, like how could I represent this also using deep learning? Like it's a bit tricky. So let's say, okay, like let's say we want to simply predict like the next letter. So like here, like what would you think would be the next letter after like this H?
E.
E. Okay, really good, man. Amazing. What will be the next letter after that?
L.
Try your luck. L. Okay. Next letter after that.
P.
Good one. I should have put that on the slide actually. That's an improvement for next time. Okay, in this case it's gonna be L, which also works. And what will be the next letter of this? O. Okay, really good. So now we've got like L. Okay, so what you've basically been doing is that like you sort of have an idea of like, okay, I know H and I know how likely it is that like, I'm like, okay, you're basically thinking like, how many words do I know that start with H? And which words could I basically use? Knowing plus a bit the distribution of words, you're like, okay, I know that E and A are more frequent. Okay, so you make a bit this sort of computation in your head. So now let's try to do this, but like into a network, okay? So like, and let's actually discard what I said, and let's still like, okay, like, okay, so we just make simply this network, and we say, okay, so we've got these input characters. So here we've got like H, E, L, L, and then for each input, you want to basically show, okay, what's the next letter? So this is, so I'm like, so for each input, you try to predict the next letter, and that's just the network what it's doing. So how would you actually represent these input letters? Like, how would you, like, now that I would need to, because it's something that for images, actually, when we talked about, we just assume that, we can just give values to, like pixels. Okay, because they're pixels, it's maybe easier. But, like, how would you represent the letter H?
Either like the numeric for that for that letter, so like 1 to 26,
Okay.
or maybe like a vector of 26 where it's just a bunch of zeros and then the 1 for the H's.
You're reading to my mind. You could do like one-hot encoding, basically, which is what you're describing. You do like, you basically do a vector. It could be of size 26. You can also represent this information in a bit shorter vectors. So here we took like 4. But that's basically the idea. Exactly. And basically, you're also going to have a representation of the output, because as we have this input representation for each one of these letters, we're then going to make some sort of computation in the hidden layer, okay, which now is not seen. And then at some point, you're going to need to make some sort of prediction about what the next character is going to be. So you're going to need to match that at some point. You're going to need to go from you're going from a letter to a number, like to a vector, to then another vector, and this vector needs to be associated to like another number. That's basically what I mean. And like, how would you, like, as you know, fully connected networks now, like what it would look like, this graph, if now you would like put a fully connected network? You've got the input layer, the hidden layer, and the output layer. Just simply like, what would you, like if you need to draw it here, like what would you draw basically?
Sorry, question.
So if you would need to draw if you need to draw the represent, like if this would need to be like every time like a fully connected network, what representation would you use basically like here in the middle? Maybe I'm just gonna
All four connect to one.
okay, so actually like that could be the case. But the thing is that like here, so that's actually a really good question that you're asking. But the thing that we're saying that we're predicting the next letter. So like imagine that here you only have H and you're trying to predict E. So actually you wouldn't have this connection, which you're referring to. You would simply have one connection. Because sorry, like we're acting a bit as if like this is masked. So basically you would have something like this. So you have an input layer, you have this hidden layer with like values that you computed, and then you have like for each one of these inputs, we have like a specific like weight that we've learned.
Oh, so
Okay.
this assumes we only know one letter before, like say for like the L, we don't know it's HE, we just know it's E.
Exactly.
Okay.
Exactly. Like, and this is actually going to become a problem. Because right now, like I'm like something that we've said is that like also like but like now we presented a fully connected network, but we said that this wouldn't work. So like, you may be wondering like, okay, but why are we doing this? Well, it's the only thing that we know. So we're still like being like, okay, can we still make this problem work? And then we're like, okay, so because actually when you think about it, like we know that the problem is about the position of the words. It's like if you've got a word that is at position 1 or if it's at position 25, you don't need to learn different weights for each of these specific. But like you can't simply learn about like every position of every potential word. It's simply too big as a problem. So one way that you can actually like remove this positional weights by having like x1, x2, x3, and each one are different from one another, because that's what a fully connected network is you can actually share all the weights. So you can actually say, you know what, like, doesn't matter what the input is, I simply multiply it by some sort of like big, like, matrix. And I do this like twice, so I do this like when I go from input to hidden, and when I go from hidden to output. And you're like, okay, like, fine. Like, so this is actually what we're doing. Fine, okay.
I have a question.
Yes.
Sorry, it's not like I'm trying to drag us back. Now, talking about these letters where like the hello word is actually being encoded, does it mean for every word there's some sort of coding for every word like that exists? Like I mean, since you said hello and H is at metrics at 1, E is 1, 2, hello is 1, 2, 3. Does it mean for every word there's a coding for every word that like exists?
So this is something that we could call like embeddings. And so the idea is that we could you can create a space. You can create your own embeddings yourself, where like each word can be on these embeddings, and where like it can be a vector of any size, and you can normalize it the way that you want. But so here the point is to say, okay, like we basically try to build like a fully connected network. So each weight were different. And we're saying, okay, like let's try to share all the weights, at least for each layer. So now like this way, at least like, okay, I'm like, means that like if I have an H, I simply multiply by this value. If I have an E, I'll simply multiply by the exact same value. But the thing is like, are we not gonna have a problem for the second L and like this one? Because what I'm trying to show here is like, okay, so here we know that like, okay, as you written like hell, like as you have an L, you don't even know the words before you. Because you said like, this is not even taking the inputs from before. So you simply know L. And you want to predict what the next character is going to be about. Well, if you know that the most frequent one is like hello, you could be like, okay, like next letter should be another L. Okay, fine. Like next letter is a, but then the problem is that like for the second L, it doesn't know that this is a second L. It just knows it's an L. So it's like, okay, then is the next letter after an L like another L? And then you just like output as many L's as you want. No, it's like, it doesn't make sense. So like these individual predictions that you do to go simply from one letter to the next letter it seems that it doesn't work because like we don't know what's before. You need to know that you're the first or the second L, like you need to know where you are in the world, And so how do you think we could include this past? Like, how do you think we could, like, because what the feed forward would do at some point that you mentioned would be like, okay, you would like do all these connections, but we know that we can't do this. So what is a way that you could think of to be like, okay, like we could include the past. So like when we're here, we could know that actually there's been like H, E, and L before me.
You connect the hidden layers.
Exactly. Thank you so much. You exactly connect the hidden layers. Like, and what you've actually been doing right now, like for the last 10 minutes, is that we've literally just created a recurrent neural network, which is the first architecture that was used to actually process text. So it's actually quite a big accomplishment that you just did. Like, it's like really like, you don't know, but simply by common sense, a bit of intuition, you found this architecture where you now, for each input, you have the same, you have the same matrix that you multiply this representation by. And then as you're inside of the hidden layer, you simply give the information about the previous letter to the network here. And so it means that like somehow you hope that like when you're right there, this representation times this weight is going to be meaningful for here, for this representation, and it's going to be able to figure out that like, okay, like we already encoded like H, E, and L. So like, okay, like now it's going to be like another L, and then it's going to be like a no, you know? So like, good job for this, guys. So this is a sort of a bit more classical way of representing this RNN. Just to briefly explain it, you've got different input. So you've got like XT like -1, so that's the previous word that you got. You've got the current word, the next word that you got, or like letters as you want. You've got this hidden state in the middle, and with like what we call HT is going to be this hidden representation. And indeed, you know, we're going to have like these one connections that go from input to output, so these two arrows, but we'll also have like this one arrow in the middle that is indeed like sharing the hidden state about the previous letter or word. But actually, like this architecture has some problems. And so even though it's like really cool because now we're able to like work with text, one of the big problems is that like first, you cannot really train this in parallel. So, and the great thing about GPUs is that you can make big computation in parallel. And right now you can't really use GPUs, so you're a bit sad. And the reason is because every step is depending on the previous one. So it's like every time, like you're waiting, actually when you're at XC, you're waiting for XT -1 to be completed. So it means that like you're always by definition sequential. You're always waiting for the next step. And another one is that like, it's actually really hard to like give a sense of like the previous word at a long range distance. Because you have to imagine like you're simply giving like this output of this hidden state. And at some point, the more you give it to another state, if then you have a sentence that is very long, or simply like you're referring a character that is called Michael, and then like 20 lines later, like 20 sentences later, you say he, then it's going to be super hard for the network to understand that he's referring to Michael. So that's like a second big problem that we had. And so what people came up with is that they actually came up for a solution of the second problem, which is, okay, like how can we make like this long distance relationship work? And it's a big network that was called like long short-term memory, LSTM. I'm not going to dive in too much into the details of this network, but basically what you need to understand is that we're like, okay, like is there a way that we could store this hidden state in a gate mechanism? And so like we came up with like different gates, like a 4-gate gate, an input gate, an output gate. And the main point of this was to say, okay, like somehow like we're going to keep the most essential information. And as we're going to go in this network, we're going to be able to reuse that information later. So that's the basic intuition. You don't need to know more than this. And the math actually can become a bit complicated in here. That's why I haven't shown it. But that's sort of the graph. So like you have your input X, you have the hidden state here from the previous element, and then somehow like you have this 4-gate gate that's going to decide whether or not to keep some information, and then you're going to like multiply it here and then you're gonna use different types of gates. You basically multiply your signal, like you use the signal like many times, and you try to somehow like compound these representations. But the drawback that we still have with this architecture is like still the same one before. It's like it's still not parallel because like every time you're still waiting on the hidden state from before. So it's like even though we solve one problem, we still have a second one. So okay, like let's refocus a bit on the problem. Yes.
Could you just explain how RNN works at inference time? Like, what's the flow exactly when you really want to do prediction with small ones straight? Like the slide before.
So this one.
I went to the slide before. Like, when you really want to do this, because here it looks like everything is together at the same time. But what's happening when I really want to do from hell to hello?
Okay, so thank you very much. Okay, so let's go it like step by step. Yes, sorry, maybe that was not clear. So okay, like I've got H. So like let's say like okay, like I don't have this slide made, but like let's say like this don't exist. Okay, these three elements are in existence. This also doesn't exist, and we also don't have this. Okay, so basically the entire right side doesn't exist, and we also don't have this up here. So it's like okay, now we have those weight matrices that were already computed that we know we've learned basically, and so now we're going to compute okay this vector H times this weight matrix. It's called XH. It's going to give us this element, which is the hidden state. We're going to store this element here. That's it. And then we're going to multiply this element by another weight matrix that we go from like hidden layer to output. So then we actually make like this element. Okay, so it's one like this. Boom. Okay, done. And then as we're going to go now from like to E, now the thing is going to be, okay, so I have E, I'm going to multiply E by the same weight matrix that goes from input to hidden state. And now here I'm actually going to use both, I'm like to actually come up with this number, I'm going to use both this representation, this weight matrix, and this weight matrix. And the thing is that like this is going to cancel each other out, and like I'm actually going to have like this one still main representation that I can keep going on with. I'm not going to go into the linear algebra of it, but basically you're able to have the previous relationship this with this word, and you can make one representation of it, and now you can make your prediction about the next character word. And so you're basically going to build this thing as you go on, because every time you understand that, okay, we go from input, okay, next prediction, and then we're going to be, okay, so now we need to wait for the previous hidden state, and you need to imagine like this, you're simply every time going to wait on the previous one. Was that clear, maybe?
Yeah. I think it's really important to understand that this is this autoregressive approach where you start with H, you're gonna predict E, and then you take the output and it's now your input.
Yeah.
E as input and you will predict L. How do you initialize this though? Because the E prediction to go to the L use some past outputs, but the H prediction to E, how do you initialize it? It doesn't have something.
You mean the H to E prediction doesn't have a. So, I'm like, you mean at inference or you mean at training?
Yeah, inference, basically.
I'm not sure I'm fully getting the question, to be honest with you.
Because basically you have one model that's predicting everything
yeah,
always
exactly.
the same way. But how you differentiate when you start, it's a bit different in this image.
Yes, I mean like so when you start you do need to actually like in the RNN I'm not fully sure whether or not they give a sort of like beginning of sequence token. I don't think they do. Or like I think that like okay, I think it's more of a technical question, but I think that they give a hidden representation here, they feed it to the first one. That basically is maybe zero, or that is something that is an identity matrix, which means that this is just the beginning of the sequence.
Why didn't it predict O?
Sorry?
You know, after the first stage, why didn't it predict an O and then it started to bring
After the first
two inputs H and it predicts an E and that's all. Yeah.
okay, so okay, that's actually a good question. So I didn't want to dive in too much about those numbers, but I just wanted to show that they're numbers and that they're here. So the things that like then as you use one-hot encoding here, here you could simply do the inverse and simply take the max value and be like, and I'm like, if it's 1 out 10 coding, you can simply say, okay, I take the maximum value, so here it could be the 4. But the thing is that like 4 is actually giving you like another letter. It's not giving you H, it's not giving you E, it's not giving you L. Exactly as you said, like it's giving you, I guess, O. So the thing is that the network is just wrong, and that what you would want to be high is the value that is in bold. I just wanted to make it easier so I didn't dive in, but yeah, so here the idea would be like at training time, you would actually look at this, you would say, okay, but this is a number that I would like to be the highest. So like you should do some sort of gradient descent to make this number smaller and this one bigger.
But it's true that if you train on the direct English dictionary, you might learn that after H there is O, not E.
Yeah.
Maybe to create the word hour.
Exactly.
It's almost like a statistical model where you're gonna take the most
Common. Yeah.
And as you start generating, you kind of have to converge down on the word. Once you start to read H and O, you don't have so many words, so it's probably gonna be U and then R.
And if you're and if it's at the beginning of a sentence, it can be confusing. If I'm saying, at what time should we meet? And then I said like, let's meet in 2HO, you're like, okay, like most likely it's gonna be 2 hours. So your model is gonna at some point understand a better representation of, okay, this is how we make sentences. Okay, when you're talking about meeting, you're talking about time, and time refers to like, okay, like words like hours. So your model is gonna understand at some point like this idea. But the main problem of RNN and LSTMs are really like they're not parallelizable. So I show now. So now the main question is, okay, so now we need to have something. We need to have a representation that's parallelizable. We first it can work with text, first of all. Second of all, it needs to be parallelizable. And third of all, we need to have like long range distances like relationship. And so here, for example, like how many relationship would you say there is for love? Again, like I'm sort of like putting it there, but so like love is like, let's say I love, so like who loves, okay? What? It's like machine, but okay, it's like actually machine learning. So it's like 2 words. So it's a bit of a tricky example because now you're thinking, okay, I love machine learning. Like, how should you make sense of all of this information? And so we're actually going to introduce like, actually probably one of the most important architecture of deep learning and of nowadays. And it's going to be a bit difficult, to be honest. But I'm going to present like 2 types of visualizations. First, I'm going to explain it to you. Then second of all, we're going to rebuild it together. And I hope that you'll like get a sense of it. Like later on, you also see like another visualization. So I think that should be helping. So this operation is now called self-attention. And this time we're just going to build it straight away. So you have as input, I love machine learning. Like RNNs, we have some embedding that we mentioned for you. And so like we're actually going to have like an embedding of like each one of these words into X1, X2, X3, X4. And just bear with me. We're now going to multiply each one of these input by 3 weight matrices that we've learned. And like we simply know this weight matrices. So it's like now like we have WQ, WK, WV. And we're now going to multiply each one of these words, each one of these embeddings by each one of these matrices. So now we have 3 different representations for every word of the same embedding. So, and we're going to call them queries, like a query that you make in an SQL, maybe database, a keys as well, and then they have a value, okay? And those words are just here for reference, and maybe they can help you. If they confuse you, don't care too much about them. And so now we basically have a representation of each one of these words 3 different times. That's everything we have. And now we're actually going to build up this one operation, which is called self-attention. So we're going to take as example like this one sentence. So we're going to take like love, so the query of love. And we're going to say, okay, so how do we do attention? So we do the math multiplication between the queries and the key. So what does it mean? It means that we're actually gonna multiply the representation of as a query of love with the keys of each one of the other words, including itself. That's why it's called self-attention. So now what we have is, as this is a dot product, it means that you have a score, that is a number. We're gonna simply scale this score. We're gonna apply some sort of softmax function, which is gonna make sure that the sum of this element is summing to 1. That's it. And then we're gonna, as the graph is showing us, as soon as we did the math multiplication between the query, the key, we scaled it, we applied softmax. We're then gonna remultiply this value, or we're gonna remultiply this number by the vector value, which is the first representation that we learned. And then as we're gonna sum those representations, V1, V2, V3, V4, we're now gonna converge to Z2, which is the representation of the word love, except that now it has in itself the relationship between every other words. And that's basically like the most important aspect. So the idea is that now we have a representation of love that now takes into account every other word. So now like love has a sort of like sense of like, okay, I know that I'm linked to I know that I'm linked to machine learning in some specific way. And we basically use like the key, the queries, and the values to create this relationship that we call attention. And this is the formula of attention. Like this is the operator itself, which was represented here. So what you need to also understand is that what you can do is that, okay, like if now I'm taking a bit of another sentence, but it's okay, the same, like you can also do this as like a matrix multiplication. So it means that like if now I take like 2 words, thinking machines, so this is 2 different rows, then this is the input X, which is embedded. I can multiply this matrix by these 3 different matrices that we've learned, which are the learn matrix about the queries, the keys, and the value. And then we can again make some sort of operation with the queries, and then we'll reach like the value of Z, which we'll have for both words. Okay? So that was probably intense, right? Or maybe not super intuitive, which because it's not intuitive. It's yes, go ahead.
Can I ask a question? So that means that the values of a word relative to any other word are fixed. So no matter where that particular word is in a sentence, like that final representation is always computing its relationship to another word as like the same, right?
Actually, like yes, it is. There is some positional encoding, if you're familiar with those. So it's like, yeah, like at the, yeah, like when you use this in a network, you use some sort of position embedding, but as an operator, you're right. Like your intuition about the operator is right indeed. Like you're able to, no matter where you are, as your, like the key point is that I think that the key operation is really that we're taking one query and we're multiplying it with every potential key, and we're also multiplying with every potential value. And so what this represents is that indeed, like, it doesn't matter where you are, you're going to have relationship with every other words, including yourself. So that's exactly it. So here we're literally fixing the problem about like long-range dependencies that we had in the RNN and that we solved in the LSTM. But this also has like another property that here you see, which is like, okay, but here it seems like we can actually do all of this like in parallel. Because you're like, maybe it's not clear yet, the next visual is going to be, I think, clear, but like, because now you can take 2 different words, and simply by making this matrix multiplication, it seems you can do things in parallel. Like at least like here, we never waited for the previous output because we're multiplying everything by each other's. So, okay, so let's actually try to rebuild this a bit from like memory. So like, let's say I have like 3 different inputs. What is the first step? Like, what are the things that we do already? Like, I forgot, like, if one of you can help me. Actually, I forgot with my slide. I'm sorry, guys.
The matrix multiplication.
Okay, yes, exactly. So one is key, right? So it's like, now I can multiply the input by a matrix that's called, let's say, the key matrix. So I have a representation of it. What were the other ones? I forgot. It was key. The value, yes. And what, there was how many were there? 3, yeah?
Q, I don't have what's there.
Query.
Query, exactly, thanks. exactly. So value, you mentioned that, and then queries. Okay, thanks. Okay, so now we have this free representation for these three different words. Okay, cool. So now, okay, so now can someone explain me what we're doing? I forgot a bit. So we're taking this input.
So we're taking the input,
Yes.
doing a matrix multiplication with the key and the value.
Exactly. So we do.
Which are, they have kind of sort of weights.
So you mean so you mean more the query and the key, right?
Yeah.
Yes, exactly. Yeah, the query and the key, yeah. And so that gives us a score.
Yeah.
Okay.
Then the scores are then multiplied by the.
Okay, so we normalize it and then we multiply it with?
I think it's the value.
Exactly. It's the value, right? We multiply the score with the value. Okay, cool. Okay. And now what was the next step already? Do you remember maybe? One of you? Maybe you again? Okay, no, so the softmax was actually applied here.
Yeah.
So here we had this, and then we scaled and applied softmax, so we went to 0, 0, 5, 0, 5. So the sum is equal to 1, so the softmax was applied. Then we multiply. Exactly, so how do we get Z already? You remember? Like, because now we have like free representation. Like, how do we get Z1? Because this is all for Z1, right?
Yeah.
So how about we just add it together? We don't ask too many questions. Okay, great. Okay, that's cool. Okay, that seems to work actually. Okay, pretty cool. Like, and let's say like I'm gonna do this again for the output number 2. So like, this is just the same graph except that now I'm taking as input 2, same graph. And then I'm gonna do the same again for output 3. And then I also have some sort of numbers. Okay, cool. Okay, great. What is different with this operator? Yes.
Is there an intuitive understanding of what query, value, and key are doing?
This is my most intuitive representation of it. The reality is that like CNN was made, the reason why using convolution is because it's a mathematical property, because we wanted a property called translation invariance. So it was literally like a mathematical proof to get to convolution. So it was, I could explain you the intuition of convolution this way. Here for self-attention, it was more or less discovered by trial and error. And we somehow thought like, okay, you know, like if we like literally, if we have multiple representation of the same words, and if you just multiply them with one another, like actually maybe we could get something out of it. And so it's more or less the understanding that, yeah.
It's a bit the framework of the database. So one of the intuitive way to think about it. Typically, the query would be maybe when you search on Google. This is what you input in Google, what you want to, and the key would be all the keywords that the website expose. And when there is a match between the query and the key, you get good results. Here, typically what's going to happen is maybe the subject is going to query verbs. So it's going to expose this query and searching for verbs in the whole sequence. And then the verbs, well, they're going to expose that they are verbs as a key, as one of the keywords. So there will be a match here. So that means in one part of the network might specialize in finding verbs like this. And then wherever there is a good match, well, there will be a high value in the score in blue. And that means that this match will be highly weighted when you do the weighted average. Because this multiplication by the score plus sum is just weighted average, weighted by the score of this match between query and key. And you can imagine that if you have a very deep network, you might have many of these relationships, typically verbs to adverbs, nouns with whatever.
That's really one of the intuitive ways to get it. For me, it didn't work. So that's why, but if it works for you, that's great. It's a self-attention to actually really understand it. It's going to take multiple times. So it's like you're going to maybe see a visual that's going to work better for you. It's, yeah. You can, again, like, feel free. I think anyway, like there is another visual representation that you're going to see later today with everyone Brown that I think is doing like a great job. One of the key ideas indeed that you mentioned, Alberic, is that like those scores that you have, they're basically attention scores. Maybe that's something I could mention. It's like, it's a bit about telling you, okay, like how much you pay attention to this one word or this other word. And it's a bit what you mentioned by this weighted average. It's like, okay, like as a word love, how much attention should I give to I and how much attention should I give to like machine and learning? And you're like, okay, I should probably give more attention to I because it's probably like the subject, like, and it's gonna try to make up like some relationships like this. And so, yeah, I'm like, basically, the super nice thing that we're seeing about this architecture, I don't know if you can see it much better than in the RNN, is that like everything can be done in parallel. Because like each one of this operation, like input one, I can just, I'm like, as soon as I compute it, like I've got already my weight matrices, so I can just multiply my input, each one of the inputs like I showed before, I can multiply them by by the key matrix, the value matrix, the query matrix. I'm gonna then get those outputs. I can get them for both input 1, 2, and 3 as once. And then I can go through this network in parallel. Like I'm never waiting for a previous output. Like, it's like I'm directly going from input 1 to output 1 and from input 2 to output 2. I'm never expecting something from, I'm never basically using Z1, if that makes any sense. And like, this is just insane. Like what that means that in reality, it's like, it's really like completely game changing for like scaling networks. So the idea is that like, this operator has then been used in an architecture that's called a transformer. You may have heard about it, like it's a transformer is basically an architecture that uses attention, more or less. And this transformer here, that was from the paper, Attention is all you need, is that you basically had, again, your input, je suis étudiant, so I'm a student in French. Then you had some embeddings, then you had some embeddings with some time signal. It's not really important to mention it. And the point is simply like, okay, like we're gonna encode this message like multiple times. So we're gonna apply this attention like stacked on each other. So like we're gonna do this like process to go from X1 to Z1. We're gonna redo it and we're gonna use Z1 as the input, and we're gonna do this like 6 times actually here. And then we're gonna give this information to some sort of decoder that's him like it's actually gonna be able to translate this word. So then for the first token, for the first word, je is going to translate it by doing this encoding, decoding, to then figure out like, okay, the output that I want, I go for the linear, for the softmax, and I have I. And then again, it's then going to take the input, like taking the entire sequence, and then it's making And we don't need to dive in like so much into the architecture of the transformer, because I think it's going to be really confusing for you all. But what you really need to understand is, I think, this image, which is now we have an operation and we have an architecture that is parallelizable. Okay, it's an architecture where you can basically like stack layers on top of each other, because you can stack the self-attentions on top of each other. So you're like, okay, great. You have these long-range dependencies, so you can track a word like at the really beginning of a book and at the end of a book, and you know that it's referring to the same person or character. So you're like, okay, amazing. So we basically have like all the ingredients to solve like text in itself, like any text that you want. Is it putting the next word? Is it translating? And basically, the solution that was found was to simply like increase the numbers of parameters. So basically, simply, instead of having like 3 encoders or 6 decoders, you just like put like 100, 1,000. Like you just scale them up. You just make this system much bigger, and like in a way that is just like, yeah, like pretty crazy. As in like in 2018, we basically went from like a GPT that had like about like 100 million parameters to like now like GPT-4 that has, sorry for the timeline, it's a bit wrong here, but like for GPT-4 that has an estimated parameters of about like more than 1 trillion, like 1.5 trillion. And what's actually great about this is that as you make those models bigger, they keep to run in parallel. So it means that like you can still train them efficiently. And as they're bigger, they can somehow, which is this we didn't really know, it's like they can somehow become much more like helpful. They can understand much better languages. And I think it's something you see already for like the GPTs that you're using. If you have the free version, 3.5 or 4, a model that is like 5 times, 10 times bigger can actually do much, much more reasoning somehow. And so as we have this sort of law that is logarithmic, companies have just been like scaling those models up. And now we're like a threshold at which language is basically solved. Like we're not like at the time when I showed you like this previous network, like we would actually train a network to simply do translation from French to English. You would train a second network to do French to Spanish. Like it was like every network was different. And actually, like if you scale these networks and if you just give them also like a lot of text, they can go from any task to any task. So it's literally like this many to many function. So like as we said like from the beginning, and that can basically solve like any problem that you want, as in the language world, I mean. And so that's it for the natural language processing part. And I like it was 90% of this hour. So like then I can really quickly go through like generative AI techniques and just for like 2 of them. Was this clear already, like this natural language processing part? Any question in the chat? No. Okay. Cool. Yeah, like the message should really be on this slide for this one, which is really now that you have this long range operator that is parallelizable, if you just scale it and if you just make it absolutely enormous, it just works better. And that's a bit the key message. Yes.
As someone that works with images, do I really need to natural language?
Okay, so good question. So I don't know if you've noticed, but like all my slides were called like self-attention is all you need. So it's a reference to a paper that was called Attention is all you need. And then I said like even transformer is all you need. And there's actually quite some beauty in the transformer, which I haven't mentioned because I wanted to really focus on text. But the reality is that like this embeddings that we're doing here, like here it's words, but actually it could actually be anything. So you can actually use this exact architecture, like with a few small changes to process images. And then it's called a visual transformer, which we call like a VIT. And actually like Eve, later today, will introduce you to the VIT. So basically the way that it works is that there's this token relationship. Like maybe you've heard about people when they talk about GPT, they say, you simply predict the next token. So the token is a bit like this embedding that you have that represents not really a full word, but like a bit of a word. And this tokenization can be used also for images. It can be used for many different like input data. It can like now like GPT-4o or like I think the model they're doing right now, like other models, they actually like even the voice signal. So like both understanding the voice. So like what I mean is that like the transformer that they basically use, which is a bit different than this one, but the transformer that they use can take as input images, like text, images, even voice, and it can output any of these other ones. And it's the exact same model. Like it's not 3 models in parallel that run, that one can do images, one can do text, one can do audio. Because there is some sort of like general representation where you can find any token, which is again like really crazy. So that's why it's a bit like transformer is all you need. This operation seems to be great. You have long range dependencies. You can take any sort of input, any sort of output, and it's parallelizable, meaning that you can make like huge models of it. So now quickly about generative AI, and actually like you ask questions about this. So like how would I do like we even asked like would I use like a variational autoencoder to like I'm like to denoise an image, and like which was I think like a great question. So briefly, what the variational autoencoder does is that it's gonna generate new similar data samples by learning an underlying representation, an underlying distribution. It's a bit of a fancy way of saying, okay, so I have X, which is like an image. I'm gonna compress this image as much as possible into like a space that's really small. This is gonna be like in Z. And then in Z, I'm gonna somehow like understand the distribution of this super compressed image, because as you're compressing it, it's much easier to have a look into it. And then you're learning to then get back this X without any sort of loss. So then you're basically learning two different networks. One network that allows you to compress, one network that allows you to decompress this image. And the nice thing is that like if you actually like add a bit of noise to the Z, like when the image is very compressed, you can very easily actually create like new images that are like very similar to the data samples that you had in here in X while you train your network. So that was a bit of an original idea to actually like, first, the idea here was to like, okay, like how can we actually use machine learning to compress information and decompress it? Then we understood that, okay, we could actually like generate data from it. And then there was like a new version of it, which then was called like a GAN, which is like a generative adversarial network. And the reason why we're calling adversarial is because one network is working against another network. So it's a zero-sum game. It's a zero-sum game situation where the discriminator network is simply trying to figure out, okay, so let's maybe from the generator perspective. So we can now reuse this Z representation to generate any sort of new image because we added some noise to it and we can generate a new image. As soon as we have this new image, we can ask to a discriminator, okay, is this an image that was real or is this an image that was created by the generator? And by making all of this information in the same loss function, what you can literally do is this model is like helping each other out to create more realistic data from this distribution Z. And a good example of that is, how do I click on end show to share my screen? Yeah, exactly.
Switch, drag it.
Yeah. Okay. A second. Okay. Sorry. Let's figure out where I am. Yes. And so, for example, GAN were used. So GANs were actually first used for like it was first introduced in the paper by NVIDIA, and then they actually used it to make new faces of people that don't exist. So this is like an actual web page. It's called like thispersondoesnotexist.com, and like every time that you refresh, you're gonna see like someone else that does not exist. And the way that and the way that has been done is that literally we train one network to figure out is this a real image, and the other network was generating the image. Okay. So by these zero-sum game elements. And then lastly, like real quickly, I'm just going to introduce like diffusion, in which the basic idea is, okay, we're going to take an image, we're going to add noise on it, which is exactly the setting that we had at the beginning of this lecture. And then I'm going to ask a network to actually revert this image back to where it was. And the idea of diffusion is that like the better your model is trained, the furthest you can go. So the more you can put noise into your image. And so you simply, at first in network, you do this, then you go here, then you can go a bit further, you can put much more noise, then you learn it to go back to it. And at some point, actually, you can go from like this fully noised image, and you can actually generate a data that you learn it to a distribution from.
Why do you have to regenerate the image at each noise? So why can't you just go to like the extreme case? Is it to like make sure that the loss is at a minimum at each point? Or
So sorry, I didn't hear at the beginning of the.
like regenerate the image each time you're adding more noise.
I'm like, so you can do the same image or like another image. I mean, an image from a distribution. But you mean why are you going further, or why are you?
Why do you have to keep on regenerating the image each time you're adding more noise?
Well, I'm like okay. So the goal of diffusion is actually like, sorry, like maybe that was not very clear. The goal of diffusion is actually to be able to create new images. So that's the goal. And what we basically figured out is that like if you add noise like this and you train a model to go from here to here, you're able to learn the distribution of the images, and therefore you're able to recreate realistic images. And so the more noise you are, the more you're starting from scratch. And so at some point when you go from full noise, you can literally make like any image that you want that has never been made before. Is that clear? Okay.
It's a question about why do you go step by step in removing a bit
Yeah.
of noise every time
Yeah,
and not fully denoising at once?
yeah,
Yeah.
Yeah, exactly. It's too hard otherwise to do.
okay, yeah.
If that's the question, is just like you need to do it gradually, otherwise the task is just too hard. And so like this is just a representation of the image before, where like indeed you've got like this forward pass in which you add this Gaussian noise, and then you learn indeed to denoise step by step, basically. And the goal is just to minimize the loss between the predicted your prediction and the actual distribution. And that's it. So thank you very much for your attention. It was really a pleasure to be here. Yeah, and like I hope this is going to be helpful. And like if you have any questions, feel free to ask. Go ahead.
All of those generative AI techniques, what kind of learning are they? You remember there are four: supervised, self-supervised, unsupervised, and reinforcement learning. You'll be able to say, I think it is self-supervised. Self-supervised, and what people think. Are they all self-supervised? What is supervised learning?
I wasn't seeing anything like it.
Yeah, there is no label there at all. This is why it's so helpful. This is why we can train out so much data.
Yeah.
You can just get images. So the variable that we consider, you take an image, you press it, and just reproduce the same image. So input is the output. The denoising with diffusion, you take an image, just add noise, and then denoise it. Say super easy. GAN, same thing.
Yeah, even actually like attention.
And attention can be used.
And like it's also
The text generation.
yeah, and like text generation, it's also something that's unsupervised. You don't really know this word is good or bad. It's just like okay, it's just if you just take like every word, and like if you just give a book to like a system, it's just gonna figure out like okay, this is how you make sentences, and this is what a correct sentences would be like.
Why is that considered unsupervised? Like
Self-supervised, sorry.
Okay.
So I mean, like the way that I'm thinking about it is, if you're giving it a sentence and you're training on the sentence to predict the next token, then in my view, the actual next token of the text that you're training it on is the like party data that you train on. But that's not considered.
So both supervised and self-supervised learning are type of supervised in the sense that there is a known output. You exactly know what the model should give you, and then you can like correct it. And the only difference in supervised learning is really you have the label, and it's been like a long manual process usually of labeling the outputs and creating this output is a lot of work. Here, it's very trivial to create output because as we see, usually the output is a very simple transformation of the input. Just add noise, for example, or input is the output, something like this.
And so that is what's considered self-supervised.
Exactly.
Yeah.
It's kind of like self-training.
Mm-hmm.
It's like both generating its data and training on it at the same time. Okay. So you can train on so much data.
One way is to say like you have a data set that is made with feedback. Like I don't know if that's if you say like, the word feedback, but it's like I know like this is the correct like this is a classifier for like cat and dog. It's like it's specifically made for cat and dog. So it's like when you have every cat image that you have, it means that you have a human that needs to label it and say this is a cat. And then as you're training this network, every time you have this feedback loop. While here, I can just give it as many images of cats or dogs or whatever. Like I don't need to know what they are. I don't need to label them. I just give it the data and it's going to learn the distribution by itself.
I
Yes?
have a question. So is the reason that like ChatGPT is like bad at math? Is that because I would think intuitively, if you can just give it a bunch of data to like, I don't know, process a bunch of different questions, like math questions, then it will be able to predict what's coming. But is the reason like you would have to train it on basically like every math problem ever possible? Like when you go past like addition, whatever easy operation.
It's a really, really good question. It's a question that I know well because my startup was about education about math. So I actually train models to be better at math. It's a bit of a, there is multiple answers to your question. First is that actually the reason why GPT is like, GPT can solve math exercises, but it's going to make computation mistakes. Meaning two things. First, it's solving the exercises. How is it solving it? Because there is a paper called Textbooks. The textbook is all we need. And basically, ChatGPT has this massive train on many, many textbooks. And that's why like it's really good at basic exercises because they all look so similar. Like as it also knows the solution, it's really easy for it to like guess the methodology of it. And then why is it really bad at like computation? It's actually because of the token representation. So it's like the way that those tokens are built. And I think there's I'm gonna try to find it like right after that, but like there's a really nice representation of it made by Karpati, again, Andre Karpati. Well, like it really shows that like, yeah, you know, it's like basically it's the way that ChatGPT is like seeing a math equation is like it's just like if I would put like 20 random emojis and ask you to somehow make a computation out of it, you know. It's really random. And also you've got some other optimization mistake in the math where it's like it's like sometimes tokens behave a bit in a funny ways because I told you like a token is not really a full word. A token is about like half a word, it's about like 3 characters. And so the things that like when you predict 3 characters from a token representation, sometimes you're gonna have digits that double themselves. Like for example, if you have a word, I don't know, like 325, at some point it could seem like 3000, something like this. In the middle for the 25, it could do 3225. Because I don't know, somehow like when it's merged information, and when you do the math of this, it makes a mistake. So there's many reasons for why it's actually bad at computation, yeah. And why it's also good in some reasoning, even though it, to me, doesn't really fully reason. So it's a bit of a funny thing, but yeah.
Maybe to add at the high level, usually self-supervised learning are pretty good at creating general models. GPT is a general model. ChatGPT is using GPT to create a more specialized model. And a lot of those general models are usually used as a training stage and as a base for many other more specialized models. So ChatGPT is actually used with reinforcement learning on question and answers. So here, where you could also do supervised learning, give a question, you want to have this exact answer. Or you could also even fine-tune ChatGPT on specialized math problems and to get even more performance.
I have a question. So I remember learning like a little bit about auto encoders and like the latent variable. You can't do back propagation, right? Because it's not differentiable. Aren't you like calculating the standard deviation and like the mean?
I think it is.
Well, the version of the encoder,
I think I would have said it is. So you're saying it's not.
you could say this is like supervised learning, right? You have X and you create X and you, well, it's self-supervised, more precisely, but
Yeah.
you just have you could have a mean square error loss where you generated
Yeah.
X prime needs to be exactly X. And I'm not sure about the standard deviation you mentioned. Maybe this is one of the tricks. I never played with those in practice. I don't know if there are special tricks to make them work.
But I would also say that they're differentiable. I would also say that you can come up with some sort of metric to make it differential.
Yeah, I don't know. I don't know. The way I learned it was like to make the Z vector, you take like the mean and standard deviation, then you have to add like a random node or something, but that's like what I did.
Okay, so the random, okay, so so this randomness is that like, if you want to create, okay, so actually it's good that you asked this question, maybe, because it probably means that was not clear. So, so I did this slide a bit fast, so, and like I presented it fast, so, you have some input images, okay, and by pushing the network to compress this information, you're then learning representation here that is like very compressed. So like imagine maybe just as a vector, like almost one-hot encoding or like whatever you want, like imagine as a vector. And then like, okay, you train the network to, from this very dense representation, give you like an image that was the same before. But then, as now you want to reuse this network, this entire network, to actually create new images, and that's what you want to do. What you're going to do is that you're going to add a bit of noise in this Z representation. So this very dense this very dense representation was supposed to be computed from this. But now I'm just going to take like a random, like I'm going to take one very dense representation of X, and then if I just tweak it a little bit by adding some noise to it, then it's never learned this representation, you know. So it's almost as if like it was an image from here before that was actually like compressed. So it's gonna decompress this image that never existed in the first place, and so you're creating an image. Is this clear or?
There is another application of VAEs, is not for generative AI, but more for representation learning. So here the goal is actually just to work with this scene. You want to take this big object X that maybe you manage or like genomic data, very high dimensional data, and you force it with architecture to end at some point in this compressed space C. It will be much more efficient to use. And then maybe there are those kind of tricks where you want Z to be maybe normalized or a special manifold. Some people maybe want Z to be a unit vector always. So you have to do renormalization techniques because you want some properties like Z for your application. And then here maybe you might have some of these technique of instant navigation and doing special things, but then it's really case by case here.
It's also like, as you mentioned, like another thing to add on top of what you said, it's a really nice way of seeing how complicated actually your problem is. It can really force you to, okay, like how dense can the representation of this problem be, or of your distribution be? And actually, like it can be sometimes very helpful in finding some solution.
There's one question on the chat.
Okay, great.
From Abel John. So with diffusion, we are essentially teaching the neural network to keep adding noise so the image is indistinguishable to a random pixelated image and remove the noise. How would that help in creating new images that have never been seen before? So yeah, why adding noise? How is it helpful to create new images?
When I said that the fact.
So, okay, I'm like, that's a very good question. I'm like, if you ask that question, maybe it wasn't clear for many other people, so great. So I think I'm just gonna re-explain then diffusion, but the idea is, again, like I think the ideas of VAE or GANs or diffusion are, I think, in a way they're very similar. It's like you're going to a new representation, and then from this representation you try to learn back what you compressed, or in this case what you noised. So the idea is really like, okay, we've got this input image, and if I add noise to it, and I ask the model to be able to retrieve that image, what it's gonna also do, okay, like it's gonna learn to remove the pixels, but it's also gonna learn actually like the distribution of the data. So it's actually gonna understand that like it's somehow gonna understand like a cat is made like this, and like I don't know, a cat has like these 2 ears, it has 2 eyes, it has this like it has a soft fur. It's gonna learn some features about a cat, and it's gonna learn features about like your entire data distribution, which is gonna be all the images that you're interested in about, and it's gonna learn like all of this simply from denoising the data. So that's why actually like it's a really good example of like self-supervised or like self-supervised learning, because it's like you never gave it the data, you never explained what a cat is, you never, like if we go back to the first slide where I said I know maybe you need to explain exactly what a car is and like it has 4 wheels and whatever. You never need to explain this. It's like the network is going to figure out everything on its own simply by doing this task of denoising the data. A bit like in the end GPT, like it's also learning how to do math. It's also learning how to reason. It's also learning about like concept of philosophy or history. It's even learning like historical facts simply by the task of predicting the next word. So what's interesting to see is that like the cool point of self-supervised learning is that you can use like raw data, and if you find like a task for it that is like unspecified enough, you may have like a really cool conclusion, you may have like a really cool outcome out of it. Which in this sense is like, you know what, like if we just use images where this noise, we actually, if we do it to the extreme, we're actually able to have like a model that produces like completely new images. And it's a bit of a positive outcome that was maybe not superintendent from the original task that it was trained for. I hope that it helps. Yeah, I'm like, you can feel free to answer back in the chat if that helped, or if you have like a follow-up question.
There's another question.
I think part of this that is important to understand, I think I'm remembering correctly, is there's an embedding that's telling the diffusion model what the image is of. And so that's how we can generate new images, is that with that embedding that's including information about what the output should look like.
Okay, because you're completely right, because this is a bit of a simple example of diffusion where like if I just output cats, then it's just going to learn the distribution of cats and I can just output this. If then I give it like an entire data set of like many animals, then you somehow need to give an embedding of like what the image is representing. And by doing that, what you're essentially doing is that then you're able to use use models like DALL-E or like or Midjourney, where you're then able to give an embedding, which is essentially like the word that you put in your query, and then from this embedding, it's able to retrieve that. Like, thanks a lot for adding that on top of it. Yeah. What was the question from the chat?
Maybe one last question, maybe to move to the exercise, but Dalton asked, could I just clarify, with the GAN, the loss function is to try and fool the discriminator.
Yes.
And by so doing, you have a way of assessing if the output of the generator is creating a realistic output.
It is exactly that. You completely understood what the GAN is about. So actually in your loss, you have like exactly try to fool the discriminator and detect generated samples. And so these two networks work against each other. And so it's really like a zero-sum game that allows you to generate realistic new data points. Again, with the same process that we mentioned, you know, it's like we train a network at like, we train a network X, then it's able to have like a representation Z, and then we had some like, and then we're using the generator, we're able to like, yeah, like it's again a bit the same loop that we have with both VAE and GANs. Any other question, or it's okay for everyone?
Let's take it back.
Okay, great.
Sorry, it's a bit tight, quite behind the schedule, so maybe back at 45. And okay, everyone, so day 2 of the exercises. This is gonna be the important ones, and we're really gonna try to do both exercises this time. No optional exercises. And a lot of it's gonna be based on using PyTorch this time, which is really the important framework that we need to master for using deep learning. So there is a tutorial. I highly encourage you to go over this at some point. Maybe today you only check a few pages. I'm gonna show you a bit so you don't lose too much time. What are important things you need to check. And basically exercise 1 is gonna be the same problem as yesterday, but we're gonna solve it with a multi-layer perceptron. So the interesting thing here is that instead of having like a specialized model where we know what is the physics, and we can, so you remember yesterday was this falling object. So we know that gravitation follows this quadratic law. And so we could use this model that was very efficient, just with one parameter. We could have a very good fit. Now we're gonna use a generic model we imagine that we have no idea what's the right model. So this multi-layer perceptron, we'll have to develop this in PyTorch. That's going to be the first part of the exercise, just checking that you can run, take some input. So there's going to be just one number at a time. And then you might expand this vector of 1 to a high dimension, high hidden vector, 10, 20, whatever. And then add as many layers as you want. And at some point, you will need to recompress it down to one number, which is the attitude. So we have many more parameters in this model. But it's still going to be a fairly simple model. And actually, in the tutorial, you will actually get a lot of basically the solution is going to be somewhere in the tutorial. Like the tutorial is also presenting a multi-layer perceptron. So you have to adapt this. And then once you have something that runs, so some kind of black box that takes a number as input and returns another number as output, we'll try to set up a little optimizer and run gradient descent on this. And then, yeah, very similar to yesterday. Check this loss function, how it goes, check the prediction, does it looks good compared with the prediction from yesterday, classic stuff. So to not lose too much time, I'm gonna send this whole exercise on Slack, but you can check, this is the tutorial, we have a few pages. Tensors are like NumPy arrays basically, but more complex. Dataset and data loaders, we won't need it for the first exercises, just a way to put all the data in one big object to iterate over the data. Transform is not super important. Model is going to be important. I'm going to show you this now. Automatic differentiation is basically what we did yesterday, and we're not going to do this so much today. Optimization loop is also going to be very important for today. It's free to do the training loop, and save, load, and use model, less important. It's more like when you want to do deployments. So today, build model and optimization loop is the important one. So this page is showing you a bit. You have to install PyTorch. It's just a pip install. And actually, I might show you just the page of installation, so we don't lose that some time on this. But you see, they have this example. Each model is a class, and it's always the same. You have an init function that takes all of your layers, and a forward function that just uses those layers to really process the input into an output. Always the same like this. And here they actually give you an example of MLP, and you might just adapt this to your problem. So here you have this sequential operation. It's way more numbers. So here you need just one input, and then it's transformed into 512 neurons. So here you have a few layers, as you can see, and the output is outputting 10 values. So you can reuse all of this, definitely. And here's a little example of how you use it. Here, as you can see, so this MLP is a bit weird. It's basically processing an image and flattening it. So we have to be a bit careful with that. That might be not the best example of network. You see, we take an image, 20 by 28. We flatten it to get a long string, long vector. And this is what we give to the MLP, because MLP doesn't take a matrix. It takes usually a vector. So yeah, you have to adapt this a bit. There might be a better example somewhere else. And here they explain everything that they do, the activation function. Yeah, you can read all of this. But really, you have the structure here. You might just find on Google other example of multi-layer perceptron that are a bit better suited. But this is a very good start. So I would try to just develop your own, and then just sending some tensor. You look like you can create a random tensor like this, and just sending it. One important detail you have to keep in mind: we usually use batch tensors. So the input is not just one number; it's going to be all of the inputs at once. So here we have 5 data points, and we can process all of them together at once, the entire data sets. So you would typically have something like 5 and 1 as the dimension, right? And so you could actually have the entire data sets into one tensor of basically those 5 things, and you could process them all at once with your model.
You go back to the website. So you said the parameters there are 5 and 1, 5 being the length of the data set and 1, what is 1?
One is the dimension of your input. In this case, it's just one number, the time. And very often, your input is a bit more complex than one number. It's a whole vector, a whole image, or whatever you want. But the first dimension is always the batch dimension. And most layers are naturally built in a way that each input is going to be processed independently, but in parallel. So your model is going to actually process all of the 5 time steps independently. There won't be any shared information between the 5 time steps, which is very important, right? Just a way to parallel compute. So you can focus on that first, and yeah, let's just focus on that first. Try to have something that runs, that can process a tensor of 5, 1, or actually the real-time steps. And then we'll go over how to set up a little optimization loop once you have this ready. All right, and I'm gonna share this whole thing on Slack. Actually, yeah, maybe also installing PyTorch is going to be important at some point. But it's easy. You could just do pip install torch. Actually,
Who here doesn't know how to use pip to install packages?
If you use Google Colab, it's like automatically by torches on there.
Is it? Is everyone using Colab?
that could be an option if you want to use Colab. Is everyone has some Python environment right now, right? That they used yesterday. Also on Zoom, don't hesitate to tell us. We can take some time with you to set up this. This is an important step. But basically, I mean, it's like any installation of Python. Usually it's very simple. You can just Google it. And in the case of PyTorch, where is it not? Yes, that this page. In their case, there are a few ways to install it, but you can see if we get the stable version, I'm on Mac. Pip is a great way to install it. I recommend it. We use Python, and all of these are for GPU typically. So for now, we're just gonna use our laptop's CPU, and that's it. Pip install torch, and actually they also recommend to install the rest. So it's gonna take maybe 2 minutes of installation max. It's a big package, but it's pretty simple. And then we can run this directly on terminal. So, okay, what is the size, what is the shape of this tensor? We only have one pair of brackets.
5.
It's just 5 actually, yes. Which is not exactly what we want. Usually what we give in the model is at least 2 dimensions. The first dimension being the number of elements in the batch, and the second dimension being the dimensionality of your inputs. Your input is never just one number. Here, each input is one number. It usually is a whole tensor. It can be a vector, a matrix, whatever dimension you want, but it's not just one number. So typically, if you wanted to be more rigorous, this is what you should give to your model. So each of these inputs is independently processed as a vector of size 1. That's what it means. And so you could do it like this. It's a bit slow and stupid, but there are better operations to kind of reshape your tensor. We're gonna do this. What would be the shape of this tensor now? It's not just 5. is 5 elements, and each element has what dimension? Yeah. So it's a 5-1 tensor. We can get the same effects by calling some reshape operation. So one of them, so you might have used those in NumPy. It's exactly the same syntax. H can be reshaped by just specifying a new number of dimension as long as it's the same number of elements. You can redistribute them as you want. So what you could do here is do just something like this. And what you give here is exactly going to be the shape of the final element, which is great because here we want 5-1, and you can just specify that you want 5-1. And here it's going to add this kind of dummy dimension.
Similar to like squeezing and unsmoothing.
I was about to present that. That's also another way. So when you just want to add this kind of dummy dimension, you might just use squeeze and unsqueeze. So squeezing is basically removing all of the kind of useless dimension. For example, maybe here I might have a lot of just dummy dimension. So this means that all of the zeros are encapsulated in other brackets, which is kind of useless. And if I just do t dot, if I, this one actually, if h is this element, and I do then h, but you know what? I'm gonna show you on VS Codes. It's gonna be a bit more clear. Yeah. Yeah, don't look at the solution, but yeah, roughly we start with this one. Okay. So yeah, you could do, let's go here. On this one actually. Set up. So T, first of all, you have to be used to use this syntax. Well, that I can't do them. So T is now a list. It's completely useless in my elements. So as we saw, T equal torch then tensor, and you can actually just do this. So T-dot shape is going to be something you call all the time, especially when developing a model. You have to really make sure that the dimension match between each layer. The black box only works as long as the input works and is transformed into the output. You can put whatever garbage inside as long as the dimension match. So whatever that shape is something that's called all the time. If we do like this, so T-dot reshape, yeah, sometimes, yeah, there are small caveats here and there. You have to be careful. Here in that case, it's indeed better to just do the unsqueeze, but you can see that if I just print T, yeah, that's this thing. And if we want the correct number of dimension, it's going to be this. So 5 elements, and each of them has each of the elements in my batch is actually a vector of size 1. Okay. I can also do like this. And here we do unsqueeze is going to remove all of the kind of useless dimension. So if I just do something like this, we're going to go back to the same. Factory is going to, you have to specify whatever. Interesting. So it's not going to remove by itself all of the dimension. You have to actually specify. Sorry, squeeze.
If we want to unsqueeze, we first need to reshape.
Unsqueeze allows you to add an extra dimension wherever you want. squeeze is removing the dimension wherever you want. So if I reshape to 5,1 and then I squeeze out the second, like dimension 1, so this guy, I'm gonna go back to my original tensor. The squeeze is quite intuitive, and unsqueeze is adding this this element. 3, do that, and T that unsqueeze is gonna just add a dimension 1, and so if we do that, we're gonna go back to the same solution. So I would actually advise to usually do unsqueeze for those simple operation, and this is now. If I print the shape, this is exactly what we want. I'm sorry, I gotta run this first. Yeah, 5 elements, each of them in 1 dimension. Okay, once you're there, you can give this to your model. And
So the initial shape was just 5. And your squeeze there is now 5,1.
yeah, at this point, T is just a vector, a tensor of size of shape 5. And so when I do dot squeeze 1, the dimension 1 does not even exist, but better understand that you want to create a new one. It adds this useless dimension, 5,1. I mean, it's empty dimension.
So squeeze means you are taking out that thing sheet.
Yeah.
But unsqueeze means you are adding that.
Yeah, I can do dot squeeze. And it's going to go back to the same elements. Okay?
I guess my question was, when you first started the example, you were showing at the end of your like H data set that you were H reshaping 5,1, and then you did the T reshape. So if we're doing squeeze, we don't need to like do anything to the H, the end of the H data set, because we're just squeezing 1 dimension.
I'm not sure to follow exactly what you want to do.
I guess I'm like confusing the 2 examples of like how you do.
So the reshape and the squeeze?
Yeah, like the reshape is more.
It can do,
involved in the squeeze.
reshape can do many things. It's a more general purpose function. One way to use it is, for example, images. When you want to transform like 2-dimensional images into just one very long vector. If the image is 28 by 28, you could do this reshape of the image into whatever 28 by 28 is as a number, comma 1, and then you would unroll it to one very long vector. It's a bit overkill for here when we just want to add an empty dimension. So we can use this other method and squeeze and then squeeze.
Okay.
Completely separate method. All right, guys, I'm gonna go through the solutions. So I think this would be best if we kind of maybe just go through like it together, so we can talk about how you guys did it. So in MLP, what is a linear layer? Like what is, MLP is constructed from linear layers, but what is a linear layer? What is it doing?
Sorry.
What is a linear layer doing? So an MLP is a bunch of linear layers with activation functions in between each linear layer. And so let's just start like breaking down the model in our heads. So what does a linear layer do?
I think it does the forward calculations.
Yeah, you're gonna do the forward calculations through the linear layer. But what does the linear layer do to the input data? So let's look at this first one. So we go 1 to hidden size. What does that mean?
But it means that it's taking the input, passing it to the hidden layer, and then it's passing it to the other layer, like
Yeah.
sequential process.
That's a network, but at each step, it's like doing a transformation on the data. And so you want to think about it. I think it's best to think about like, why are we showing you the squeeze, the unsqueeze, the shape, and all these things? Is because you really want to start thinking in like a linear algebra sense about how these networks are formed. And you want to think about the dimension size. And so what this says
is I'm starting at this dimensionality and I'm going to this dimensionality with my data. If you guys can see that on the Zoom, I'm just pointing to the inputs and outputs. And so you'll see this defined as input dimension, output dimension. And so we're transforming the data, instead of it being like 5 by 1 or whatever, it's going to now be 5 by 10. And this is seen, you'll hear this term a lot called embeddings. And what are embeddings? Embeddings are these hidden dimensions in which it's just some numerical value to represent the data. So that's what it's doing. Does that make sense?
Could you repeat that again?
Yeah. Think of it as matrix multiplication. So I don't know how I grabbed this, but the linear layer, we're starting at a single dimension. We're 5 by 1. And we're not going to go to a hidden size. And so all this is doing a matrix multiplication, changing this 1 into whatever our hidden size is, which in this case we're saying is 30. And so now we have a 5 by 30 matrix.
Oh, okay.
And so and this is what an MLP is. And so I think it's rather interesting. If you remove all the activations out of an MLP, what do you have? You have linear regression, which is like your very early stage, like linear transformations or really early stage, like learning, like the first learning algorithm you learn is linear regression. And that's just what this MLP is without activations.
So given size from the field.
Sorry, what was that?
Size, give it a value of state.
Yeah,
So that means the first one also wants.
exactly.
The
So
second one is stations.
hidden size, yeah, exactly. So we're starting off, if we can look at here, with a 5 by 1 matrix, let's just call it like that. And now we're going to a 5 by 30. And so how do you do that? You do it through some weight matrix that transforms the data. That's just like matrix multiplication, linear algebra. And that's what we're doing. But we're also adding then on top of this, we're then doing like a nonlinearity to it, like the ReLU function. So that's the intuition behind linear layers. It's like MLPs. This is like the most simple learning module that you'll come across, especially in deep learning, because all it is just linear layer after linear layer after linear
So
layer.
the second line was the dimension, the hidden size.
Hidden size to hidden size. And so this is like directly like almost, I mean, they're fully connected. So it's not like a one-to-one. That's what the FC stands for. But it's just going from size 30 to size 30. But now you're adding these weights to transform that data to different values. And so each one of these, you just want to think as a matrix of weights that is transforming your data from one dimension to another dimension. And then you're adding in a nonlinearity when you do the self-activation. And what does nonlinearity mean? Like a nonlinearity, some of you are using sigmoids. I like ReLU, Swiglu is like the state of the art right now. These are just all a bunch of fancy names for different types of functions that you're going to map your data to. And so for example, this is ReLU. So this is my standard plot. I'm going to do a leaky ReLU. It's called leaky because it doesn't go to 0. It's more like that. And then you go up. And so if I map my data onto we all see this. You'll see this. If I map my data onto this, what is it doing? It's putting this X onto Y, right? And so if I'm at a negative value, I'm going to 0. If I'm at a positive value, I'm going to here. And this nonlinearity helps them. This is like what actually helps it learn and change the weights and stuff. That's like your basic building blocks of a deep neural network. Do you have anything to add?
Fantastic explanation.
Cool. Does that like make sense? I think this is really important for us to get down. It's like, here's the simplest neural architecture. And if we're still struggling with this, the next task is going to be like rather hard because you have to think in dimensions. So let's like, if we have more questions, if we want to go over this again, I'd be happy to.
Another way maybe just of saying the same thing, but like your explanation is absolutely great, is like we sometimes just call it like a linear projection. So you just do a linear projection from one space to the other. Okay, simple. It's just another word that's being used.
Yeah.
Because maybe one word is meaning something like this.
Yeah. So matrix multiplication, matrix multiplication with just some weird mapping to change the weight values in between. This is what we're doing. And this is the network. But you're like, okay, how do you define these matrices, the matrices that are doing this multiplication? And that's your gradient descent that updates each one of those parameters based on how we saw yesterday. And so these are just matrices full of parameters. And so the size of the matrices, you add them all up, and that's going to be the model size, like the number of parameters that are actually being learned. The for loop, as you guys, as you were saying, Daniel, just goes through the first layer and it gets activated, which I was showing earlier. So matrix multiplication through an activation, so changing it on that nonlinearity graph I was showing you. A lot of you guys are doing sigmoids, which is just like that, and that just goes from, I should do something like that. This is -1, this is 1. It's just an S curve. So you can put them on that. You can, activation functions are a hyperparameter, which means you are going to change them as experimentalist, and some are better than others for whatever task you're doing. And natural language processing, which is what I focus in, we use Swigglue a lot, which seems to just be what works. It's experimentally, like, that's just how they found them. So no real theory behind it. Besides that, it's nonlinear. Good, Casper. You got it? Okay, good. So that's a model. So does your guys' model look something like this?
Mine actually looks like, I don't know, mine looks terrible.
No, not terrible. I mean, look, let's see. Yeah.
The second.
The second activation.
Why do you comment it out?
This shouldn't be commented out. You should go through all of these, but you may not need it, right? Like,
Yeah. No, like it's just because I think like they just do like an NLP of one
of one size.
That's two, yeah.
Yeah, but if you're basing it off of this, you would keep the activation
Yeah.
in between each linear layer. So that's why they kind of go together like this. So every time, besides on the output layer, notice. So this is input layer, hidden layer, output layer. If you're thinking about your MLP.
Actually, like let's ask a question. Like maybe it's like so right now so right now, like knowing that the line is commented, like how many layers would you say that they are getting activated?
Just one.
Like which one then?
The first one.
So like this one.
Yes, they initially speak.
Okay, so for you there is just one layer. Okay, and there is also this one, right? So that's two. Okay, and like let's say like actually like we would uncomment this line. How many would we have? Okay, 1, 2, 3. And let's say like we would like to do. Actually, let's say that we would like to have 4 layers. I'm wondering like which one of these FC would you use? Would you create a 4th one, or would you use one that already exists?
Sorry, can you ask your question again? That's a good question.
So. Thank you. Okay, so let's say like, okay, so right now like we got a network. How many layers do we have? We said 3,
Yeah.
right? Let's say like I would like to have like a 4th layer because I don't know, I'm just like thinking, like maybe we need more depth in this network. Like, would you tell me that I need to like write a new like FC layer, or can I use one that's already there? Or sorry again?
I think you would have to.
Exactly. All right.
So you want to update the parameters for
But
the
what
new
if
layer.
they-
Yeah,
they
that's
give the
nice.
size?
Yeah, makes sense.
Maybe you want to move the value of the hidden size.
So
If you want to use FC2,
Yeah,
it has a hidden size here.
exactly. So the size matches of FC2, but indeed, if you want to update the parameters, you need to create a separate object.
Yeah.
So you do need to create an FC, like I can create an FC4, right? But then like FC, I rename them. But then at least like indeed like the second one, and like the third one, then will also be hidden size to hidden size. Like that's what I mean.
Yeah, dimensionality would be the same.
Yeah.
Good. So this, is there,
Oh, he said it shouldn't be.
I said it can be. It's not like I think like this problem can be solved with just 2 layers. We can also do it with 3, but yeah, I think it was saying. If you want, you can try 10 and you'll see what happens.
so that's the model. And this is an MLP. So anytime and now you can use that term, multi-layer perceptron, and you're gonna sound like mega mind. And people are like, what is that? Yeah. So that's like the first model that was kind of invented in deep learning. This is it. And it comes from linear regression. It comes from statistical learning. Good. All right, step 2. So this is actually like how we train the model. So as you saw, here are our arrays. This is how we define the model. We're increasing the hidden size to 50. And so what is that? Okay, let me ask you guys. So what does that mean that the hidden size is 50? What are my weight matrices gonna look like? What is their shape gonna be? What is their dimension gonna be?
5 by 50.
Exactly, okay. And so it's 5 by 50, and that's what so that's gonna be the number of parameters I'm gonna be updating. I don't think we went, you guys,
So
yeah.
what happens to the first one, the 5 by 30?
Thank you.
Just,
The 5 by 30,
because the first class, this class, yeah.
this FC2, what happens to the FC, or the, yeah, is that your question? Yeah, so this just will get initialized, but nothing will happen to it. It's not used at all. It has no, the only thing that our model actually runs is this forward function. This is just setting up the model, so it's, you can think about it as like, it's going to initialize it and set this up in like the computer memory. And so it's a waste of memory, but you're not gonna actually do anything with it. But yeah, so it's not gonna update at all. But the other two, these will update, FC1 and FC3. Optimizer, did we talk about optimizers? Or is that like too much?
No, actually, yesterday, not, yeah, don't mention it.
What, did you guys learn about optimizers at all?
Not really, no.
Alright, I think we just leave it like this. Atom is an optimizer. This is pretty much the standard. Maybe you'll use another one, but Atom optimizer, you need to put all your parameters in, and learning rate we did talk about. This is your step size. And so we just do a linear rate of whatever 1e to the -3. This is a hyperparameter as well. You'll do this. Yeah, what's up?
Yeah, the learning rate, what about we just write it in the decimal form instead of this notation, maybe 0.001?
Yeah, you could do that as well. Yeah, yeah, it's all the same. So yeah, there's the notations all good. And in fact, like when you get with really large models, this is maybe too much information, but it could be useful if you're going to start working with large models and just start doing the engineering task of things. Learning rate is oftentimes put on a schedule. What that means is it's changed over training time. And you can imagine why this is useful is maybe early in training, you have this vast field of all these pits and valleys that you're thinking about. Let's think about it in like a 3D sense. And I'm looking for the right one that is minimum. I'm going to take large leaps and bounds. And then once I find a well that looks really good, I'm going to start taking small steps to find the bottom. And I don't want to overjump that well. Kind of.
Yeah.
MSE loss, what is mean squared error? This is what we defined yesterday.
Yeah.
Mean squared error is
Between the observed and the predicted.
squared. Good, the absolute value, yeah, good, your main absolute. All right, and that's our criterion. So this is where we're gonna calculate the gradients from. Makes sense how we set up the model, optimizer, just leave that's boilerplate. And then we run 100 epochs. Okay. So how'd you guys do this? I mean, I'm gonna leave it here, but I'd be interested, how'd you guys run 100 epochs of gradient descent? Do you guys wanna walk me through how you would do this? You didn't get there?
I only said, model.train, for epoch and range of epoch, model.train, why what's still messed up though.
It's so messed up. Okay, yeah. So we can walk through it together. Let's do it. All right, so all that epoch. So for epoch and range, 1,000, that for loop, this is just creating a list from 0 to 1,000, and we're just starting at whatever epoch. So this is gonna be a number in that list. Losses, we're just defining a list that we're gonna start appending to. And then we have our tensors, and we talked about unsqueeze. This is just a dimensionality change, so we can input it into our model. So we have this 5 by 1 or 1 by 5, whatever you want to do. X, Y. We know it. Yeah, that's the time, that's the height. We're good on that one. Good. All right, cool. This is optimizer things. This is boilerplate. You're just going to run this every time. Every time your optimizer needs to take a step through every step of the model, or every epoch, so for every X and Y. And sometimes epochs are defined, yeah. What is an epoch? Do we know what an epoch is?
Epoch is just like, the number of steps you, the number of training steps.
To go through all your training data. Yeah, exactly. And so in machine learning, when you're training, you're gonna be going through all the data many times. And epoch is a single time through all your training data, or a subset of whatever subset of training data you set for your training. So that's an epoch. And so we only have like 5 and it gets sent in one batch. Our batch size is like 1. We just send it through, right? Our batch size is 5, but yeah, whatever. Model X that sends it through that forward function. We update it, so that's our output. So this is our y hat, if you want to think about it. This is our estimate. We then calculate the loss. And so we send it through MSE. So we do the H minus Y pad squared, that's the loss, and then L that backward, all that gradient stuff you did yesterday, it's all there. That's amazing. And it updates it automatically. It's fantastic. And so this is kind of abstracted away from you. And this is what Albert was talking about yesterday, is that like all this gradient descent stuff, you don't really need to think about all that much because frameworks like PyTorch have it baked in, but it's good to know like how this is working if you ever want to debug. But that's what that is. So the gradient stuff you did yesterday is L dot backward. You take a step with your optimizer, and for graphing purposes, we're appending the loss item, which is just the loss calculated here. If you do item, that's like a tensor node, that's like a coding thing in order to actually pull out the value from your tensor array.
So,
Yeah.
what are the optimizer state?
The optimizer, this is, you want to explain optimizers?
Yeah, I mean, like,
Like, it's just like, you have optimizer state, what are they?
and then like,
Oh, you need to go. Alright.
he's calling me and like,
Yeah.
is that, there are just like multiple ways that you can explore this space that he mentioned about the values, okay? And it's just like you can see it as like as a function of like how do you go down or how do you go up, like how much sensitive are you, and like it's just like you have different ways of computing it to get to a value. And Adam is just one methodology among like others.
The reason why you have optimizers then, is a lot for compute efficiency. Hence the name optimizers and actually pulling out the most information that you can.
Yeah, I get it, so the optimizer, I'm just asking.
The optimizers have values themselves. They're being tuned over time. The dot step is telling you to update those values.
Okay.
So it's the same as the L dot backward. Very similar. It's just not done through a backward propagation. Does that make sense?
Yeah, I get it.
Good. All right, cool. I see what you're asking. That's a good question. Thanks. Cool. All right. Any questions on the training loop? This is really important. This is like boilerplate stuff. The only other thing I could think you would see in here is maybe another for loop in order to go over batches. Because like I said, like maybe you're going to have more data than your R in your batch size, which is like your input size. And so you're going to have to go through many batches in a single epoch. That's terminology. That's like lingo. Does it make sense what I'm saying? Good. Okay, so batch is a subset of your training data that you go through in epoch. So I'll go through, like, let's say in a genomic sequence thing, if I batch everything, I'll have 2 million steps to go through a genome. And like each batch will have like 1 million nucleotides. And then one epoch would be going through the entire genome. And I do that many times. Think of it like that. All right, and then you print out, bless you. No worries. Every 100, you'll see this is decreasing. That looks really positive, right? We want our loss to go to 0. Plotting, you just do this plot. I mean, that looks great, right? Wow, look at that loss go down. So X is epoch, Y is loss. Good. All right. And then you can plot the predictions. I mean, you compare, but it should work, right? Like this model is way too big. We did this model yesterday on like less parameters, so you don't need whatever 5 by 50 parameters. Let's talk about exercise 2 as well. I think that's what we're going to work on now, and it's a little harder. You have about an hour to work on it, so I'm just going to get you guys started. Do we feel comfortable with this? I should ask first. Are there any questions related to exercise 1 that you still feel unsatisfied?
Can you share the notebook and Slack later?
Yeah. Any other questions? Coding questions, theory questions? I'll wait 5 seconds and then I'll go.
So, sorry, just one question right here.
No need to apologize.
So you could add inside of the training loop, inside the epoch, you can add an extra folder for your batches. Okay,
Yeah, that's exactly where you got it.
okay.
Because epoch is the superset of batches.
Okay, and you only do that if you have like a really big.
Large, yeah, because you usually like, in deep learning, it's all about data, right? How much data you have, so you're gonna have 1 million training samples, but you can't have a model that has 1 million batches. Your model would be huge, right? Let's, for example, here, we do 1 million by 50. Like, I'm not training that on my laptop, right? And so you subset the data in order to have a model size that fits. And this is like a open question too. Does it make sense, the intuition why we batch?
Yes.
But you also want a sufficient batch size in order to get good estimate. So batch size is an important parameter to actually learn. You can think about batch size as like a like in sampling theory, when you're sampling in statistics, you need a sufficient number of n in order to get a good estimate. Batch size is something similar, so you want a larger batch size.
What's a hyperparameter?
It's a hydroparameter, yeah, exactly. Yeah, exactly. So you test that, and it's depending on the amount of data, it's really important, but yeah. Where do I want to go? Is this making sense, Casper? Example 2. Let me find it real quick. Give me 1 second, guys.
Is example 2 the second bubble? Are we supposed to be done with the second bubble?
No, I'm just gonna overview it and help a little bit. Because you have an hour on it, and I think it's quite a bit harder, but I'll give you some like intuition into it. I just have to find it. I am suggesting, currently I already have it open somewhere. All right, let's look at exercise 2. We'll tackle the classic problem of hidden written digit recognition. The inputs of your model are small black and white images of size 28 by 28. The output is a vector of size 10, representing the probability you assign to a model. So we understand what the data looks like? Or, yeah.
Can you go over what you said?
Yeah, I'll repeat it, and I'll just draw it out. I think it's better to see like an image of what this is. So I have a data set of things that look like this. And these are 28 by 28 in size. And what I want to output is I give it this. And what number is that? It's 3. My model, here's my black box. It's not really a box, but we'll call it that. We want it to say that's 3. And we get the number 0. We get the numbers 0 through 9, so we have 10 numbers it can classify. So this is a multi-class classification problem. And is this a supervised, unsupervised, semi-supervised? What type of learning is this?
Supervised.
Good. And so we're trying to classify the numbers as we see them. And so it can only bin them into one of these values. You'll never get a number that's not one of these values. And so the format is this. We have a 28 by 28, and we're going to output a tensor of size 10. And in that tensor, it's going to have a probability, and we're going to choose the one with the highest probability and say that's what the model thinks that number is. We choose the highest probability, and then we run our loss on that. Or you can run your loss across all the probabilities, but it's just going to be 1 minus whatever that highest probability is, because that's what the y value looks like. Good. All right, write a model that takes a batch of images. So again, this is the batch size, this is n here. It's like so tall. 1 by 28 by 28. Because it's a 2D image, it doesn't have a first dimension. And then it's going to send it through a bunch of 2D convolutions. Remember what convolutions are from yesterday? It's just like, again, it's just these transformations, but now you're defining a different matrix size. And this matrix will like go and convolve over the thing. It's actually fun. If you look into it, convolution's like a misnomer. It's not actually what a convolution is, but deep learning people aren't mathematicians, so don't worry about it. And then output's n by 10, so batch size by 10, which is your probability. Lynette? Yeah. Questions on this? Does it make sense what we're supposed to do? Would you guys like more detail or less detail? More detail on what particularly?
Oh, no, just,
More about the model architecture?
Yeah.
Okay, that's good. One thing that I would say would be really good to look into is softmax. So softmax is going to output that probability thing. So that's going to be your output layer as a softmax function. And look into that, read about it, but essentially it's just a probability base. So this is an important term, logits. You're going to hear logits all the time. You've heard logits before, haven't you, Casper? Sarah, have you heard the term logits before? Well, what is a logit?
So when you're talking about the like output of whatever your final values are, at that point, like they usually haven't been turned into whatever your like probability or whatever thing is, but it's like that last possible stage of your values of your neural network before you turn them into like your
tiles made about it.
Exactly. And so in this case, we're outputting logits, but we want a probability that it's going into one of those 10 things. And so you're going to send it through a softmax that's going to turn those logits into probabilities. And you'll see it just does it based on like the weighted sum. So it just divides whatever that number is, the index by the total. That's it. Convolution 2Ds. Let's just look at a 1D convolution really quick. We remember this from yesterday was like a 1D convolution. This is my image. It's 28 by 28. If I have a convolution, well, let's say size, I don't know, 2 by 2. This is my kernel size. What am I doing? I'm just taking this kernel and running it over all these things. So this 2 by 2 window, this 2 by 2 window, this 2 by 2 window, I'm gonna output it into here. And I'm weighting it. So this 2 by 2 window gets weighted into, so let's just call this 2 by 2. And it's just a linear transformation again. You just do the same thing. This times this plus this times this into a single value. And you do that, then take a step and do it. Then you take a step and do it. And then you fill out this. That's all a convolution is. Does it make sense? All right, is that too much explanation? No. Okay, so that's how your network is working. And so what we want to say is we wanted to learn some sort of mapping from this image. Let's say this is my giant bag 3. Go to mapping, and then we finally get this 1 by 10 or n by 10, but let's just say our batch size is 1 for right now. And these are all probabilities. So this is a 3. So the probability that it's a 0 is like 0.0. Let's say our model is really good. That's 1. But it thinks it's a 2 because they kind of look the same. But then it's like, ooh, wow, it's so sure. Let's call these logits, or no, it's just 6, right? And then 0.1 or something, and then that's all 0. That's what we want the output to be. What loss function would you use for this?
Cross central.
Yeah, good. Does it say right there? Oh, it does say right there. What is cross entropy loss?
Cross entropy is a loss that you use when you're dealing with multi-class classification.
Good. Yeah, exactly. Yeah, that's pretty much it. Anytime you're using multi-class classification, you're going to use cross entropy. Okay. Yeah, that's good. Let's just try and we'll see how it goes. In like 20 minutes, I'll go through the model with you all. And then we can write the training loop together if need be. Let's go over COM2D together really quick. Would that help?
What is COM2D?
I was gonna say, I'll take anything you wanna throw in.
Okay, cool. So this is the building block you're gonna use. All right.
So you're gonna pen your.
Let's see, how do I want to define this?
Okay, and then instead of doing this thing, at the very end.
Maybe there's like a way, like, well, like, you can use, at least on Google Chrome, when I go to like print something, it allows me to select like save it in PDF.
Yeah.
So that's what I was thinking of doing. I don't know what the Mac equivalent is.
Here, and yeah, but we want to do every time.
All right.
You have everything.
You guys want to go over what a COM2D is really quick?
Yeah.
All right, cool. There's a really important concept in convolutions, which is known as channels.
Oh, let's just do it one follow.
You can think of these as, hey, Sarah, really quick, we're gonna go over COM2D, if that's good. So what is a channel? You can think of a channel as like another kernel that you're searching over. And so let's just draw with different colors. This is one channel. This is 2 channels. And so it's a second kernel I'm going to apply over this. If that makes sense. Does that make sense?
Why are you going to kernels?
Because, what do you think? Why
Traditional, more accurate?
better representation would be like a good word for it? Because each kernel is its own mapping. So for every channel, so let's just look at this really quick. So you have input channel and output channel. This is the number of kernels I have in my, let's say like I have a stack of kernels. Let's just think of it like that. And I'm going to output that number of channels. And so if I have one image, an image by itself is a single channel. A 2D image by itself is a single channel. And so this is one channel. I'm going to send this through a bunch of different channels. You can think of these also as filters, right? And each filter is going to learn a different representation, its own representation of this image. And so by having multiple filters go over it, they can learn different things. People have looked at this too, and if you analyze filters, they do learn different things about the image. Maybe you'll learn the color content, maybe you'll learn some positional things, something like that. And so having multiple channels just is like having multiple filters to learn the same thing. And so the numbers in the channel are going to be different. The parameters, the number of channels, they all have it, each channel has its own parameter.
So learning different things of same content.
Same content, yeah, exactly. And so it's like a stack of windows I'm applying over my image, each one with its own representation of that image and own understanding of that image. Is that?
So like one could be detecting vertical edges, one could be detecting horizontal edges.
Sure, something like that. Yeah, that's one way to think about it. And so that's a channel. And so you'll see that these models can get pretty tall. And what I mean by that is how many channels, especially if it's really complex things. So that's that channel input, the channel output. And let's just, you don't really need to worry about this. Let's just focus on the input and output. And so right now we have number of batch size by 1, because we only have one channel or image, by 28 and 28. And then our output is going to be n by channel output. This is like the hyperparameter we'll tune, and we can look at the net to see how many channels they use. H out window out. H out window out is going to be defined by your kernel size, which is that like square window I was showing you earlier, which I gave you a 2 by 2. And so you got to do the math like real quickly on what the size will be, but essentially the H out, the height and width will be defined based on your stride, how many steps you take, how many pixels you skip over when every time you move that channel, and the kernel size. So usually kernel size is 3 and stride is 3 to 1. And that means I'm going over every single pixel with a 3 by 3 window. Or well, every 9 pixels spaced over by 1. And down by 1. Good. Yeah, that was really fast. Let's do it again. So right now, what is our input? Our input is n by 1 by 28 by 28. And we're gonna put it through some convolution 2D, in which we're gonna have n c out, so the number of filters we have, those number of channels, h out w out. You don't need to worry about h out w out. What you really are gonna want to worry about is this output channel, this kernel size, and this stride. Kernel size. Let's go back to my image. This is my 3. That 2 is my kernel size. Stride is how many pixels it goes. So when I say stride, it's like number of pixels walked or traversed or whatever. And so if I have a stride equal to 1, let's say this is 1 pixel, this is 2, this is 3, da 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 da. I'm just going to go over 1 with my window 2 by 2. And so this H out, W out gets like figured out by your network. You don't really, that's abstracted away. So you don't need to do that math necessarily. Just make sure it matches what your kernel size is. So that's the combo, that's the basic building block of what we're going to do. And convolutions are like state of the art for image analysis. And even for genomic text, which is interesting. But that's a story for a different day.
Okay, so n is in channels, so is that gonna be the total number of pixels in the image?
No.
No.
So Cn is just the stack of the image. So if you had a 3D image, these are usually defined in like stacks. So like you can think of like MRIs, but we only have a 1D image. So channel n is just a single channel.
Is it n?
Oh, n, sorry, that's the batch size. Yeah, so batch size of 10.
Oh, okay.
I think you said Cn, my bad. Yep.
So, okay. Cn, we're just choosing.
Yeah, you choose your C out, and that's that out channel in the definition, class definition. Any other questions? All right, let's get started, y'all. People on Zoom, we're just gonna walk through the problem. We have about 20 minutes left before the next session. So yeah, so I'm gonna focus mainly on the model component of it. I think that's the more interesting part. The data loading, we can look here. You just use this dataset class, and mnist is the name of the data set. And you can see here, this is what the training loop looks like. You'll notice it's very, very similar to what you saw previously. What are some differences? You'll notice is this for loop, this extra for loop, which is going over the batches, which I described. And if you look at the loss, it's this new criterion we have, which is cross entropy. Where's Daniel? Maybe Daniel. Thanks, Casper. Yeah, but otherwise it's the exact same. So, yeah, once like training loops like this are very boilerplate, so they're very standard, and in the different frameworks, not PyTorch, they're abstracted away from you. So this whole like training loop thing is just handled by someone else. All you have to give it is your loss and then your data. It'll handle it for you. But PyTorch doesn't have that, and we think it's important, like as a pedagogical goal, to understand the training loop. So look over that yourself, but if you understood it from last time, you understand it this time. The only difference, again, being that for loop for batches. The big meat of this is in the model. Let's walk through the model initialization first, so we can get an understanding of it. So we have two convolution functions, and then we have two fully connected layers. And so essentially we're going to think about, like you're going to look at this, is you have two convolutions, then you do something, max pooling, which we'll go over, and then you send it through your MLP, which we now know what an MLP is, which is nice. So if anyone is brave, would they like to explain what this COM2D is doing? Based on the inputs, the output channels, the kernel size, and the stride. Just hold it here. No.
So if the kernel is 5 by 5, then are we losing like 4 off of each like length and width?
So that's a really good question. You can do padding, and I think padding defaults to true, and which will just add 0 pixels in order to make the dimensions work.
Oh, okay, so automatic padding would be then just like them adding however many zeros it takes to preserve the initial string. Okay.
Exactly, so we don't lose any information. And 0 is put on there, no wait. Good, that's a really good question. So what is this first layer doing? Let's start simple. So the in channel is 1, that's just our input. This out channel, 20. So what does that mean? What was that?
Just an output.
The output, yeah, the output channel. So what that means is we have 20 filters. So 20 of these 5 by 5 kernels that are scanning the same image. I think a better way of looking at it is if we look at the Kaggle, which I have here. You can really see it here. This one has 6 channels. So this is our image, and then each one of these is the channel. And you can see here's the information from this channel. This would be your kernel. You put in this filter or this channel here. So this is what's happening. But instead of 20 by 20, we have 20 by 20 by 20, or 20 by whatever you do the math, like having a kernel size of 5 is. I'm not really good at math, so I'm not going to do it. And so now we have the shape, these stacks of filters, essentially 20 high, we got from this channel when we send it in here. So we send it to here, and then we apply our nonlinearity or activation function. Okay, now we're going to, don't worry about max pooling right now. Now we're going to send it through this second convolution. So can someone describe what this is doing?
So similar to before, you're starting with 20 and now it's increasing that to 50.
Mm-hmm. And so you can think about this like when we're signal processing, we're trying to, did you guys ever learn about like Fourier transforms? Or if you have a bunch of normal, like, let's just say let's think about it, like we have a bunch of functions added together and I want to figure out what part of those functions actually have signal or what they look like. You can think about this the same way, that this image can be filtered out to get information into all these channels. And so, yeah, so now we're trying to get more information from this embedding channel out to this 50 channel. That's pretty much all we're doing. Same kernel size, so that 5 by 5 went down. Does that make sense? Yeah. And so now we have this huge stack that's like 50 large. And again, if we look here, I think this follows like a similar logic, and this is normal, right? You want to go from like very short depth to very deep depth is really hard to do, but going from deep to intermediate to larger, oftentimes you'll see neural nets have that kind of shape in which they go skinny, fat, skinny. And so we're pulling out all the information, we're now adding it together and then trying to get it to whatever optimization or whatever our Y is. So you'll see they do the same thing here. Good. Conceptually, are we there? Does this make sense what's happening? I'm filtering an image. That's all you kind of have to think about this. And from a signaling processing standpoint, I think that makes sense, right? Images are going to hold different values. Like if you think of like, Casper had a good point. Let's say this image was RGB, like this was a colored image, then our input channels would be 3, because we have these 3 different color values for the same image. So think of it like that. But now we're going to send it through this MLP, which we are all familiar with an MLP, right? Since from the last one, into our output. Cool. So what is max pooling? It's like a smoothing function a little bit. And so you have all this information, it's dispersed, but sometimes it's hard to pull out, like you'll need a really deep network in order to pull out all that information separate from each other. And so what you'll perform is like a max pooling or an average pooling or whatever, in which you look over this window size and you just take the largest value in that window size and you set all values in that window to that value. So I'll give you like, that's it in English. I'll write it out for you just to make it really clear. So if I have let's say one of my channels looks like this, and then here are my values for it. And then my kernel is 2 by 2, so my max pulls over this 2 by 2 window. And then I'm going to set it to this. All these values are going to go to what? They're going to go to 3, because that's the max. And so that's all this max pull is doing. Good. And this is just a way to smooth things, and it just helps learning. Again, that's empirically found, but has basis in like math. But yeah, it's just making things a little easier. Change the shape so it can fit into this function. So essentially what this is doing is like flattening things. And so that all the information is in like this one big array, and then we send it to our linear layer to shrink the size. So it gets fat, and now it's like super long and skinny, and now it gets smaller.
I'm sorry, for the.
Yeah.
Four-shot max pooling.
Mhm.
Why do we have 2, 2?
That describes the stride size,
Okay.
or the kernel size in the stride. Yeah, so it's kind of the same, like it's like a convolution, but instead of like adding things, it's just maxing all the numbers or choosing the max value and setting them all to that. Okay. And so it's like describing what you're searching over to find that max value. And yeah, and if you want to look at that function, that's a good point. We can look at it here. Yeah, so kernel size, stride. It also reduces dimension because there is a kernel size and a stride. Yeah.
So
Yeah.
2 isn't arbitrary.
No, it's a hyperparameter.
Okay.
Yeah, so this is something you can test. Maybe you want like to do it 210 or something like that. But this is something you'd be testing. How much do we need to smooth it? How many steps do we need to take? Things like that. It's a lot of people do average pooling as well. So you just average all those numbers. And this is, you can think of it almost like the same way in which we had that image that had all that pixel noise and you looked at the neighbors to find what the accurate value is. So it's doing the same thing, but instead it's setting it to max. Great. I think, yeah, convolutions are the best to think, just think in images. Just think like if I'm an MRI machine or I'm some sort of like imaging processing machine, this is all convolutions are. Just how would I process an image? Good. So that's the neural net. And it's really lovely that, you know, PyTorch and other frameworks have these layers. I think they really simplify things. As long as you understand how many filters you want and have a basic intuition on how that structure and those shapes are going to be formed, you'll be good. So like, this is a lot like, in a way, it's a lot like high school chemistry, in which really all you're doing is like dimensionality checking. You're just like sending it through like, oh, I need to go from like what grams to moles to whatever. Kind of the same thing. I want this single channel thing and I need a 10 output. What do I put in between that will pull that information best out? Convolution layers, linear layers. Really simple way of thinking about it. Went over training, the loss will go down. You can do your plotting.
Can this
Yeah.
column not be shared with us?
Yeah, end of day. You have 10 minutes left, so let's continue clearing up any confusion, any general questions about what we learned. Yeah.
Four, 500. It's sort of like.
How do you get that? Right, yeah. Yeah, like I said, yeah, it's just a cube. So these, like, the way these arrays are, they'll just be a cube. If you want to think about it in like a geometric way. And so, by the end of, so every time we have a stride, we're decreasing its size because it's taking like 5 values. So you're going to decrease it by like the dimension by what your kernel size -1, right? Because like it's going over a window of 5 and it's stepping one going over window 5 and taking up those values. So like you're going to decrease by like 4 and by 4 on each side. And so your dimensionality gets decreased to the point in which at the end, so right before we get to this linear layer here, so right, the output of our second convolution, every image or like every channel is 4 by 4. This is 2 by 2, 1, 2, 3. So this is the size of it, right? And you have all these values in it. So this is 4 by 4, and we have 50 of those. So by 50. And so we have this cube that is 4 in width, 4 in height, with 50, or yeah, and then 50 in depth. And so that's where we get this 4 times 4 times 50. So this kernel that's going over and doing all these convolutions, this max pooling that's going over and doing these maxing convolutions is decreasing the width and height of our image, but then we're increasing the channel size. And then these are hyperparameters. This is our hidden dimension. And then that's our output dimension. Is that clear, Sarah? Am I missing anything?
That's good.
That's good. Any other confusions? You look up there, you see something, you're like, what the hell is that? This is the time to ask, because, yeah.
Can you describe the line as, the x view of -1? And then the three shapes.
Yeah, exactly. Yeah, that's a great thing. So -1 is a value that's just, -1 is a placeholder value, and it's telling PyTorch, let me figure out this value, like figure it out for me. And so it's going to do whatever the remaining dimensions are and put it into that spot. This x1, x2, x3 shape is exactly what I was describing earlier. It's this 4 times 4 times 500. So yeah, so x is going to have this, like x here is going to have 4 dimensions by the end, and we need to flatten it. So we need to like, so this is where like the information is. So if we're just thinking of like information processing, like, which is just all these random numbers, I have this 4 by 4 by 50, so this whole stack of information, and I want to flatten it out into this really long array. That's what that's doing. And so taking all that information and now making like every data point in my batch is going to be 4 times 4 times 50 in size, and whatever the batch size is. So this is what it is. So every data point now is this shape. So it started off in which it was n by 1 by 28 by 28. Now we're just n by whatever 4 times 4 times 50 is. 200 times 4,000. Or not, that's
I'll be back.
800. So it's 800 in size. So that's what. That's this really skinny thing. And now we send this through a fully connected layer, a linear layer. And so all that information from all these channels that was taken out and parsed over all these channels are now getting mixed together. And our MLP is going to use all that mixing of those channels in order to come up with a probability for what number this is. So that's where it gets abstract, and that's why it's called a black box, because I don't understand what those embeddings look like. I don't understand, like as human, you can't really understand, but that's the logic behind what's going on. You want to take all these channels, you want it to filter out information at different levels that we're not gonna understand. You wanna flatten it and mix them all together to get a better prediction.
I guess I just didn't know where the -1 came from.
Yeah, the -1 is a placeholder that is like a PyTorch syntax that's really useful. Because then I, as like a bad mental math man, don't have to worry about that stuff. I can just put -1 and let it fill out for me.
So in terms of not understanding like what these like values actually mean when we have these fancies and what is actually learning, if you do get stuck, you have like a CNN that you're trying to use for some like task that you're like really care about, that you're care about that it's like correct. There are sort of interpretability methods that you can use that can go back and say like, what actually am I learning from? And you can like use the like types of inputs and like the weights of your major piece to see like what your models actually learning.
This is a great point. All right, let's give you like let's just do a thought experiment together really quick, like about biology context. So let's say we have a sequence. And I want to try to pull out like the regulatory elements from that sequence. And so my sequence is a bunch of like whatever A, C, yada yada yada. It's just DNA, right? And so we have A, C, T, G. You can make DNA into an image, but this image is going to have 4 channels, and each channel represents as a 1-hot encoding of ACTG. So A would be 1, 0, 0, 0, C would be 0, 1, 0, 0, T would be 0, 0, 1, 0, G would be 0, 0, 0, 1. And so in a lot of genomics deep learning, CNNs are like the state of the art. And so they do this, they take it as an image. And so if I'm a researcher, I'm like, oh, I'm really interested in these regulatory elements. How many channels should I have? What should what should the kernel size be? In which each like pixel, in this case, is a single token or a single like nucleotide. So what is the average size of a regulatory element? 10 base pairs. And so I'll make my kernel 10. Just make it 10. And so that way it's scanning over 10 base pairs at a time to look at something. And so this is where you can put your biological priors into the model. And if you use those techniques that Sarah was talking about, you can actually pull out what it puts weight on, what base pairs it's putting weight on. So yeah, so 10. So now you have a stride of 10 or a kernel size of 10. And then how many like regulatory elements could there be? How many kernels will I need? How many channels will I need? You could do hundreds, you could do 60, right? That's a hyperparameter. I mean, it really depends on what you're looking at. If I'm looking at splicing, like there's like maybe 80 splicing regulatory elements that I want to delineate from. I'll put 80, and that's my channel size. And what you hope is that each channel is learning a different, in this case, 10 nucleotide, putting weights on a different 10 nucleotide sequence. And so you can use those as a way to pull out what information it's learning and what is important for the regulatory model. Is that a good way of explaining that? Yeah. And so that's why this is like exactly, like don't stop thinking about images, but if you are stronger in biology, have a biological sense, this is how you can use it as well. And the way to bake in like biological priors to make this model more interpretable and to look at those, then what you do is look at those actual channels and you can see what they're learning, what it's putting weight on. You look at the parameters that are getting tuned via gradient descent. And then you can learn what base pairs it finds important. That's essentially it. But you could use a Linnet. Like I use ResNets in like splicing genomic regulatory things, and they are state of the art. And so it's really like crazy that like an imaging processing network is now used in, like, why does that work? Well, I think it works as a strong like local positional encoding that's really important to people. Like if you do DNA language models, you use all these fancy transformers, and you look at the weights it's putting, it's really only focusing in a local area. So then like the question for you to start thinking is like, how do I make a model that puts equal weights on vastly different areas, right? I'm only thinking that way. But yeah, that's up.
Okay, so this here is going to be a visual introduction to transformers and specifically GPT. So who all has used ChatGPT at this point? Did you ever wonder why it was called ChatGPT? What that GPT meant?
I don't think that hard.
So now you have some idea what, well, we have on the board generative pre-trained transformers. what do you guys think these words mean? So what does generative mean?
Make something new.
Yeah. And as opposed to doing what?
Like transformation of pre-existing data.
Yeah, or as opposed to like classifying something. So there's like generative models and then there's discriminative models. So discriminative models would be like, here's a picture of a cat or here's a picture of a dog, which is a cat and which is a dog. Where a generative model would be like, make me a new picture of a cat. And so this here is a generative model. And then do people know what it means to be pre-trained?
You're working with a trained model, maybe large model. You're trying to do some kind of transfer learning.
Yeah, so pre-trained, these are models where essentially you train them first on these large data sets. So whether it's all of the sentences on the internet or this giant database of images in Google Images or all of YouTube, and then do further fine-tuning on them. And then the T is for transformer. So let's get this started. And we'll just pause in a little bit with some questions.
The first word is straightforward enough. These are bots that generate new text. Pre-trained refers to how the model went through a process of learning from a massive amount of data, and the prefix insinuates that there's more room to fine-tune it on specific tasks with additional training. But the last word, that's the real key piece. A transformer is a specific kind of neural network, a machine learning model, and it's the core invention underlying the current boom in AI. What I want to do with this video and the following chapters is go through a visually driven explanation for what actually happens inside a transformer. We're going to follow the data that flows through it and go step by step. There are many different kinds of models that you can build using transformers. Some models take in audio and produce a transcript. This sentence comes from a model going the other way around, producing synthetic speech just from text. All those tools that took the world by storm in 2022, like Dolly and Midjourney, that take in a text description and produce an image, are based on transformers. Even if I can't quite get it to understand what a pie creature is supposed to be, I'm still blown away that this kind of thing is even remotely possible. And the original transformer, introduced in 2017 by Google, was invented for the specific use case of translating text from one language into another. But the variant that you and I will focus on, which is the type that underlies tools like ChatGPT, will be a model that's trained to take in a piece of text, maybe even with some surrounding images or sound accompanying it, and produce a prediction for what comes next in the passage. That prediction takes the form of a probability distribution over many different chunks of text that might follow. At first glance, you might think that predicting the next word feels like a very different goal from generating new text. But once you have a prediction model like this, a simple thing you could try to make it generate a longer piece of text is to give it an initial snippet to work with, have it take a random sample from the distribution it just generated, append that sample to the text, and then run the whole process again to make a new prediction based on all the new text, including what it just added. I don't know about you, but it really doesn't feel like this should actually work. In this animation, for example, I'm running GPT-2 on my laptop and having it repeatedly predict and sample the next chunk of text to generate a story based on the seed text. And the story just doesn't actually really make that much sense. But if I swap it out for API calls to GPT-3 instead, which is the same basic model, just much bigger, suddenly, almost magically, we do get a sensible story, one that even seems to infer that a pie creature would live in a land of math and computation. This process here of repeated prediction and sampling is essentially what's happening when you interact with ChatGPT.
So what does it mean that GPT-3 is much bigger than GPT-2? So what does it actually mean in terms of modeling?
It was trained on a larger data set?
Yeah, that's probably true. What else could be bigger?
The number of pictures was trained with.
Yeah, the number of parameters.
Yeah.
Yeah, so like a lot more weights, like bigger sized weights. Anyone else? Yeah, we got more pre-trained data. Someone online. Anyone else? So you can also have like more layers, just like a generally bigger network as well. And so we talked before about scaling laws. And so what kind of like are these implications if GPT-3, like just by being bigger, actually does perform more than GPT-2? Like, will we kind of continue to see this increase with bigger and bigger models, do you think?
Yeah.
Yeah, and so maybe not for all tasks, but yeah, people have just continued to like try the scaling of going more, training on more data, training with bigger parameters, and like as long as there is more data to train on, these have been more and more successful as they just get bigger and bigger. Oops.
Or any of these other large language models, and you see them producing one word at a time. In fact, one feature that I would very much enjoy is the ability to see the underlying distribution for each new word that it chooses. Let's kick things off with a very high-level preview of how data flows through a transformer. We will spend much more time motivating and interpreting and expanding on the details of each step, but in broad strokes, when one of these chatbots generates a given word, here's what's going on under the hood. First, the input is broken up into a bunch of little pieces. These pieces are called tokens, and in the case of text, these tend to be words or little pieces of words or other common character combinations. If images or sound are involved, then tokens could be little patches of that image or little chunks of that sound. Each one of these tokens is then associated with a vector, meaning some list of numbers, which is meant to somehow encode the meaning of that piece. If you think of these vectors as giving coordinates in some very high dimensional space, words with similar meanings tend to land on vectors that are close to each other in that space. This sequence of vectors then passes through an operation that's known as an attention block. And this allows the vectors to talk to each other and pass information back and forth to update their values. For example, the meaning of the word model in the phrase a machine learning model is different from its meaning in the phrase a fashion model. The attention block is what's responsible for figuring out which words in the context are relevant to updating the meanings of which other words, and how exactly those meanings should be updated. And again, whenever I use the word meaning, this is somehow entirely encoded in the entries of those vectors. After that, these vectors pass through a different kind of operation, and depending on the source that you're reading, this will be referred to as a multi-layer perceptron or maybe a feed-forward layer. And here, the vectors don't talk to each other. They all go through the same operation in parallel. And while this block is a little bit harder to interpret, later on we'll talk about how the step is a little bit like asking a long list of questions about each vector, and then updating them based on the answers to those questions. All of the operations in both of these blocks look like a giant pile of matrix multiplications. And our primary job is going to be to understand how to read the underlying matrices. I'm glossing over some details about some normalization steps that happen in between, but this is, after all, a high-level preview. After that, the process essentially repeats. You go back and forth between attention blocks and multi-layer perceptron blocks, until at the very end, the hope is that all of the essential meaning of the passage has somehow been baked into the very last vector in the sequence. We then perform a certain operation on that last vector that produces a probability distribution over all possible tokens, all possible little chunks of text that might come next. And like I said, once you have a tool that predicts what comes next given a snippet of text, you can feed it a little bit of seed text and have it repeatedly play this game of predicting what comes next, sampling from the distribution, appending it, and then repeating over and over. Some of you in the know may remember how long before ChatGPT came into the scene, this is what early demos of GPT-3 looked like. You would have it autocomplete stories and essays based on an initial snippet. To make a tool like this into a chatbot, the easiest starting point is to have a little bit of text that establishes the setting of a user interacting with a helpful AI assistant, what you would call the system prompt. And then you would use the user's initial question or prompt as the first bit of dialogue, and then you have it start predicting what such a helpful AI assistant would say in response. There is more to say about an added step of training that's required to make this work well, but at a high level, this is the general idea. In this chapter, you and I are going to expand on the details of what happens at the very beginning of the network, at the very end of the network, and I also want to spend a lot of time reviewing some important bits of background knowledge, things that would have been second nature to any machine learning engineer by the time transformers came around. If you're comfortable with that background knowledge and a little impatient, you could probably feel free to skip to the next chapter, which is going to focus on the attention blocks, generally considered the heart of the transformer. After that, I want to talk more about these multi-layer perceptron blocks, how training works, and a number of other details that will have been skipped up to that point. For broader context, these videos are additions to a mini-series about deep learning. And it's okay if you haven't watched the previous ones, I think you can do it out of order. But before diving into transformers specifically, I do think it's worth making sure that we're on the same page about the basic premise and structure of deep learning. At the risk of stating the obvious, this is one approach to machine learning, which describes any model where you're using data to somehow determine how a model behaves. What I mean by that is, let's say you want a function that takes in an image and it produces a label describing it, or our example of predicting the next word given a passage of text, or any other task that seems to require some element of intuition and pattern recognition. We almost take this for granted these days, but the idea with machine learning is that rather than trying to explicitly define a procedure for how to do that task in code, which is what people would have done in the earliest days of AI, instead, you set up a very flexible structure with tunable parameters, like a bunch of knobs and dials, and then, somehow, you use many examples of what the output should look like for a given input to tweak and tune the values of those parameters to mimic this behavior. For example, maybe the simplest form of machine learning is linear regression, where your inputs and your outputs are each single numbers, something like the square footage of a house and its price. And what you want is to find a line of best fit through this data, to predict future house prices. That line is described by two continuous parameters, say the slope and the y-intercept, and the goal of linear regression is to determine those parameters to closely match the data. Needless to say, deep learning models get much more complicated. GPT-3, for example, has not 2, but 175 billion parameters. But here's the thing, it's not a given that you can create some giant model with a huge number of parameters without it either grossly overfitting the training data or being completely intractable to train. Deep learning describes a class of models that in the last couple of decades have proven to...
Okay, so I just want to pause there. How are people doing so far? Is it good?
Yeah.
Okay, and then he mentioned overfitting. So what does it actually mean to overfit your training data?
Overfitting, I think basically means overfitting basically, I would say it's when your model makes predictions that are above based on usually from the fine tuning. I don't know.
Yeah, so the predictions won't be correct when you're comes time to actually use them for your use case. That's definitely true. Does anyone else want to chime in?
Is it like when your model, from the training data, it memorizes the features of the training data instead of learning from it? So it develops a lot of biases, which can really when you now try using new inputs that's never seen before, like a benchmark training data set, it probably can't make any predictions because it's basically memorized instead of learned.
Yeah, so the word overfit means you're literally fit very, very well to that training data, but so well that you might not actually generalize to newer data. So what are some things you can try to kind of prevent overfitting? Yes.
You could purposely set aside a portion of your training data to use, after you kind of officially trained the model the first time. That way you can kind of know initially if you overfit or not, and if you have you can use those extra, maybe say usually it's 80-20%, 20% of training data to fix that.
Yeah, how would you be able to tell with that extra set whether you overfit or not?
If you did overfit, then the first 80% would have a really good score, and the second 20% would have a really bad score.
Yeah, definitely. Any other thoughts about how to kind of prevent overfitting?
Stringent parameters.
Yeah, so if you have a giant 175 billion parameter model, but you only have a tiny bit of input, what's it actually going to be learning? You're probably going to essentially be memorizing the data that you have because there isn't enough data there to actually be learning something meaningful with all those features. And so a good thing to look at is what's the amount of features that you're actually training and how much data are you actually using to actually train. Yes.
I don't remember if this was today or yesterday, but someone talked about randomly establishing some of the layers to go to 0 or something so that you wouldn't
Yeah, so yeah, you can do, it's called dropout. So for instance, like, if you have like your neural network, you can drop out some of your neurons. That can help prevent memorization because it can make sure that certain neurons, like, that's not the only neuron responsible for doing one thing, like another neuron also has to be responsible for that information in some way, because if one neuron is dropped out, set to 0, your model still needs to be able to learn something. And so this sort of kind of like backup plans and the neural network training is also like a good strategy to help prevent overfitting as well.
What's the difference between having a dropout neuron and then just not having that neuron exist at all?
Dropout neuron means that sometimes like you can use that neuron, like it does exist. Like it's not that the same neuron's always dropped out.
Okay.
It's that you're like kind of randomly each time you're training, choosing different subsets of neurons to drop out.
So your output can change depending on which one dropped out?
During like inference, like when you're actually like using that model, like you would typically run it, I think, with like all of the neurons there. But during training, yeah, sometimes like during one round of training when certain neurons are dropped out versus a different round of training when other neurons are dropped out, you would get slightly different outputs. Though at that point you're still like updating the weights anyway. But the goal there is that your outputted prediction should not be wholly dependent on like one particular neuron, and it will be kind of spread out across a bunch of different neurons.
Might actually change the optimizer, the learning rates, that kind of so work.
Yeah, so yeah, the things like your learning rate or your optimizer are like also things that you could change. For instance, if you're like hopping around your data too much, like because your learning rate is so big, like you might that might allow you to explore more of the space, but not really ever get to like a local optimum. Or if your learning rate is like really, really small, it's possible you're just gonna like maximize what you're doing in like the local area, but you're going to be missing some like other performance there. And it's, I guess, perhaps possible to like, if you are like really just maximizing that like local performance, that you could have end up overfitting to your training data. Yes.
When dealing with so many parameters, do you have to worry about having like almost like identical like weights and biases for maybe like certain neurons or something just by chance? Or?
Yeah, so you definitely could. The like what's going on here is we'll be talking about attention and essentially like multi-headed attention, and the fact that you are doing the same operations like over, but like with a different like weight matrix.
Mm-hmm.
And the hope is that each of the weight matrices is going to learn something different.
Right.
But yeah, you could worry that like if you haven't trained your model right, that yeah, you essentially could have copying of this weight matrix looks like another weight matrix. But I think in the like ideal scenario, they start with different random initializations.
Oh, right, I forgot about that initialization. That's probably gonna deal with.
And so that's one way to like help ensure that yeah, the two ones aren't just learning the same thing. And then I guess like it's just the fact that if you are starting at two different starting points, and it ultimately would be better for your model to have the advantage of learning multiple different things as opposed to all learning the same thing. That your model wouldn't just all converge and learning the same thing with every weight matrix.
Right, got you, thank you.
Great. Okay, we'll keep going a little bit longer.
To scale remarkably well. What unifies them is that they all use the same training algorithm. It's called backpropagation. We talked about it in previous chapters. And the context that I want you to have as we go in is that in order for this training algorithm to work well at scale, models have to follow a certain specific format. And to know this format going in, it helps to explain many of the choices for how a transformer processes language, which otherwise run the risk of feeling kind of arbitrary. First, whatever kind of model you're making, the input has to be formatted as an array of real numbers. This could simply mean a list of numbers. It could be a two-dimensional array, or very often you deal with higher dimensional arrays, where the general term used is tensor. You often think of that input data as being progressively transformed into many distinct layers, where again, each layer is always structured as some kind of array of real numbers, until you get to a final layer, which you consider the output. For example, the final layer in our text processing model is a list of numbers representing the probability distribution for all possible next tokens. In deep learning, these model parameters are almost always referred to as weights, And this is because a key feature of these models is that the only way these parameters interact with the data being processed is through weighted sums. You also sprinkle some nonlinear functions throughout, but they won't depend on parameters. Typically, though.
So let's just take a moment and talk about those nonlinear functions. I know you've heard about them before. So what are some examples of nonlinear functions? Yes. So what does that look like?
It kind of, zeroes out the negative number.
Yeah. So, and so that will kind of keep it so that, it's non-linear in the sense that it is still linear in the positive side, but on the negative side, because you're getting rid of those negative numbers, you're like forcing things to still move around. What other nonlinear activation functions are
You
there?
have 10.
What does that kind of look like?
I can't recall.
Anyone? What range of numbers does it squash your?
Between 1 and -1.
Yes. And so can you think of like a scenario where that might be useful?
You can use it in case of multi-classification.
Yeah, you could. Why do you think that might be helpful?
That would be helpful.
Yeah, so especially if you have numbers like all over the place at different scales, it can be useful to kind of standardize it into like a -1 to 1 scale to make it so that things like are a little bit more comparable when you're like bringing things together, so you don't have like one number that's kind of just dominating. Anyone else? What's another super common nonlinear function? Sigmoid, yeah. And when can that be super useful?
You can use it in I think you can use sigmoid in one class where you have to decide when it's positive or negative.
Yeah.
And it's between 0.5, where anything less than 0.5 is negative, greater than that is positive.
Yeah, and what's the overall range of the output number?
1.
Between 1 and what?
It's I think it's between sigmoid. It has this, I think 0.5 is like benchmark.
Yeah.
Less than 0.5 and greater than 1.
And yeah, what's the like minimum value that a sigmoid could output?
It could have put a negative -1.
So 10H was -1 to 1.
Yeah.
Sigmoid is 0 to 1.
0 to 1.
And which is why, yeah, it makes sense. If you're trying to classify something, you kind of interpret that as like a probability.
Yeah.
And halfway through the 0 to 0.5 is one class, and the 0.5 to 1 is another class. And so that can be super useful when you do want to be interpreting things as these probabilities. And so yeah, these nonlinear activation functions are useful not just in like multi-layer perceptrons, but get used throughout all different kinds of neural networks. So they also even get used here.
Instead of seeing the weighted sums all naked and written out explicitly like this, you'll instead find them packaged together as various components in a matrix vector product. It amounts to saying the same thing. If you think back to how matrix vector multiplication works, each component in the output looks like a weighted sum. It's just often conceptually cleaner for you and me to think about matrices that are filled with tunable parameters that transform vectors that are drawn from the data being processed. For example, those 175 billion weights in GPT-3 are organized into just under 28,000 distinct matrices. Those matrices in turn fall into 8 different categories, and what you and I are going to do is step through each one of those categories to understand what that type does. As we go through, I think it's kind of fun to reference the specific numbers from GPT-3 to count up exactly where those 175 billion come from. Even if nowadays there are bigger and better models, this one has a certain charm as the first large language model to really capture the world's attention outside of ML communities. Also, practically speaking, companies tend to keep much tighter lips around the specific numbers for more modern networks. I just want to set the scene going in, that as you peek under the hood to see what happens inside a tool like ChatGPT, almost all of the actual computation looks like matrix vector multiplication. There's a little bit of a risk getting lost in the sea of billions of numbers, but you should draw a very sharp distinction in your mind between the weights of the model, which I'll always color in blue or red, and the data being processed. which I'll always color in gray. The weights are the actual brains. They are the things learned during training, and they determine how it behaves. The data being processed simply encodes whatever specific input is fed into the model for a given run, like an example snippet of text. With all of that as foundation, let's dig into the first step of this text processing example, which is to break up the input into little chunks and turn those chunks into vectors. I mentioned how those chunks are called tokens, which might be pieces of words or punctuation, but every now and then in this chapter, and especially in the next one, I'd like to just pretend that it's broken more cleanly into words. Because we humans think in words, this will just make it much easier to reference little examples and clarify each step. The model has a predefined vocabulary, some list of all possible words, say 50,000 of them. And the first matrix that we'll encounter, known as the embedding matrix, has a single column for each one of these words.
So in the natural language processing case, where you're dealing with large amounts of text, it kind of makes sense that the individual building blocks would be the words of that text. But I think a lot of you guys are interested in biology. So and we're talking about modeling biology, what could the tokens be? And any possible use case when you're thinking about images, when you're thinking about sequences, what are some examples of how you could use tokens for biology? Yes.
Each one could be an amino acid, say each like in a protein sequence.
Yes. We talked about one-hot encoding for RNA. How do you think that would work for proteins?
I guess it depends on exactly this, like if you really care that much about like the tRNA come from, but if not, just one for each amino acid as the column. So instead of having 4, you have like, what is it, 20?
Yeah, so it would be like your encoding matrix would be the length of your protein times 20, and it would be a 1 where it is for that amino acid that corresponds to that row, and a 0 for all of the other rows for that amino acid. There are also other ways to embed amino acids where if you don't just want the 0, 1, you could say that I know positively charged amino acids are more likely to behave more similar to one another. So why don't I put them in an embedding space? And we'll talk here more what embedding spaces look like for words. You could similarly put amino acids in an embedding space where amino acids that have similar properties in terms of like charge or hydrophobicity actually are more similar to each other in their representation. Yes.
So in that case, would the sort of like that table of like physical properties of amino acids, would that be input or would that be like pre-built already into the model somewhere?
Either way, you could like you could build an embedding model to essentially learn a feature vector that best puts amino acids that are similar to one another or as close to another. You can also just decide that my first feature is going to be charge, and my second feature is going to be hydrophobicity, and my third feature is going to be this. And then that's how I make like an embedding matrix of size 10 or 20 or however many features that you've pre-decided on. So you could also predefine some sort of embedding as well that makes things similar to one another. So the thing about the 0, 1 thing is because everything is just 1 in one place and 0 in the rest of the places, all of those are equally distant from all another. There's no notion of similarity there.
Gotcha.
And so with words, would not have made sense if you have 50K words in the English language trying to be tokenized. A one-hot encoding of words would be so sparse. You would be the length of your sentence maybe times 50,000 and only one in each of those. And you would also be saying that all of those words are like equally likely. And when you're like learning weights and things, any weight that you learned would be only relevant to like each individual word, because there would be no like way of translating it to being also relevant for the things that are similar to those words, because all of the words are equally apart. So that's why we do like these embedding matrices.
Gotcha, makes a lot of sense.
Back to other biology examples besides amino acids and RNA. Can anyone think of other kind of ways to tokenize biology?
You could I don't know, but I'm going to, because I do some cheminformatics.
Mm-hmm.
That would be to, just like you said, that would be to you could encode different certain substructures, specific substructures, the absence or presence. And that could be some kind of embedding too.
Yeah, exactly. So I forget what it's called for chemistry, but there is that exact kind of embedding for chemistry that is a do you or do you not have like certain types of bonds and things like that. There's also Smiles codes embedding for chemistry, which is like a way to write out the chemical formula in a constant way that like doesn't really change depending on like it's like just like a common nomenclature of like when you write it out in this way, it means these kinds of bonds are there, and it's like a way to kind of standardize that. So that's like also another way to kind of be encoding like chemical structures.
Yeah.
Cool. And there's also like biology still has images, so it's very often for people to want to do like segmentation tasks on images. Like for instance, here's an image where is a cell, where are like the outlines of certain things, and so it's still very common to have kind of images as well. And images can also be inputs into certain kinds of transformers.
These columns are what determines what vector each word turns into in that first step. We label it WE, and like all the matrices we see, its values begin random, but they're going to be learned based on data. Turning words into vectors was common practice in machine learning long before transformers, but it's a little weird if you've never seen it before, and it sets the foundation for everything that follows, so let's take a moment to get familiar with it. We often call this embedding a word, which invites you to think of these vectors very geometrically, as points in some high-dimensional space. Visualizing a list of 3 numbers as coordinates for points in 3D space would be no problem, but word embeddings tend to be much, much higher dimensional. In GPT-3, they have 12,288 dimensions, and as you'll see, it matters to work in a space that has a lot of distinct directions. In the same way that you could take a 2-dimensional slice through a 3D space and project all the points onto that slice, for the sake of animating word embeddings that a simple model is giving me, I'm going to do an analogous thing by choosing a 3-dimensional slice through this very high-dimensional space and projecting the word vectors down onto that and displaying the results. The big idea here is that as a model tweaks and tunes its weights to determine how exactly words get embedded as vectors during training, it tends to settle on a set of embeddings where directions in the space have a kind of semantic meaning. For the simple word-to-vector model I'm running here, if I run a search for all the words whose embeddings are closest to that of tower, you'll notice how they all seem to give very similar tower-ish vibes. And if you want to pull up some Python and play along at home, this is the specific model that I'm using to make the animations. It's not a transformer, but it's enough to illustrate the idea that directions in the space can carry semantic meaning. A very classic example of this is how if you take the difference between the vectors for woman and man, something you would visualize as a little vector in the space connecting the tip of one to the tip of the other, it's very similar to the difference between king and queen. So let's say you didn't know the word for a female monarch, you could find it by taking king, adding this woman minus man direction, and searching for the embeddings closest to that point.
Does this point here make sense of why the direction distance between man and woman could perhaps be similar to the direction distance between king and queen? Yes.
At the beginning, they said that the model isn't mapped on actual words. Is that true? Or maybe I just got confused. Like if he was like dividing the sentence.
So yeah, so in terms of like how the tokens work,
Yes.
it makes the most sense to think of tokens as individual words, but sometimes it can be done differently in the sense that like fish versus like fishing, like is fish a word or is fishing a word, or like do those each get their own tokens, or are there some like modifications? Like there's like additional complexity to exactly what you might want to consider an individual token.
Okay.
And so, but for the most part, you can think of like one token as like one word.
Oh, okay. I thought he was saying that like no tokens were words.
Yeah.
Okay.
Like,
Okay.
I think on average, a token is like 3/4 of a word. So like a longer word might be 3 tokens, but I think for words like these, they might actually all be 1 token.
Yeah, that would make sense to me. Can anyone think of like, especially if you're training this off of the context in which you see these words. Why might man minus woman not be strictly equal to king minus queen? What are some explanations for any differences that you would see, besides the fact that these embeddings just like aren't going to be perfect?
Like vernacular, like maybe queen isn't being used as to describe like a monarch, but it's like a slang term for something, and so then it kind of like loses the how you can extrapolate it up to king.
Yeah, exactly. So queen is going to be seen in lots of different contexts, some of which are not specifically just a female monarch. And so it's going to have to be similar to not only like this definition of monarch, but also whatever other like kind of uses of queen it would need to be. Exactly.
At least, kind of. Despite this being a classic example for the model I'm playing with, the true embedding of queen is actually a little farther off than this would suggest, presumably because the way the queen is used in training data is not merely a feminine version of king. When I played around, family relations seem to illustrate the idea much better. The point is, it looks like during training, the model found it advantageous to choose embeddings such that one direction in this space encodes gender information.
Memories were meant to be saved. Saved for their college memories, but...
Another example is that if you take the embedding of Italy and you subtract the embedding of Germany, and then you add that to the embedding of Hitler, you get something very close to the embedding of Mussolini. It's as if the model learned to associate some directions with Italianness and others with World War II Axis leaders. Maybe my favorite example in this vein is how in some models, if you take the difference between Germany and Japan and you add it to sushi, you end up very close to bratwurst. Also, in playing this game of finding nearest neighbors, I was very pleased to see how close cat was to both beast and monster. One bit of mathematical intuition that's helpful to have in mind, especially for the next chapter, is how the dot product of two vectors can be thought of as a way to measure how well they align. Computationally, dot products involve multiplying all the corresponding components and then adding the result, which is good since so much of our computation has to look like weighted sums. Geometrically, the dot product is positive when vectors point in similar directions. It's 0 if they're perpendicular, and it's negative whenever they point in opposite directions. For example,
so what's the dot product if you're thinking of a one hot encoding between two like amino acids that like one's arginine and one's tryptophan, and they're being represented with one hot encoding? What would the dot product be? Yes.
0.
Yeah. So, and that's true for any pair of amino acids because the only places where these vectors are non-zero to begin with is where one of them is 1, and another one will have to be 0 at that same position. And so you're doing 0 times 0 plus 0 times 0 plus 1 times 0 plus 0 times 1. And so that's why you can say they're all perpendicular to each other, and why that might not make the most sense. Also on the amino acid side, can anyone think like some reasons why, like, we always say protein language modeling can be similar to natural language processing, but in what ways are amino acids kind of different than words?
They'll often be related to ones like a lot farther down the sequence than in actual like sentences. Like it's fairly common to have like kind of like a nucleotide, like a nucleotide bind to like another one that's like dozens of bases away from it. Or in sentence, like in, I don't know, stories or sentences, it's a lot harder to find that phenomenon.
Yeah, you definitely still want that like attention between things or far away in the natural language process, but it's less direct. You can like use context in another sentence to help you understand like what he or like something else would mean in like your current sentence. But yeah, you don't so much have those direct contacts that you do have in proteins, where one word is like kind of could be entirely dependent on another word that's a completely far away. What are some other reasons why kind of words and amino acids might be different? Yes.
Maybe like if an amino acid has evolved to have a certain function that is not in the training set database, it's similar to what happens with words, maybe where like the model can't predict that an amino acid will like show up in a structure having that particular function.
Yeah, so you can definitely have mutations that occur that like essentially would never have been trained on because it's never been seen in that context before. I
Right.
would argue with sentences, there are so many sentences that have never been seen before where it's, you also have the similar set of like, you can very easily make a unique sentence. I think it's like once you make like a 10-word sentence, you're like very unlikely to have written a sentence that anyone has ever written before in their life.
That's fair. I guess I was talking more about, for example, like if someone came up with a new slang word, like
Yeah.
a language model that has not been trained on that, like, is that a good parallel to an amino acid?
So I guess the slang word would be like a whole new token. And so like it would not know what to do with that token because it's never even seen that token before. The amino acid would, you would have to be like a non-canonical amino acid
Okay, that makes
as
sense.
opposed to like just a mutation where the mutation's never been seen in that context before, but a word may never been seen in a context before. Though I suppose maybe it's slang where it's like an existing word, but it's never before been used to mean.
Yeah, exactly.
Okay, that's what you were meaning. Okay, yeah, so that is also true. Definitely. Like if you met, like if people are only now just starting to use one current word to like mean something completely different. And that's done all the time in biology where like mutations are happening that like you would never have seen it in that context before as well. I think one of the biggest differences are just like these sizes. So 50,000 words versus 20 amino acids. What do you think are kind of like the implications of those different sizes?
Sorry.
What do you think is the implication of having like 50,000 unique words versus only like 4 unique nucleotides? There are only 20 unique amino acids. So a word is like meaningful by itself. Like it has some meaning. You might not know exactly which meaning of queen you're referring to, but at least you have like some idea of like what it's talking about. If I just told you arginine, does that have any meaning whatsoever?
Yeah, no, I can't say anything about that protein.
Yeah. So that's like also really difficult that like is a word more equivalent to like a single amino acid, or maybe it's more equivalent to like a chimer, like a set of amino acids. Like what actually is the word equivalent in biology? Like we're not sure. And I think that's why like direct like metaphors of amino acids are words, and therefore we can just straight up use a transformer that's done great on natural language and use it for biology. You have to like think about in what ways like are these two actually very different things. Yes.
If there are less tokens, is there a bigger risk of overfitting?
That's a good question. Certainly there's also a lot less data too. So I mean, we're getting to the point where we do have like a lot of protein sequences, so there's a lot less protein structures. But yeah, just like depending on like how many things you're training on, you're in a much smaller space than this like natural language space, I would say for sure. And so, yeah, I think that's definitely a big issue all of the time is overfitting when you're talking about biology and memorization. So it's like, especially in the biology case, people are going to ask you, what's your train split? What's your test split? Like, how are you dividing like what you're training on and what you're validating on is very important. And there's part of the thing is like, do you need to do like date splits, for instance, demonstrate that your model trained up into like a specific date could still generalize to like new structures or whatever, like new structures in the PDB that came afterwards. Like, would it actually have been useful to for those new structures that it hasn't been trained on? But it's also that certain like sequences of proteins could be like 20 mutations away from one another and still behave very much the same. And so you don't want one protein that's in your training set and then another one that's essentially the same protein with a couple of mutations in your test set. That's not actually shown that you can generalize to a new setting. And so like especially in this biology space, like what your train test split is super important. And I think there's a lot of like sorts of rules about how to properly do it. And I think it's much less thought about in like the natural language space than it is in the biology space where it's really important.
Let's say you were playing with this model and you hypothesize that the embedding of cats minus cat might represent a sort of plurality direction in this space. To test this, I'm going to take this vector and compute its dot product against the embeddings of certain singular nouns and compare it to the dot products with the corresponding plural nouns. If you play around with this, you'll notice that the plural ones do indeed seem to consistently give higher values than the singular ones, indicating that they align more with this direction. It's also fun how if you take this dot product with the embeddings of the words 1, 2, 3, and so on, they give increasing values. So it's as if we can quantitatively measure how plural the model finds a given word. Again, the specifics for how words get embedded is learned using data. This embedding matrix, whose columns tell us what happens to each word, is the first pile of weights in our model. And using the GPT-3 numbers, the vocabulary size specifically is 50,257. And again, technically this consists not of words per se, but of tokens. And the embedding dimension is 12,288. Multiplying those tells us this consists of about 617 million weights. Let's go ahead and add this to a running tally, remembering that by the end, we should count up to 175 billion. In the case of transformers, you really want to think of the vectors in this embedding space as not merely representing individual words. For one thing, they also encode information about the position of that word, which we'll talk about later. But more importantly, you should think of them as having the capacity to soak in context. A vector that started its life as the embedding of the word king, for example, might progressively get tugged and pulled by various blocks in this network, so that by the end, it points in a much more specific and nuanced direction that somehow encodes that it was a king who lived in Scotland, and who had achieved his post after murdering the previous king, and who's being described in Shakespearean language. Think about your own understanding of a given word. The meaning of that word is clearly informed by the surroundings, and sometimes this includes context from a long distance away. So in putting together a model that has the ability to predict what word comes next, the goal is to somehow empower it to incorporate context efficiently. To be clear, in that very first step, when you create the array of vectors based on the input text, each one of those is simply plucked out of the embedding matrix. So initially, each one can only encode the meaning of a single word without any input from its surroundings. But you should think of the primary goal of this network that it flows through as being to enable each one of those vectors to soak up a meaning that's much more rich and specific than what mere individual words could represent. The network can only process a fixed number of vectors at a time, known as its context size. For GPT-3, it was trained with a context size of 2048, so the data flowing through the network always looks like this array of 2048 columns, each of which has 12,000 dimensions. This context size limits how much text the transformer can incorporate when it's making a prediction of the next word. This is why long conversations with certain chatbots, like the early versions of ChatGPT, often gave the feeling of the bot kind of losing the thread of conversation as you continued too long. We'll go into the details of attention in due time, but skipping ahead, I want to talk for a minute about what happens at the very end. Remember, the desired output is a probability distribution over all tokens that might come next. For example, if the very last word is professor, and the context includes words like Harry Potter, and immediately preceding, we see least favorite teacher, and also if you give me some leeway by letting me pretend that tokens simply look like full words, then a well-trained network that had built up knowledge of Harry Potter would presumably assign a high number to the word Snape. This involves two different steps. The first one is to use another matrix that maps the very last vector in that context to a list of 50,000 values, one for each token in the vocabulary. Then there's a function that normalizes this into a probability distribution. It's called softmax, and we'll talk more about it in just a second. But before that, it might seem a little bit weird to only use this last embedding to make a prediction, when after all, in that last step, there are thousands of other vectors in the layer just sitting there with their own context-rich meanings. This has to do with the fact that in the training process, it turns out to be much more efficient if you use each one of those vectors in the final layer to simultaneously make a prediction for what would come immediately after it. There's a lot more to be said about training later on, but I just want to call that out right now. This matrix is called the unembedding matrix, and we give it the label WU. Again, like all the weight matrices we see, its entries begin at random, but they are learned during the training process. Keeping score on our total parameter count, this unembedding matrix has one row for each word in the vocabulary, and each row has the same number of elements as the embedding dimension. It's very similar to the embedding matrix, just with the order swapped, so it adds another 617 million parameters to the network, meaning our count so far is a little over 1 billion. a small but not wholly insignificant fraction of the 175 billion that we'll end up with in total. As the very last mini lesson for this chapter, I want to talk more about this softmax function, since it makes another appearance for us once we dive into the attention blocks. The idea is that if you want a sequence of numbers to act as a probability distribution, say a distribution over all possible next words, then each value has to be between 0 and 1, and you also need all of them to add up to 1. However, if you're playing the deep learning game, where everything you do looks like matrix vector multiplication, the outputs that you get by default don't abide by this at all. The values are often negative or much bigger than 1, and they almost certainly don't add up to 1. Softmax is the standard way to turn an arbitrary list of numbers into a valid distribution in such a way that the largest values end up closest to 1, and the smaller values end up very close to 0. That's all you really need to know. But if you're curious, the way that it works is to first raise e to the power of each of the numbers, which means you now have a list of positive values, and then you can take the sum of all those positive values and divide each term by that sum, which normalizes it into a list that adds up to 1. You'll notice that if one of the numbers in the input is meaningfully bigger than the rest, then in the output, the corresponding term dominates the distribution. So if you were sampling from it, you'd almost certainly just be picking the maximizing input. But it's softer than just picking the max, in the sense that when other values are similarly large, they also get meaningful weight in the distribution, and everything changes continuously as you continuously vary the inputs. In some situations, like when ChatGPT is using this distribution to create a next word, there's room for a little bit of extra fun by adding a little extra spice into this function with a constant t thrown into the denominator of those exponents. We call it the temperature since it vaguely resembles the role of temperature in certain thermodynamics equations. And the effect is that when t is larger, you give more weight to the lower values, meaning the distribution is a little bit more uniform. And if t is smaller, then the bigger values will dominate more aggressively. Where in the extreme, setting t equal to 0 means all of the weight goes to that maximum value. For example, I'll have GPT-3 generate a story with the seed text, "Once upon a time there was A," but I'm going to use different temperatures in each case. Temperature 0 means that it always goes with the most predictable word. And what you get ends up being kind of a trite derivative of Goldilocks. A higher temperature gives it a chance to choose less likely words, but it comes with a risk. In this case, the story starts out a bit more originally, about a young web artist from South Korea, but it quickly degenerates into nonsense. Technically speaking, the API doesn't actually let you pick a temperature bigger than 2. There is no mathematical reason for this. It's just an arbitrary constraint imposed, I suppose, to keep their tool from being seen generating things that are too nonsensical. So if you're curious, the way this animation is actually working is I'm taking the 20 most probable next tokens that GPT-3 generates, which seems to be the maximum they'll give me, and then I tweak the probabilities based on an exponent of 1/5. As another bit of jargon, in the same way that you might call the components of the output of this function probabilities, people often refer to the inputs as logits, or some people say logits, some people say logits. I'm going to say logits. So for instance, when you feed in some text, you have all these word embeddings flow through the network, and you do this final multiplication with the unembedding matrix. Machine learning people would refer to the components in that raw, unnormalized output as the logits for the next word prediction. A lot of the goal with this chapter was to lay the foundations for understanding the attention mechanism, Karate Kid wax on, wax off style. You see, if you have a strong intuition for word embeddings, for softmax, for how dot products measure similarity, and also the underlying premise that most of the calculations have to look like matrix multiplication with matrices full of tunable parameters, then understanding the attention mechanism, this cornerstone piece in the whole modern boom in AI, should be relatively smooth. For that, come join me in the next chapter. As I'm publishing this, a draft of that next chapter is available for review by Patreon supporters. A final version should be up and public.
Okay, any questions about that video before we move on to the next? Good, everything pretty clear?
Yeah, I wanted to ask a question.
Yes.
Yeah, when he talked about, certain word being used in context, in like, the pool of words, I'm trying to understand, does it work like that in protein? In case, just for example, we have ton of proteins, And does this work in large language model for proteins? Like the particular amino acid might, have different functions, in different pathways. Does it really relate to how certain amino acid might, activate different pathways, with reference to other pathways? This is how this works in large language model of proteins.
Yeah, so essentially by training on a lot of your examples, like where amino acids have been seen in many different contexts, it can start to learn like what combinations of amino acids mean and what single amino acids mean in terms of, are you seeing them on the surface of the protein or maybe on the interior, it's having these effects and that effects. Like the context can like, by the fact that you see it in lots of different examples, you can start to learn like what combinations you might be expecting to see. And then when it comes down to like actually trying to embed that specific amino acid and then going through the layers of like those update steps, you'll start to essentially, your transformer will be like asking these questions of like what sorts of features is it seeing, and therefore like updating the like essentially embedding of the different amino acids in terms of, okay, I'm seeing you next to this other amino acid that's, and when you two are together, I expect this function, and therefore be like updating them in that way. And so yeah, the similar sorts of like trying to learn how amino acids come together and how when they are come together in certain like motifs, like certain results would happen.
Thank you.
Okay, let's switch to the other video then. This one's gonna go deeper into what's actually going on with the attention mechanism.
You and I started to step through the internal workings of a transformer. This is one of the key pieces of technology inside large language models and a lot of other tools in the modern wave of AI. It first hit the scene in a now famous 2017 paper called Attention is All You Need. And in this chapter, you and I will dig into what this attention mechanism is, visualizing how it processes data. As a quick recap, here's the important context I want you to have in mind. The goal of the model that you and I are studying is to take in a piece of text and predict what word comes next. The input text is broken up into little pieces that we call tokens, and these are very often words or pieces of words. But just to make the examples in this video easier for you and me to think about, let's simplify by pretending the tokens are always just words. The first step in a transformer is to associate each token with a high-dimensional vector, what we call its embedding. Now, the most important idea I want you to have in mind is how directions in this high-dimensional space of all possible embeddings can correspond with semantic meaning. In the last chapter, we saw an example for how direction can correspond to gender, in the sense that adding a certain step in this space can take you from the embedding of a masculine noun to the embedding of the corresponding feminine noun. That's just one example. You could imagine how many other directions in this high-dimensional space could correspond to numerous other aspects of a word's meaning. The aim of a transformer is to progressively adjust these embeddings so that they don't merely encode an individual word, but instead they bake in some much, much richer contextual meaning. I should say up front that a lot of people find the attention mechanism, this key piece in a transformer, very confusing. So don't worry if it takes some time for things to sink in. I think that before we dive into the computational details and all the matrix multiplications, it's worth thinking about a couple examples for the kind of behavior that we want attention to enable. Consider the phrases American shrew mole, 1 mole of carbon dioxide, and take a biopsy of the mole. You and I know that the word mole has different meanings in each one of these based on the context. But after the first step of a transformer, the one that breaks up the text and associates each token with a vector, the vector that's associated with mole would be the same in all three of these cases, because this initial token embedding is effectively a lookup table with no reference to the context. It's only in the next step of the transformer that the surrounding embeddings have the chance to pass information into this one. The picture you might have in mind is that there are multiple distinct directions in this embedding space, encoding the multiple distinct meanings of the word mole, and that a well-trained attention block calculates what you need to add to the generic embedding to move it to one of these more specific directions as a function of the context. To take another example, consider the embedding of the word tower. This is presumably some very generic, non-specific direction in the space associated with lots of other large, tall nouns. If this word was immediately preceded by Eiffel, you could imagine wanting the mechanism to update this vector so that it points in a direction that more specifically encodes the Eiffel Tower, maybe correlated with vectors associated with Paris and France and things made of steel. If it was also preceded by the word miniature, then the vector should be updated even further so that it no longer correlates with large, tall things. More generally than just refining the meaning of a word, the attention block allows the model to move information encoded in one embedding to that of another, potentially ones that are quite far away, and potentially with information that's much richer than just a single word. What we saw in the last chapter was how after all of the vectors flow through the network, including many different attention blocks, the computation that you perform to produce a prediction of the next token is entirely a function of the last vector in the sequence. So imagine, for example, that the text you input is most of an entire mystery novel, all the way up to a point near the end, which reads, "Therefore the murderer was." If the model is going to accurately predict the next word, that final vector in the sequence, which began its life simply embedding the word "was," will have to have been updated by all of the attention blocks to represent much, much more than any individual word, somehow encoding all of the information from the full context window that's relevant to predicting the next word. To step through the computations, though, let's take a much simpler example. Imagine that the input includes the phrase, "A fluffy blue creature roamed the verdant forest." And for the moment, suppose that the only type of update that we care about is having the adjectives adjust the meanings of their corresponding nouns. What I'm about to describe is what we would call a single head of attention, and later we will see how the attention block consists of many different heads run in parallel. Again, the initial embedding for each word is some high-dimensional vector that only encodes the meaning of that particular word with no context. Actually, that's not quite true. They also encode the position of the word. There's a lot more to say about the specific way the positions are encoded, but right now, all you need to know is that the entries of this vector are enough to tell you both what the word is and where it exists in the context. Let's go ahead and denote these embeddings with the letter E. The goal is to have a series of computations.
So why do you need that positional encoding for something like a transformer? So you have to label essentially each.
Because you need to know like the orders, like which words come before or after others.
Yeah, so like why do you need that for a transformer when you don't need that for something like an RNN?
So that it's aware of the different position of where it's aware of the different position where then for example for protein, you kind of do this kind of positional encoding so that it's aware of where a certain amino acid is, it's like the standard, it's just aware of where every amino acid is within every protein, something like that.
Yeah, definitely. Like it doesn't make sense. Like the same set of amino acids scrambled is a completely different protein. So why don't you need that for something like an RNN? Why don't you need the positional encoding?
Recurrent RNN is recurrent neural network.
Yes. Are you doing everything in parallel for an RNN?
It's basically going to come from the architecture itself because transformer actually takes is aware of where these things are in a way the RNN can't. So its attention, just like the name says, attention. It pays attention to those particular sections or particular structures in a way the RNN model can't.
Yeah. So like, what is the difference? So does that
RNNs cannot be run in parallel. They're like each step is dependent on the step before.
Yeah, so that means that you're kind of getting the order, that the order is important already in the RNN because the only way an amino acid is gonna be like happening in like position 3, you'll directly have already seen position 2, and the thing that's coming next is the position 3.
So that position information is then already.
Already in the
present, so
model.
You don't need to do this.
Yeah, whereas now here, all you're doing is all of the words or all the amino acids all have an embedding, and now you're gonna be multiplying these certain vectors associated with each of these next to each other. But all of this multiplication happens at once, and so there's no notion of order already. Like you could have scrambled the words and you would still get the same output, because all it is figuring out, like, if I'm this word and this other one is this word, what do the matrices that go with each of those look like then multiplied together, with no notion of order. And so you actually need to explicitly add the position encoding into that so that there is a notion of order, because everything is just happening all at once. So also, what do you think are some good criteria for position encoding? It's not just that they're labeled like 1, 2, 3, but they use some sort of like transformation. But like what, like, are there any like features that you think would make sense to like make sure that these position encodings can be used in a way that's actually like meaningful? So like what might you want about things that are like next to each other? You would want like some notion of like the distance between like position 2 and position 3 should that be like similar to the distance between position 100 and 101? Like what are some like features that make sense for these encodings?
One could be charged.
So at the moment we're just dealing with like what's your like order, what's your like element number, and so like what are some features in terms of trying and turn that element number into like an actual encoding of a position? What things might you want that encoding to look like?
In the space of like words
Or in the space of like the positional encoding is being turned into a vector of some sort or a value of some sort. What do you want to be true of those vectors? Just like general like criteria. Like for one, you want like
unique for each word then?
or unique for each position. Yeah, that's definitely true. And you want it to always be the same, like deterministic.
Mm-hmm.
Yes. What else might you want?
Maybe, I don't know if this is like what you're asking, but like in English, you would want the positions that are right before that given position to be looked at like very closely in how they can affect that position versus like after that position, there might be more of like an action like type relationship.
Okay, so this we'll get into a little bit more of the difference between before and after, and like whether you are actually going to be able to even pay attention to things that come after. Because for instance, if you're trying to predict the next token, you don't really have access to everything that comes in the future anyway. So, but that would be a good point that like if you did have access to that future stuff, that you might want to weight the future things differently. But what about like the fact that do you want to be weighting things that are closer better than things that are further away? So you want, like when you're talking about positional encodings, you want some notion of like common distances when you're thinking of like different step sizes in your like distance. So like the difference between like position 2 and position 3 should be like a similar value than the position between 91 and 92. So those are both just like 1 apart. And you don't want, when you're like later in a sentence, positions to like the difference between positions to be like much bigger than maybe at the start of a sentence. You want like when you're talking about the difference between things that are like a set distance apart from one another, you want that to be constant throughout. And so this isn't going to go into exactly like how you calculate positional encodings, but that might give you like a little bit of thought about like what's actually being used there and why you actually need it for a transformer as opposed to like why we didn't need it before.
Produce a new refined set of embeddings where, for example, those corresponding to the nouns have ingested the meaning from their corresponding adjectives. And playing the deep learning game, we want most of the computations involved to look like matrix vector products, where the matrices are full of tunable weights, things that the model will learn based on data. To be clear, I'm making up this example of adjectives updating nouns just to illustrate the type of behavior that you could imagine an attention head doing. As with so much deep learning, the true behavior is much harder to parse because it's based on tweaking and tuning a huge number of parameters to minimize some cost function. It's just that as we step through all of the different matrices filled with parameters that are involved in this process, I think it's really helpful to have an imagined example of something that it could be doing to help keep it all more concrete. For the first step of this process, you might imagine each noun, like creature, asking the question, hey, are there any adjectives sitting in front of me? And for the words fluffy and blue to each be able to answer, yeah, I'm an adjective and I'm in that position. That question is somehow encoded as yet another vector, another list of numbers, which we call the query for this word. This query vector, though, has a much smaller dimension than the embedding vector, say 128. Computing this query looks like taking a certain matrix, which I'll label WQ, and multiplying it by the embedding. Compressing things a bit, let's write that query vector as Q, and then anytime you see me put a matrix next to an arrow like this one, it's meant to represent that multiplying this matrix by the vector at the arrow's start gives you the vector at the arrow's end. In this case, you multiply this matrix.
Do we understand the dimensions of this and what this like matrix multiplication looks like? So here we have a matrix and here we have one vector. So how are you actually like making like this value right here? What are you actually doing? So if you notice like by size, you should have like this should be essentially the same length as your embedding one, and this one's the shorter distance of 128. So you have 128 here. This is going to be like the size of your embedding, and then this here is the newer output. So this is also the embedding, and then this is our new thing of size 128. So you start with something. This line here is the size of your embedding, and you have 128 of these lines. And then you also have a size 128 of your query vector. So how could you possibly, how would you think you make this value considering it's the first of 128 values?
It would be the first value in E, and then multiply all the terms of the first row of W, and then summing them.
Do you think this
No.
one for all of these? Or do you think this one for the first value and the second one for the second value?
I don't remember if it's the dot product or.
I think this one should be dot product, right? So like, yeah, so that you want not just this value to matter only for the first row, but because this thing should be essentially, if you think about it in terms of lengths, this is the length of your embedding, which is what, 12,000? And this length here is 12,000. So like, what would it make sense to be doing? And then this height is 128, and this height is 128. So if you think about it just of heights, it makes sense that the first value here must be because of the first row, because both of these heights are 128, right? And then these lengths, this length is 12,000, and this one here is 12,000. So it makes sense that each value here should correspond to each column here, if you just think about it in terms of lengths. And so it should be like this one multiplying by this value here, this one multiplied by this value here, and then what else is there to do besides like sum them? And so I think like when you're not sure like what the matrix multiplication is actually doing, thinking about what the lengths are is like super helpful.
By all of the embeddings in the context, producing one query vector for each token. The entries of this matrix are parameters of the model, which means the true behavior is learned from data, and in practice, what this matrix does in a particular attention head is challenging to parse. But for our sake, imagining an example that we might hope that it would learn, we'll suppose that this query matrix maps the embeddings of nouns to certain directions in this smaller query space that somehow encodes the notion of looking for adjectives in preceding positions. As to what it does to other embeddings, who knows? Maybe it simultaneously tries to accomplish some other goal with those. Right now, we're laser focused on the nouns. At the same time, associated with this is a second matrix called the key matrix, which you also multiply by every one of the embeddings. This produces a second sequence of vectors that we call the keys. Conceptually, you want to think of the keys as potentially answering the queries. This key matrix is also full of tunable parameters, and just like the query matrix, it maps the embedding vectors to that same smaller dimensional space. You think of the keys as matching the queries whenever they closely align with each other. In our example, you would imagine that the key matrix maps the adjectives, like fluffy and blue, to vectors that are closely aligned with the query produced by the word creature. To measure how well each key matches each query, you compute a dot product between each possible key query pair. I like to visualize a grid full of a bunch of dots, where the bigger dots correspond to the larger dot product.
Does it make sense why dot product is a measure of how similar that key is to the query? So if you think of each of those as two vectors, what would happen if those two values are kind of like very dissimilar to one another?
There'll be difference in the widths.
Yeah, so if they're very dissimilar to each other, when you're thinking about like the first index of those vectors, maybe one is really big and the other one's like really small. And then at the second index, maybe like one is 0 and one is like a really big number. And so like at each different element, if there are big differences there, when you take the dot product, that dot product will like probably be really small, right? Because you're multiplying the like elements together. So the first elements together, the second elements together. And so if these are pointing in completely different directions, like those will be very different values. Like for instance, like one vector could be like very similar to another vector in terms of the values, but like completely different order. But this measure of similarity is like, are you the same in the first element? Are you the same in the second element? Are you the same in the third element? And so the dot product is a measure of like when you're going like element by element, are you similar or not? And that's why it can be used to like do these weights of similarity between key and query when you're doing a dot product between the two of them.
Products, the places where the keys and queries align. For our adjective noun example, that would look a little more like this, where if the keys produced by fluffy and blue really do align closely with the query produced by creature, then the dot products in these two spots would be some large positive numbers. In the lingo, machine learning people would say that this means the embeddings of fluffy and blue attend to the embedding of creature. By contrast to the dot product between the key for some other word, like the, and the query for creature, would be some small or negative value that reflects that these are unrelated to each other.
Is it the magnitude here that's important, or is it high positive values that are important?
Magnitude and direction.
So, does it matter if two things are like the same, but essentially like opposite directions to each other? So like a negative value, like a very high negative value, would that be like a large or like a small like importance weight, do you think?
Well,
Yeah. So it's not like, yeah, so it's not just like the magnitude, but like the direction also really matters here.
So we have this grid of values that can be any real number from -infinity to infinity, giving us a score for how relevant each word is to updating the meaning of every other word. The way we're about to use these scores is to take a certain weighted sum along each column, weighted by the relevance. So instead of having values range from -infinity to infinity, what we want is for the numbers in these columns to be between 0 and 1, and for each column to add up to 1.
So who can say what transformation they're going to use here? Yes, exactly.
If they were a probability distribution. If you're coming in from the last chapter, you know what we need to do then. We compute a softmax along each one of these columns to normalize the values. In our picture, after you apply softmax to all of the columns, we'll fill in the grid with these normalized values. At this point, you're safe to think about each column as giving weights according to how relevant the word on the left is to the corresponding value at the top. We call this grid an attention pattern. Now, if you look at the original transformer paper, there's a really compact way that they write this all down. Here, the variables q and k represent the full arrays of query and key vectors respectively, those little vectors you get by multiplying the embeddings by the query and the key matrices. This expression up in the numerator is a really compact way to represent the grid of all possible dot products between pairs of keys and queries. A small technical detail that I didn't mention is that for numerical stability, it happens to be helpful to divide all of these values by the square root of the dimension in that key query space. Then this softmax that's wrapped around the full expression is meant to be understood to apply.
So why are we doing query key transpose instead of just like query times key? What would it be if you weren't doing like query key transpose like this? What would that mean instead? Like a dot product.
What does query key transpose mean?
So the query key transpose was originally query and key are just both vectors like this, right? So they're the same, they're going like the same way in a sense. So if you were to just dot product them, it would be query 1 times key 1 and query 2 times key 2. That wouldn't actually get you at like the impact of, say, for instance, query 1 on key 3. What you actually want to do is treat this as if you're like trying to get a full matrix. So the full matrix, as opposed to just having query 1 interact with key 1, transposes keys. So like now the query is like a vector in like one dimension, and the keys is now essentially like the vertical vector. And so instead of just having the diagonal of query 1, query 2, key 2, you're having all of these things happen as well. So you have Q1 and query 2 and Q1 and query 3. And so that makes sense why you want like the full like matrix and not just like a dot product essentially of query and key and query. Right?
Yes.
That I didn't mention is that for numerical stability, it happens to be helpful to divide all of these values by the square root of the dimension in that key query space. Then this softmax that's wrapped around the full expression is meant to be understood to apply column by column. As to that V term, we'll talk about it in just a second. Before that, there's one other technical detail that so far I've skipped. During the training process, when you run this model on a given text example, and all of the weights are slightly adjusted and tuned to either reward or punish it based on how high a probability it assigns to the true next word in the passage, it turns out to make the whole training process a lot more efficient if you simultaneously have it predict every possible next token following each initial subsequence of tokens in this passage. For example, with the phrase that we've been focusing on, it might also be predicting what words follow creature and what words follow the. This is really nice because it means what would otherwise be a single training example effectively acts as many. For the purposes of our attention pattern, it means that you never want to allow later words to influence earlier words, since otherwise they could kind of give away the answer for what comes next. What this means is that we want all of these spots here, the ones representing later tokens influencing earlier ones, to somehow be forced to be 0. The simplest thing you might think to do is to set them equal to 0, but if you did that, the columns wouldn't add up to 1 anymore. They wouldn't be normalized. So instead, a common way to do this is that before applying softmax, you set all of those entries to be negative infinity. If you do that, then after applying softmax, all of those get turned into 0, but the columns stay normalized. This process is called masking. There are versions of attention where you don't apply it, but in our GPT example, even though this is more relevant during the training phase than it would be, say, running it as a chatbot or something like that, you do always apply this masking to prevent later tokens from influencing earlier ones. Another fact that's worth reflecting on about this attention pattern is how its size is equal to the square of the context size. So this is why context size can be a really huge bottleneck for large language models, and scaling it up is non-trivial. As you might imagine, motivated by a desire for bigger and bigger context windows, recent years have seen some variations to the attention mechanism aimed at making context more scalable. But right here, you and I are staying focused on the basics.
So if you were modeling proteins or DNA or RNA, how important do you think that context window is? The video had said earlier that what this GPT was using was size 2048. But do you think that's big enough, not too big for like proteins, or if you're doing DNA? What do you think?
I mean, it will actually depend on the length of the protein in context. And some proteins are larger, some are smaller.
Yeah, do you think most proteins are within 2,000 amino acids? Probably.
Yeah, sure.
Yeah, so you end up, well, there certainly are proteins that are longer than that. And there are a lot of models, the biological language models, instead of doing the 2048, they're actually 1,024. And even then, I would say like most proteins fit within that context window. But sometimes they don't, in which case you'll have to do some tricks like sliding the context window across your protein and then somehow getting an aggregate score. What about for like if you're trying to do a genome model? Does 1,000 or 2,000 bases, do you think that is big enough?
Yeah.
So maybe if you're trying to, for instance, fold one particular RNA, you might be borderline there. But like, what if you're like trying to understand how like one promoter influences some very far away genomic element?
You need like on the order of like 10,000.
Yeah. So that's where you start getting into the problem when you're getting to like genome scale language modeling, that you really have to figure out what are you going to do about these context windows, where it does matter that like some promoter or some enhancer is right next to like a certain biological element, but you have all these really, really long distance relationships in biology where like kind of the simplest versions of like directly using these natural language models, yeah, don't work once you start getting into like those larger and larger context size. And I would say like no one's really successfully done like genome scale on a way that's like really working yet. How was our experience? Say excellent.
Okay, great. Computing this pattern lets the model deduce which words are relevant to which other words. Now you need to actually update the embeddings, allowing words to pass information to whichever other words they're relevant to. For example, you want the embedding of fluffy to somehow cause a change to creature that moves it to a different part of this 12,000 dimensional embedding space that more specifically encodes a fluffy creature. What I'm going to do here is first show you the most straightforward way that you could do this, though there's a slight way that this gets modified in the context of multi-headed attention. This most straightforward way would be to use a third matrix, what we call the value matrix, which you multiply by the embedding of that first word, for example, fluffy. The result of this is what you would call a value vector, and this is something that you add to the embedding of the second word, in this case, something you add to the embedding of creature. So this value vector lives in the same very high dimensional space as the embeddings. When you multiply this value matrix by the embedding of a word, you might think of it as saying, if this word is relevant to adjusting the meaning of something else, what exactly should be added to the embedding of that something else in order to reflect this? Looking back in our diagram, let's set aside all of the keys and the queries, since after you compute the attention pattern, you're done with those. Then you're going to take this value matrix and multiply it by every one of those embeddings to produce a sequence of value vectors. You might think of these value vectors as being kind of associated with the corresponding keys. For each column in this diagram, you multiply each of the value vectors by the corresponding weight in that column. For example, here, under the embedding of creature, you would be adding large proportions of the value vectors for fluffy and blue, while all of the other value vectors get zeroed out, or at least nearly zeroed out. And then finally, the way to actually update the embedding associated with this column, previously encoding some context-free meaning of creature, you add together all of these rescaled values in the column, producing a change that you want to add that I'll label delta E, and then you add that to the original embedding. Hopefully, what results is a more refined vector encoding the more contextually rich meaning, like that of a fluffy blue creature. And of course, you don't just do this to one embedding, you apply the same weighted sum across all of the columns in this picture, producing a sequence of changes. Adding all of those changes to the corresponding embeddings produces a full sequence of more refined embeddings popping out of the attention block. Zooming out, this whole process is what you would describe as a single head of attention. As I've described things so far, this process is parameterized by three distinct matrices, all filled with tunable parameters: the key, the query, and the value. I want to take a moment to continue what we started in the last chapter with the scorekeeping, where we count up the total number of model parameters using the numbers from GPT-3. These key and query matrices each have 12,288 columns, matching the embedding dimension, and 128 rows, matching the dimension of that smaller key query space. This gives us an additional 1.5 million or so parameters for each one. If you look at that value matrix by contrast, the way I've described things so far would suggest that it's a square matrix that has 12,288 columns and 12,288 rows.
What do you guys think? Do you think it makes sense for this value matrix to have this many times more parameters to learn than the query and key matrices? Do you think it's more important, or do you think you should find a way to make it smaller?
I mean, I don't know, but I would look at it in terms of how computationally expensive it can be.
Mm-hmm.
Yeah, so if there's a way to make it small, I mean, so that you reserve computational cost, it would make sense.
Yeah, are you guys all in the same boat, or do you think the value matrix like deserves more parameters? Yeah, let's see what they end up doing.
Since both its inputs and its outputs live in this very large embedding space. If true, that would mean about 150 million added parameters. And to be clear, you could do that. You could devote orders of magnitude more parameters to the value map than to the key and query. But in practice, it is much more efficient if instead you make it so that the number of parameters devoted to this value map is the same as the number devoted to the key and the query. This is especially relevant in the setting of running multiple attention heads in parallel. The way this looks is that the value map is factored as a product of two smaller matrices. Conceptually, I would still encourage you to think about the overall linear map, one with inputs and outputs both in this larger embedding space. For example, taking the embedding of blue to this blueness direction that you would add to nouns. It's just that it's broken up into two separate steps. The first matrix on the right here has a smaller number of rows, typically the same size as the key query space. What this means is you can think of it as mapping the large embedding vectors down to a much smaller space. This is not the conventional naming, but I'm going to call this the value down matrix. The second matrix maps from this smaller space back up to the embedding space, producing the vectors that you use to make the actual updates. I'm going to call this one the value up matrix, which again is not conventional. The way that you would see this written in most papers looks a little different. I'll talk about it in a minute. In my opinion, it tends to make things a little more conceptually confusing. To throw in linear algebra jargon here, what we're basically doing is constraining the overall value map to be a low rank transformation.
Does that low rank transformation make sense? Why you can use those two matrices, even though they're much smaller, to still make something go from like the large embedding size to large embedding size? Does that make sense? So you're taking something.
Value down matrix.
Both of these
The second matrix maps from this smaller.
So you have your initial embedding that's of size 12,288. And so you want to end up with an output that's also 12,288. And so one way to get from 12,288 to again 12,288 is to just have one matrix in the middle that essentially input dimension of the matrix is also 12,888 and the output is also the same. Another way to have it is to have two matrices, one that's has an input dimension that's the same, and I'm saying input dimension and output dimension because you can kind of think of these matrices as depending on how many rows and how many columns they are. If you're using kind of that input dimension and you're multiplying each element of there with like your original like input matrix, that needs to be the same dimension as the input matrix. So you can't have that input dimension be a smaller number because if you're going to like element wise multiply, for instance, each of these values with your embedding thing that's also 12,288, if this was shorter, you wouldn't be able to like element wise multiply. So this like input dimension needs to be the same as your like dimension you had before. So this is going to take your thing that's of size 12,288 and move it into a space that's of size 128. And now that means you need a second matrix whose input dimension matches the output size of this one. And now the new output size is 128. And so you take something that's now gonna move to like element wise multiply these 128 values. And so that input dimension needs to be 1288. And so that's why here you have this shorter matrix where the input dimension is 1288. And now the last one is this larger one again. And so you're going from something that's of size is 12,000, and then you have one matrix that transforms the large dimension into the smaller dimension, and then another one that transforms the smaller dimension back out again into the larger dimension. And this is much smaller than just having an original like transforming matrix that's already 12,000 by 12,000, because instead you're doing 12,000 by 128 plus like times 2. So does that make kind of a little bit more sense of what this like matrix multiplying is doing? I think it like, for me, in terms of like understanding like what dimensions things need to be, it's like easy to think about like the matrix multiplication just in terms of like what's your input dimension, what's your output dimension, and then for your next matrix, like the input dimension needs to like match the previous output dimension.
Space back up to the embedding space, producing the vectors that you use to make the actual updates. I'm going to call this one the value up matrix, which again is not conventional. The way that you would see this written in most papers looks a little different. I'll talk about it in a minute. In my opinion, it tends to make things a little more conceptually confusing. To throw in linear algebra jargon here, what we're basically doing is constraining the overall value map to be a low rank transformation. Turning back to the parameter count, all 4 of these matrices have the same size, and adding them all up, we get about 6.3 million.
You have a question?
Sorry, just wondering, so when you're doing the low rank transformation, does the order of the multiplication matter? Because like usually like just integers, it doesn't really matter how you multiply it.
Yeah, your order would matter, because if you went from, for instance, so you're starting at your 12,000.
Yeah.
You couldn't start with a matrix whose
That's
input dimension was
128,
128, because you could have 128 things that you're trying to multiply by 12,000 things, and you're trying to element wise multiply these. You wouldn't be able to do that. And so you need to start with the matrix whose input dimension is the same as your like input matrix.
In parameters for one attention head. As a quick side note, to be a little more accurate, everything described so far is what people would call a self-attention head, to distinguish it from a variation that comes up in other models that's called cross-attention. This isn't relevant to our GPT example, but if you're curious, cross-attention involves models that process 2 distinct types of data, like text in one language and text in another language that's part of an ongoing generation of a translation.
How do you think doing what do you think changes when you move from the self-attention space to the cross-attention space? We have our query, key, and value vectors. What do you think like actually changes now that we have 2 paired inputs, like something in one language and something in a second language? Like before we wanted, for instance, every word in our first thing, like I want pet to attend to, I do not want to pet and it. What do we want pet now to attend to? Is it going to be words in the same sentence, or is it going to be words in the other sentence, the paired sentence?
Word or words in the the French.
Yeah, in the French sentence. So what do you think you actually like are changing? You've got your before we were doing a query and a key to make those weights of how much to attend between like the pair of pet and want. Now what are we trying to attend to? Like, well, how do we change our query and our key? So if our query is, for instance, pet, what, and like corresponding to pet, what might we want the key to correspond to? Is it gonna be the words in the English sentence, or is it gonna be words in the French sentence?
I mean, this is where we talk about context also.
Mm-hmm.
It's basically going to maybe connect to words that are kind of synonym of pets.
Yeah, so French words.
Yeah.
Yeah, exactly. So if you're trying to get your model to learn what goes with pet, it's going to be what in French goes with pet. So if your key, or if it, so like you instead of your key and your query both being words of the same sentence, now they're of the opposite sentences, and you're doing cross attention across.
Or
across
maybe
the two.
audio input of speech and an ongoing transcription. A cross-attention head looks almost identical. The only difference is that the key and query maps act on different data sets. In a model doing translation, for example, the keys might come from one language, while the queries come from another, and the attention pattern could describe which words from one language correspond to which words in another. And in this setting, there would typically be no masking, since there's not really any notion of later tokens affecting earlier ones. Staying focused on self-attention, though, if you understood everything so far, and if you were to stop here, you would come away with the essence of what attention really is. All that's really left to us is to lay out the sense in which you do this many, many different times. In our central example, we focused on adjectives updating nouns, but of course, there are lots of different ways that context can influence the meaning of a word. If the words "they crashed the" preceded the word "car," it has implications for the shape and the structure of that car. And a lot of associations might be less grammatical. If the word "wizard" is anywhere in the same passage as Harry, it suggests that this might be referring to Harry Potter. Whereas if instead the words Queen, Sussex, and William were in that passage, then perhaps the embedding of Harry should instead be updated to refer to the prince. For every different type of contextual updating that you might imagine, the parameters of these key and query matrices would be different to capture the different attention patterns, and the parameters of our value map would be different based on what should be added to the embeddings. And again, in practice, the true behavior of these maps is much more difficult to interpret, where the weights are set to do whatever the model needs them to do to best accomplish its goal of predicting the next token. As I said before, everything we described is a single head of attention, and a full attention block inside a transformer consists of what's called multi-headed attention, where you run a lot of these operations in parallel, each with its own distinct key, query, and value maps. GPT-3, for example, uses 96 attention heads inside each block. Considering that each one is already a bit confusing, it's certainly a lot to hold in your head. Just to spell it all out very explicitly, this means you have 96 distinct key and query matrices, producing 96 distinct attention patterns. Then each head has its own distinct value matrices, used to produce 96 sequences of value vectors. These are all added together using the corresponding attention patterns as weights. What this means is that for each position in the context, each token, every one of these heads produces a proposed change to be added to the embedding in that position. So what you do is you sum together all of those proposed changes, one for each head, and you add the result to the original embedding of that position. This entire sum here would be one slice of what's outputted from this multi-headed attention block, a single one of those refined embeddings that pops out the other end of it. Again, this is a lot to think about, so don't worry at all if it takes some time to sink in. The overall idea is that by running many distinct heads in parallel, you're giving the model the capacity to learn many distinct ways that context changes meaning. Pulling up a
Does that make sense? What's kind of like the similar thing when we were talking about CNNs? How were we able to learn like multiple different like kinds of weights that are important?
Just like in CNN, the model is learning the different layers that make up the image, the edge, different kind of edge. I think it's the same thing with layer 2.
Yeah, and how was it able to learn like different kinds of edges? Like have certain things learn do edge detection, have certain things learn to do something else? What was the mechanism that the CNN is using?
It was I think the deeper the layer, each layer is able to learn different sections or different edges of an input image.
Yeah, so we had these different like kernels that were like going across the image, and maybe one filter is gonna, like in the RNA example, one filter you would hope would learn one type of motif, and another filter would learn a different type of motif. And those are each gonna start with like different random initializations. And like through that you hope that when you train it, that each one would be learning different things. So kind of same thing here, you have multiple heads of your attention, and so the hope is that by doing all of these simultaneously, certain ones are gonna pick up on some details and certain ones are gonna pick up on some other details.
Our running tally for parameter count, with 96 heads, each including its own variation of these four matrices, each block of multi-headed attention ends up with around 600 million parameters.
So many.
There's one added, slightly annoying thing that I should really mention for any of you who go on to read more about transformers. You remember how I said that the value map is factored out into these two distinct matrices, which I labeled as the value down and the value up matrices. The way that I framed things would suggest that you see this pair of matrices inside each attention head. And you could absolutely implement it this way. That would be a valid design. But the way that you see this written in papers and the way that it's implemented in practice looks a little different. All of these value up matrices for each head appear stapled together in one giant matrix that we call the output matrix, associated with the entire multi-headed attention block. And when you see people refer to the value matrix for a given attention head, they're typically only referring to this first step, the one that I was labeling as the value down projection into the smaller space. For the curious among you, I've left an on-screen note about it. It's one of those details that runs the risk of distracting from the main conceptual points, but I do want to call it out just so that you know if you read about this in other sources. Setting aside all the technical nuances, in the preview from the last chapter, we saw how data flowing through a transformer doesn't just flow through a single attention block. For one thing, it also goes through these other operations called multi-layer perceptrons. We'll talk more about those in the next chapter. And then it repeatedly goes through many, many copies of both of these operations. What this means is that after a given word imbibes some of its context, there are many more chances for this more nuanced embedding to be influenced by its more nuanced surroundings. The further down the network you go, with each embedding taking in more and more meaning from all the other embeddings, which themselves are getting more and more nuanced, the hope is that there's the capacity to encode higher level and more abstract ideas about a given input beyond just descriptors and grammatical structure. Things like sentiment and tone, whether it's a poem, and what underlying scientific truths are relevant to the piece, and things like that. Turning back one more time to our scorekeeping, GPT-3 includes 96 distinct layers, so the total number of key, query, and value parameters is multiplied by another 96, which brings the total sum to just under 58 billion distinct parameters devoted to all of the attention heads.
So for GPT-3, who thinks most of the parameters go into attention? So we think of back to transformer papers having titles like attention is all you need. Do you think the bulk of the parameters are attention, or they also mentioned the multi-layer perceptron? What do you think is your guess? Do you think it's 50-50? Do you think it's majority attention? Throw out some numbers.
Sorry, go ahead.
What do you think is the percent of the parameters that go towards the attention layers versus the multi-layer perceptron? So you have these attention blocks, and then you have just like kind of the normal neural network between them. And so when you're talking about transformers, oftentimes people think like attention is all you need. Attention is like most important. So do you think like 90% of the parameters here are these 57 million attention parameters, or what do you think the breakdown is? Just guess, throw out some numbers.
I would say that personally, I don't know, but I would say that a bulk of this concept will tell you that attention plays a critical role. Or I might just say that 70% might be attention, then the 30 is more high. 30% might be multi-layer perceptron, because when you look at it, you see that everything here has to do with context. It's looking at a different context of a particular word, and to know what comes next. So I think attention is going to take like 70%. The next 30 might actually be multi-layer perception.
Anyone else have a guess? Okay, let's see what it says.
That is a lot, to be sure, but it's only about a third of the 175 billion that are in the network in total.
So it's 33%.
So even though attention gets all of the attention, the majority of parameters come from the blocks sitting in between these steps. In the next chapter, you and I will talk more about those other blocks, and also a lot more about the training process. A big part of the story for the success of the attention mechanism is not so much any specific kind of behavior that it enables, but the fact that it's extremely parallelizable, meaning that you can run a huge number of computations in a short time using GPUs. Given that one of the big lessons about deep learning in the last decade or two has been that scale alone seems to give huge qualitative improvements in model performance, there's a huge advantage to parallelizable architectures that let you do this. If you want to learn more about this stuff, I've left lots of links in the description. In particular, anything produced by Andre Karpathy or Chris Olah tend to be pure
We've
gold.
already seen that.
In this video, I wanted to just jump into attention in its current form, but if you're curious about more of the history for how we got here and how you might reinvent this idea for yourself, my friend Vivek just put up a couple videos giving a lot more of that motivation. Also, Britt Cruz from the channel The Art of the Problem has a really nice video about the history of large language models.
Great. What did you all think? Do you have any questions off the bat?
This is a lot of concept.
Yeah, it definitely is. Let's just talk about motivation for a second now. Like, why do you think you might choose to use a transformer over some other like sequence models, like say an RNN? What kind of like decisions do you think would go into it? Like if you had like really short sequences to model his long sequences, do you think you would rather choose an RNN or do you think you'd rather choose a transformer?
I remember, I remember them mentioning that RNNs are bad with long distance relationships, so I would think that they'd be better for shorter things.
Yeah, do you know why are RNNs so much worse for longer sequences?
So data set?
Because it's on one way.
Mm-hmm.
That's why.
And so if it's doing the first and then it's doing the second and then it's doing the third, maybe by the time you're at the 100th, it's basically forgot what's going on with the first, right? And then instead here at the transformer, you're doing all this attention. So you're doing like the thing that's happening first is kind of just as much of a chance to influence what's happening on the 100th step than like the RNN where you might essentially have forgotten what's going on with the first thing by the time you're at the 100th thing. Any other like thoughts about why you might choose to use something like a transformer?
Maybe I would say that a transformer is good at mapping a relationship between the different.
Yeah, it's really good at figuring out the context and like the relationship and understand that you see this word in this context, it might be different than seeing it in the other context. And then again, like they said, that you go through the many different layers of it. So at the very beginning, you're looking more at maybe the small scale relationships. Like the same way when we talked about the CNN, like the initial layers are maybe like, are you seeing an edge here? And by the time you get to the end, you're getting at more and more fine grained of like, what kinds of patterns are you expecting to see a 7? Are you seeing like maybe the straight line here and another straight line? And these are like the aggregate things. In the transformer, you also get that aggregate context as you go further and further on. Your initial self-attention might be like more local of, yeah, the creature is blue and it's fluffy. Those are kind of right next to each other and those are important. And then by the time you've gone to the later and later layers, yeah, you're going to build up that kind of more nuanced context of like really how to like modify those embeddings based off like everything that it's seen.
We can have Yves from Atmo, good friend of the lab, presenting his work. It's going to be way less technical, more at the high level, what we can do with AI, like when we reapply it deeply on weather forecasts.
All right. Good day, everyone. Today we're going to talk about the weather. Also, talking about the weather can be, very appropriate for, an elevator conversation or a boring date, right? But on a darker note, for some people, a good weather forecast versus a bad weather forecast can literally mean life or death. So that's why, since we have computers, we've been very interested in the 50s. We've been very interested into forecasting the weather. Yet, we're not exactly to the point where we're totally satisfied with it. Actually, the current method that we've been using for the last decades haven't
really changed from the method we used in the 50s, and the quality increase is like a couple of % a year. It's not, you know, we're not exactly there yet with weather forecasting. And however, at most, so my group and also my company, essentially the company I work for, we work on developing a AI weather forecasting model. You know, you might be familiar with AI as we get through this whole workshop. And it presents inherent qualities like better accuracy, you know, faster forecasting, much faster forecasting, you know, learning from data, being much less expensive. So yeah, that's why, and like this is very good news for some people that would live in somewhere that had very poor forecasting, and you know, this information for them, having a good weather forecast, can help them get, you know, getting covered for an event or like an extreme event or something. So essentially, I'm not scared to say that to some extent we save the world with AI. And linear algebra, it's even more funnier. Anyways, so here's what it looks like, right? This is a live forecast. Now, this is a live forecast of the temperature across the globe. And you might have seen before some weather forecasts, right? I mean, it's not something uncommon. But what's very specific about this weather forecast is that it's AI powered. It's been built with AI, it's forecasted live with our deep learning models that's built in-house. And, you know, I think it looks pretty good. And, you know, it's very valuable information for many people. I'm going to explain that as we go. So we close this now. Perfect. Nope. Alors.
Just restart the presentation.
Yeah, share content. How do you do that? Presentation. You know, we try to do fancy stuff and then it fails.
Share content.
Yes. Meeting.
Just start the presentation.
Wonderful. All right, thank you. Never mind. Okay, so my name is Yves Martin. I worked with Sylvie Ruskin when I was at Stanford. So for 2 years, I work on RNA structure modeling. And then I decided to model, still like doing AI for physics and like biochemistry, like modeling the real world with AI models, but at a much bigger scale. And so these two fields have a much bigger connection than you would think, well, except for the scale. And so I thought you'd probably be interested into seeing what are the techniques and the results that happen into the weather forecast field using AI, and how that could impact your own research, whether it's in bio or in other fields. So today I'm going to talk to you about, like Atmo, I'm going to present this company I work for. I'm going to show you the projects we do and what kind of impact you can have doing deep learning with physics. Kind of why it works. I think it's an interesting chapter. Why is AI well suited for weather forecasting? How does it work and what doesn't work? I guess it's pretty straightforward. All right. So a little bit about the company. It's headquartered in San Francisco, California. It's exactly, there is a reason why it's here, is because it's exactly the Silicon Valley started to think of. We target a huge problem, which is, forecasting weather is pretty hard. We do it with the newest technology, which is deep learning. And we have a team of experts that founded cool companies before. Experts in AI, experts in meteorology. And what's really strong about this company is that we were in the starting blocks of not only forecasting the weather with AI, but also putting it into operations, right? So there is something about publishing a paper, but there is something else about like doing the proof concept. But there's still like this last mile that you need to do to get it to production. And so, not only we have very good research, but also we're able to deploy and provide products to customers, essentially. These customers are governments, militaries, corporations, so in general, big institutions that can afford their personal weather forecast and who need it. All right. So, maybe a bit of history about weather forecast. If you open the newspaper, in the 50s, you're in Arkansas, and you'll say, okay, what's the weather tomorrow? The answer will be probably a bit cooler than today, and it might be slightly covered, right? So very qualitative. Hey, we shouldn't laugh because it's actually pretty impressive what they could do by that, right? But that was the quality of the forecast back then, and then time went by, and then we had more complex systems, which and still the same approach, which I'm going to develop later, which is having massive set of partial differential equation and tries to solve them, but with maybe more and more accuracy. So that's the forecast that's on your TV. And where Atmo was making a big difference was by doing this AI-powered weather forecast, which is about 40,000 times faster to run, also more detailed and more accurate. I'd like to make a little point about why is it important that it's detailed? Because something I personally didn't know before I started to work on weather. So I'm going to try again this this thing. All right. So this is a map of San Francisco, and this is a wind map actually, and this is the wind forecast. And so you can see, this is a Golden Gate Bridge. So it's pretty long, but it's not that long. And so on the width of the Golden Gate Bridge, if you look on the opposite, you have like about 6 or 7 knots of wind here, and 16 or 15 knots of wind here. So it's a huge difference on such a small distance. And so essentially, if you have a more detailed forecast, you're able to have much better accuracy inherently. Or more likely, if you don't have very detailed forecast, you just cannot reach a good accuracy. And so AI-powered forecasts are typically enabling this kind of resolution.
Can you be like the weatherman for the picture? So like the weatherman presenting the.
Yeah, I'll show you something that you might be interested in. Okay, so that's the weather forecast for today at 3:50 in San Francisco. And so, all right, so this is microclimate. Right, in the way that you have this kind of super hot temperature right here. It's covered by this mountain, so it's not being cooled down by the Pacific Ocean. And so if you look at here, you have an 86 degrees like Fahrenheit here, and right there it might be like 68. And if you look at different periods of the year, so that can be up to like 20 Fahrenheit on this distance of 500 meters. So that was a weatherman picture. So, now let's say there is a heat wave, right? And so all the temperature is super hot. People who are here better know to get to cover up to get prepared for extreme heat. So yeah, I guess that's the strong advantage. Okay, now I'm going to try to close this navigator. Oh, see, learn from my mistake. Okay, great. Okay, so that's kind of who we are, what we do, what's AI-powered weather forecast. Now, let me show you a couple of projects we do. Okay, I guess each of these projects is going to highlight one specific advantage of AI weather forecast. First off, the performance. That's very obvious, right? You get better performance by doing these new models, and especially this customer is the Air Force, the U.S. Air Force. They have a base in Cape Canaveral, and Cape Canaveral is actually quote unquote from the military there one of the hardest places to model just by the disposition of like the sea, the island, all those things. It's in Florida, right next to Orlando. And so that's why we provide to them a personalized forecast that's really good at predicting this area. And so they have better performance, right? Especially if they're very interested in the wind, for example. Okay. Another strong advantage of doing AI-powered forecasting is the accessibility. So as I mentioned, doing the traditional approach, that's something pretty well known. You know, it runs on huge computers, which cost tremendous amount of money. And so the countries that can actually afford having a personalized weather forecast today are rich countries. So it's going to be like North America countries, Europe, which is another country, but there is a European Center for Weather Forecasting, China, Japan, I think India as well, but that's about it. Why? Because it's very expensive, and also you need some some specialized people in this field and so on. The Philippines cannot have their own weather forecast, so Atmo provides the national weather forecast for the Philippines. So as far as I know, it's the first time like a company or even a startup provides a national forecast. So it's an AI powered on top of this. So it's actually pretty impressive and pretty cool, I would say. The reason why this works is because our forecast can run on one GPU, right? It's super inexpensive. It goes super fast. It's not like you need these massive computers. So what the impact is down the line is that Filipinos, which suffer from a tremendous amount of cyclones, can see them coming, and then reduce the impact on people's lives, on infrastructures, and so on. So accessibility, and I will also put a focus on extreme events forecasting. So because it's a learning model, you can decide to predict more this or that, you know, on tweaking your loss function. I think we've talked about this before, like in the workshop. And so that's very interesting for Tuvalu. So Tuvalu is an island in the middle of the Pacific. It's like 30,000 people. Average height above sea is 1 meter. So whenever there is, and it's very small, right? Whenever there is an extreme event, they are hit extremely bad. And so if they can see it coming, again, it's better for like, you know, saving people's lives, saving infrastructures, and so on. All right, on maybe a brighter note, a good weather forecast can help you integrate better renewable energy into the grid. So, for example, let's say you're Germany, and you have essentially two sources of electricity: lignite, which is one of the most polluting coal you can find, and like solar and wind, which is renewable energy. Well, and you have a massive amount, and like 45% of your GDP, 25% of your GDP is going to be industry, right? So you really need your electricity grid to be put together, right? That's very important. All right, so, well, you have a good weather forecast. You know when it's going to have wind, you know when it's going to have sun, and so you can know how to tune your plant so that you can reduce the amount of CO2 emitted by the coal and like save coal and so on. So I guess it's one more very interesting project, and just to show you kind of the broad impact of weather, it's not only about having something to talk in a day, I would say. Okay, cool. So that's for the impact. Now, any questions so far? Okay, so now, yeah.
So for the island, that's Tuvalu Island.
Yeah, Tuvalu.
You guys go there, you and the US do there.
So I personally haven't been there yet. We met with their president. I don't know if it was in Tuvalu or if they came here. The partnership with Tuvalu is done through the UN also. So it's the UN that's helping Tuvalu getting this forecast through us. So it's like a whole partnership essentially.
We're just in the US and providing them the weather forecast about it.
Yes. Hopefully we can get there at some point. I would love to visit Tuvalu, to be fair. If I can, you know, pretend it's gonna help me doing a better weather forecast, I mean, happily flies there. Okay, so now the more technical stuff happens, right? Why does it work? So brace yourself. No, it's good to be fair. Okay, so essentially modeling, like forecasting the weather, essentially it's about simulating the interactions between 5 variables, which are the temperature, the wind, U and V, I mean, it has 2 directions, humidity, and pressure, also called geopotential. It's once you have this set of variables, these are called the diagnostic variables. And so as long as you can model the interaction between all these variables, you can actually model the state of the atmosphere, and therefore kind of probe some other variables, such as precipitation, like the rain, or I don't know, a storm, or extreme heat, or whichever that is. So most weather models are going to be working essentially on these variables. And so you have to think about the weather forecasting problem as a time series forecasting. It's the same way you could be forecasting, an EFT or something. You just have one state, and you want to predict the next state, and then the next state. So the state of the atmosphere, it's a vector essentially with multiple dimensions. So you have the latitude, the longitude, and the altitude. So you have like 3D data, and you have different channels or features or variables. I mean, depends on who you talk to. As deep learning implementation, I use the term channel, but it could be whatever. And so for each point of the vector, it's going to be, for example, the temperature at the surface, so at this altitude, on the latitude and longitude of Harvard, Cambridge, and that's it. That's one data point of your state, right? And if you enroll your state, you just have a massive column vector. And so you want to get from this column vector at which is now, right? Like so, we call it x k. You want to predict xk plus 1. Right? So you want to know, so let's say this function f takes the state at a certain time and predicts, it's going to predict the weather, let's say 3 hours later, right? And so f, you could call it, for example, f3, and it takes a certain state of the atmosphere, it's going to predict the state of the atmosphere in 3 hours. Okay, most, if not all, actually, let's say all weather forecasts are following this equation, and most weather forecast models are going also to use what's called autoregression. So autoregression will be, you are going to predict the state of the atmosphere 3 hours later, and then use this output as the input of this same function once again, so that you can predict in 6 hours, and then in 9 hours, and then in 12 hours. So you predict the state now to get in 3 hours. All right, that gives you another state of the atmosphere. This could be an input to know how it's going to be in 6 hours, and so on. And so you enroll your function until you get a full forecast with a 3 hours time step. Saying 3 hours could be 1 hour, half an hour, 6 hours. Kind of varies from one model to another. And well, obviously you need to have a state of the atmosphere in the first place. So the way it's done is that you have many sensors like radars, weather stations, satellite data, many different sensor sources, and it's just assimilated, as it's called, a data assimilation process. So we can get the state of the atmosphere now, and from there we can enroll the process. So that's for, again, from x to xk plus 1 with f, that's every single weather forecast model. Enrolling, that's most forecast models. Okay, so you could ask okay, you talked a lot about how it was done before, the models, fine, but now let's get a bit more into detail. So the technology So this is actually, let me start with this. This is supercomputer frontier. It's the biggest supercomputer, and it's, I think this one is the American one. There is also a Japanese one, which actually is bigger now. There is kind of a competition. But essentially, yeah, this is outdated. I think the Japanese one is bigger now. But regardless, these are massive supercomputers that cost like hundreds of millions of dollars. And so they're going to run, they're going to do this step by solving a set of partial differential equations. So what's a partial differential equation? It's an equation with variables and their derivative within the same equation. Like it's a differential equation with multiple variables, essentially. Which makes it pretty tough to solve. In general, we don't really have a closed form for a partial differential equation. Actually, trying to find this kind of solution is a whole field in math by itself, and a painful one for the least. So, in general, the way you would want to solve a partial differential equation system would be by using big solvers. And so you can just shape this equation and try to find one solution by iterating over. And so that's what they do. They model the weather as a set of equation. They solve it. That takes about 4 hours of massive supercomputer. That's one way to do it. And we're glad we had it for so long. I mean, this was developed in the 50s. And essentially what they've done is just increasing the size of the computer, fine-tuning the equation, integrating more sensor data, and so on. Okay, now, the thing that it scales pretty poorly, because the way it's done is that you have to chop the Earth into cubes. And your equation is going to be modeling the interaction between the cubes. So now let's say you want to increase the resolution. We've seen that resolution was very important. Say you want to increase the resolution. Well, it's a cube. You have to increase the number of cubes by literally power of 3. So, 2 times more resolution, 8 times more cubes. And it's getting even worse, just for the fact that then we have to look at the number of interactions between the cube. So, the scaling up is pretty tough. And on top of that, it does capture pretty well the small local patterns, but it's pretty bad at capturing the mesoscale patterns, which is an interaction, which is essentially long distance interaction. So, I mean, that makes sense, right? This cube interacts only with his neighbors. So how can he know that the big wind is coming from here or rain is coming from here? That takes a lot to propagate through the system. So this kind of inherent limitation are going to limit, at a point or another, the performance of this method. In opposition, machine learning has a tremendous capability to scale up. And I think that's one interesting way to, I'll keep this one for later. But yeah, the way machine learning does it in opposition is to take, you have your whole data set, right? You have the state of the atmosphere at many different times. And then you're going to take a certain time, and that's going to be your input data. And you're going to look at what was the state of the atmosphere 3 hours later. So that's your target. And you're going to learn this function f that will map the input to the target. So essentially, you're going to learn this function f that, given the state of the atmosphere, predict the weather 3 hours later. So that's the core of it, really. Any architecture will follow that logic. And what's great about this method is that, first off, it uses only gradient-based optimization, like you've seen the backpropagation and so on. And so you don't need to compute the Hessian. The Hessian is essentially the matrix of double derivative of a function. And so you need it for this whole CPU compute we've seen before, they do need the Hessian, right? So they need massive and hard to compute matrices. We don't. So that means a much smaller memory footprint. On top of that, we can probably look, you've seen this attention mechanism class. which is very strong at parallelism operation. Well, that means that you can do much more operation at the same time, which means you can actually train your model more and do more things and have just smarter models. And so that's where it's kind of, I think, as scientists, we tend to think, I'm going to develop an algorithm, and then I will put it on my computer. But with machine learning, what's very interesting is that we look at the hardware we had, and we look at what was a good algorithm we could run on it. And so that's where it's actually, it makes such a difference, is that the algorithm, like the model, is very adapted to the hardware we have, right? Okay. So, in general, when you do a machine learning project, they ask you, oh, so what's your data? And that's a tricky question. What's your data? Do you have biases in your data? Right? This kind of question, right? And so we're kind of lucky in the weather field, I would say, because we have like the European Center for Middle Range Weather Forecasting delivers a reanalysis data set, which is basically a high resolution, a high accuracy data set, but that can only be done once the weather is gone. So, it can only be done by hint casting, right? For forecasting backwards. And so we can actually train on this, right? So a model is going to compress all of this data to be able to smartly interpolate it later and redeliver a forecast. So we have great training data, and we have also pretty good testing data because every single airport is equipped with a weather station, which is public data. Great. So that means we have 10,000 publicly distributed weather station data. So we can actually test our model. So you could say, well, it's kind of biased, obviously, because the airport are at certain locations and so on. But I mean, it's not bad, frankly, it's pretty good. Okay. So, big technological breakthrough, a lot of free data online, mechanically leads to many people publishing papers about it. Also, this is not totally up to date in the way that there were much more papers in 2024, right? So, but what's interesting to see is in 2020, 2021, essentially no one was interested into doing AI for weather. So there was like one paper. And, starting 2022, it just hit and now everyone wants to do this. And like an anecdote I heard from the founders was essentially saying, oh, when we started the company in 2020, 2021, well, no one was, you would go see a VC and you would say, oh yeah, AI for weather is going to be revolutionary. And VCs would say, no one is doing this, that's you're a dreamer. And then, now we go see them and they say, oh, everyone is doing it. So like, it's interesting how time changes. Anyways, okay. So that's why AI for weather forecasting works. Now, kind of the meat, I would say. So that review of AI forecasting architectures. I'm trying not to throw too much hard stuff to your face as much as I can. I will still do a little bit, but hopefully it will be understandable. Please, 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 during this section, feel free to ask questions, interrupt, get it clear so that when you walk out of this room or of this Zoom call, you know what he's talking about pretty well, and you can reuse it in your projects. And this is meant to be interactive and interesting for everyone. Okay, so in this talk, I'm going to cover. Maybe to list the dominant architectures in weather forecasting models and architecture. You could say there is either you see the weather as an image, right? That makes sense. It's like coordinates, channels. You could see it as an image. And so that's what convolutional neural nets do, vision transformers do, and diffusion models do, right? you could also see the weather as the observation of an underlying set of equations, right? That's what would ACNO do. So it's going to be relying on Fourier and like the Fourier transform. And you could also see it as a graph, so it's called GNN. For today, we'll only cover like CNNs, vision transformers, and AFNO. And that is because vision transformers and CNN are very common and pretty easy to use in general. So I really want you to have this in your stack of tools that you could use later. And AFNO are extreme, I would say weather specific, but also physics specific, because they are going to be operating in the Fourier space. And so it can be very good at equations, like a mapping underlying equations, and so being very good at solving physical problems. Okay. So I put this little, repetition is key. So I put this kind of image here saying our job is really take the state x0, predict xk and xk plus 1 and so on, like x1, x2.
It's always the same. It's always the same.
You want to do, if you want to be my slide maker, please.
Easy prediction.
No, well, this one is very static, I will say. No. So please be making it regarding this slide. Okay, cool. Convolutional neural network. Okay, so in this room, who has taken a class of which the name was something like signals in the system, like essentially a signal processing class, and has seen Fourier transforms, convolution product operators? 1, 2, 3, 4. Okay, more or less. Okay, 5 people. Okay. Yeah, that may be a bit tougher. Okay, let's.
We studied CNN this morning.
Okay. Yeah, but I'm really going to like use the Fourier transform during this presentation. Okay, essentially, the idea of the Fourier transform is to say that any function can be described as a periodical function. Any bounded function can be described as a periodical function, and so you can break down the downstream application of this is that you can break down every single signal into a sum of sinusoids, right? And so all these sinusoids will have a frequency, and so the Fourier transform will be the amplitude of these frequencies. Yeah, that's it. So, for example, if you take, sorry people on Zoom, I hope you can see it. If you take sinusoid, right? The Fourier transform will be this. It will be like 1, which will correspond to here the frequency of the signal, right? So this is the Fourier transform noted f of the signal s, and this is s, right? Okay, and now let's say this is a sum of this sinusoidal and this sinusoidal. You will have, this is twice the frequency, so you have one more frequency here. All right, so it's going to be 2f. And so that's the Fourier space is going to be, it's a mapping of the temporal space of a signal, or it's a mapping of but in the frequency space. So you describe this, when we talk about Fourier space, we talked about a like a dual space, so like you can have a one-to-one mapping between these two spaces, between the Fourier space and like whichever space you're operating in, so spatial or temporal, and like whichever is this axis essentially. And so it's convenient because then you can work on the frequencies directly instead of working on the signal. So for example, you say you want only high frequencies, you can just take your signal, put it into the Fourier space, remove this function, this frequency, and then get it back into the temporal space, and then you only have this signal. So it's a very, very, very useful transform in signal processing. Okay, so now back to the CNN, and that's going to be pretty useful later. So CNN is, the way it's been presented to me, it was like dark magic. So you have a kernel, right? And you apply it to a matrix, and you just apply it as a patch here, here, and there. You look at the sum of each of the products of the elements of the matrix. So the sum of the Adama product, essentially, and that would give you a value. And you do this over and over, and then you get this matrix, and you would reiterate it. And it, you know, by the time people were actually doing an extremely cumbersome job of designing these filters by hand and having like banks of filters and trying all the filters into one image to do and just selecting the right one. Now, you know, the CNN is just going to learn this kernel, and so you can stop there and think, okay, fine, that just this is a filter, it's being learned, it's great for images processing. I'm pretty sure that's what most people do. One other thing, it so happens that actually what this is doing is a product in the Fourier space. Because a convolution is a product, it's mathematically equivalent to do this operation than to do a product between the Fourier transform of this kernel and the matrix. All that means is that when you do a CNN, you are operating on the frequencies of your image. So you're going to capture frequency-like features, right? So I guess
frequency-like features, like seconds or what?
For example, yeah.
Time points per second is that
Yeah, so if you take like my frequency features, I would say, if you notice, okay, let's say you make a classifier, and you have two signals. You have let's get back to this idea of having two signals, one which has f equal 1 hertz, and the other one which is f equals 2 hertz, right? Now you want to classify. You have a couple of signals like this. Like you have some signal which is 1.89 or one which is 2.02, whatever. So you have a family of signal which look like more like 2 hertz, and a family of signal that look more like 1 hertz. What I mean by, and you want to classify these two, then a CNN is a very good choice because I mean, you could just do it with regular data analysis, but let's assume you want to do a model to do this. You're going to be operating directly on the frequencies of your signal, and so you're going to be better at detecting this pattern, signal patterns. It's hard.
So the first graph is your text and the second one, or is it Epoch data? Like what? I'm confused.
Yeah, sorry. A, B,
Okay.
right? You have a model M,
Okay.
and you want when you have A that is modeled by M to be yes, and when B is modeled by M to be no, right?
But how, so you pick which data set's the best and which one's yes, which one's no?
You want to.
That could be problematic, yeah.
I mean, this is a market test, right? But let's say that the job of your model is to tell A from B. So and A being some signals that would be in the 1 hertz domain, and B would be some signal that would be like more like 1 hertz domain, which is a 1 hertz region, right? Like around 1 hertz, and B would be signal that would be around 2 hertz.
So, but I get that. So, but if it's too frequent, is that gonna I'm concerned with how this ties to frequency, like you were saying.
Well, the way to tell this signal from that signal is because they don't have the same frequency. And so this model is really good at dealing with frequency. So inherently, it's going to, hidden somewhere in this map, is going to look at the Fourier transform of the signal and tune or not tune this or that frequency. And so this can give you an intuition when to use this. Yeah, thanks. Thanks for the question. Yeah. Okay. So that's for CNNs. So we've seen the convolution operator. One way to use it is to make a unit. So it's a very classic architecture. The way it works is that you have, and it's called a unit because who can guess why it's called a unit? It's shaped like a U. So it's pretty easy to remember, right? And so the way it works is that you're going to apply these kernels on your image here, and then you're going to downscale your image, right? And then apply some other kernels, and they apply some other kernel. And so as you downscale the image, you capture bigger picture, you capture like more like global features, right? Whereas when you apply your kernel into a large image, your kernel has kind of a fixed size. It's never much bigger than like 9 or 13. So when you apply your kernel across your matrix, if your matrix is really large, you're going to capture more like details, right? Because you have like a regional operator. Whereas as you reduce the size of the matrix, you're going to start to capture more like coarse, like high-level details. And then you upscale it so that you can actually get an output image which has the same size as your input image. So that's pretty fortunate because the size of the herb doesn't change that much. So the input and the output data is going to be the same dimensions, and so you might have noticed these arrows here. Actually, what they correspond to is that you're going to add the input to the output to do what's called residual learning. So residual learning will be, this intuition is, it's much easier for your model to predict the difference between the current state and the next state than to reinvent everything. I mean, the weather in 3 hours is not going to be that crazy different from now to like in 3 hours, right? So that's what the idea is with these lines. It's called residual learning. It's just to add the input to the output, so you just learn what changes. So yeah, I guess that's about it. UNet is like very classic, very useful, and can be applied to a whole range of different problems, including maybe yours. Okay, here it's another very classic architecture, and that's going to rely on the principle of self-attention. So you've seen the you've seen the attention mechanism with Pierre. And so essentially what the attention mechanism is you take a sequence, can be words, can be sound, can be like whatever you want. I mean, as long as it can be embedded, you take a sequence and then you look at who in the sequence should talk with whom, right? Like I am a student, like I and student typically have a strong connection. I am not a student. Also, the not is very important to the sentence. Here in the vision transformer, we leverage the attention mechanism as we patch. We're just going to chop. We leverage the attention mechanism on tokens which are actually patches of the image. So you take your image, you chop it into patches. You embed these patches, so you just embed them. You just stamp them with, by the way, you were here in the image. That's called positional embedding, right? Just so that the neighbors know they have something in common. And then you use a attention mechanism on it. So you've seen it like attention, the NLP, and it's like a classic encoder that I want to delve into because it's a rabbit hole. But yeah, it turns out this architecture is also very classic. You definitely want to use it at some point, especially it's very good at with long distance interactions. Just because the token blending, it's like there is no priority of this token over this token interaction rather than these two. They know they're close to each other, but there is no, it's not like in the CNN in which you actually have kernels that move and that enforce regional intercommunication and influence. I don't know. Okay. Yeah. So a typical use case of this would be to like take the state of the atmosphere. I mentioned like you could simulate the state of the atmosphere and then use it as kind of a state to then probe other variables from it. Like from the diagnostic variable, you want to probe out the prognostic variables. Well, that's typically a good application of this model, right? You have the state of the atmosphere, and you could use it to forecast rains, for example, or you could use it to forecast I don't know, thunder or storms or whichever that is. It's a very good model for doing this. Okay. I'm going to skip the Fourier neural operator presentation. You don't know what you're missing. I mean, very, very quickly, but like very quickly. The idea is that instead of using a CNN to do this Fourier-based operation, you're going to take your data, put it into the Fourier space directly, apply transformation in it, and then back into the regular space and go and iterate like this. And so that means that instead of having just a couple of frequencies that you can do with a small convolution operation, you actually have like the equivalent of an infinite kernel. For so that's and so why don't we do infinite kernels? Because it's extremely expensive, right? So here you can have an infinite kernel for a fixed amount of power. And so it's very interesting also when you use the inverse Fourier transform, this can be mesh free in the way that you're still converting. You're looking at all of your Fourier transform of all of your frequencies, and then you put them back into the regular space, like the space you took them from, essentially. And then you can actually choose the resolution that you want because you're just interpolating you're just sampling a sum of periodic signals. So the takeaways are, it's like a CNN layer, essentially the same thing, except that you have much more frequency covered. It's mesh free in the way that you can use whichever resolution at the output that you want. It's like if you want to increase the resolution, it's a much smarter interpolation than just doing linear interpolation or whichever. And it scales pretty well if you want to work in the frequency domain compared to CNN. Okay, this one I'm sparing you as well, because this was a mix between VAT and Fourier neural operator, but anyways, I'm happy to talk about it afterwards if you want.
Yes.
Okay, so we are past the whole technical stuff. Now it's more, let's talk about just the challenges, right? Like, let's talk about what stuff. That's the fun part. Let's put it this way. Like, what is hard to solve in weather? What are the open challenges? Why is it hard to solve them? What's the hard problem in deep learning in general? So I think everyone knows that weather is pretty chaotic. So I put a lovely picture of a monarch here. And that is to illustrate, any guess? Maybe someone? Where is there a picture of a monarch on this slide? With written chaos on it. Exactly, yeah. The flap of a butterfly wings effect. And And so, this is an image to show that, the flap of a butterfly somewhere in Japan can cause a tsunami somewhere in like Tuvalu, for example. And so it's obviously not exactly the way it works, but what it means is just that the weather is extremely chaotic. So it means that small variation induce massive changes. And so I guess one way to understand this really good is just to if you take this pen, right, and you put it like this, and you drop it, maybe it's going to drop to the left or to the right or whichever. But we don't really know which direction it's going to go in. But interestingly, once it's in one direction, it's actually pretty consistent, and you know where it's going to go. And so that's kind of how weather works. Is that it's going to take, it's either going to go right or go left, but one of these two. And you can even put percentages on these probabilities. And so once you're and so the butterfly effect happens when it's exactly this position, and then you have a little butterfly that say, okay, you're going to go this way or this way. But that's what the butterfly effect is. It's like you have some nodes like that's going to say right now whether it goes either left, either right. And so that could mean this tornado is going to hit Japan or not. For example, they have many tornadoes. So yeah, that's also a big issue because, okay, now let's say you want to make a model that's going to predict where the tip of this is going to fall, right? Where the tip of this pen is going to fall. Well, either it falls left, either it falls right. Okay, great. The thing is, if you just use a MSC loss that's going to optimize for the Gaussian distribution, essentially it's going to tell me middle, right? Because if you do this on average many times, you're just going to fall in the middle. And so essentially the MSC loss is not a good method to learn about chaotic events. And so that's specifically where like the most iconic phenomena for this is typhoons, right? So right now, right here is the butterfly place. It could go either left or either right. Once it goes one way, it's actually snowballs, it compounds, and it goes this direction. I mean, I'm going this way or that way. And so, yeah, that makes it hard to train specifically. To forecast, it's fine. You can just do a bunch of different forecasts. You add some noise as the input, and then you could have what's called ensemble forecasting. So add some noise as the input, and do many forecasts, and look at what you have as a typical output. But yeah, for training, it makes it pretty tough, and you get this kind of results. So that's one of the first papers that has been done on weather and from ForecastNet, and that's kind of what the issue is. Like essentially what this curve tells you is that they have to assume, just for the fact that they use MSE, that they learn a Gaussian process, right? But actually, this is not Gaussian at all, right? This was going either try to plot the derivative to be like either left, either right, and you're penalizing for something that should look like this. So when you're here, you're going to be called out for this one, and when you're here, you're going to get called out for this one. So you're going just to say this and be always wrong. And so that's exactly what's happening here. It's like when it was up, and it was down, and so it was like, you know what, middle. So yeah, it's still a big challenge to forecast hurricanes, or so hurricane and typhoon. It depends on which hemisphere we're talking about, but hurricanes / typhoons are pretty hard to forecast. Okay, lightning. So it's also pretty tough to forecast in the way that for this one specifically, it works with small scale phenomena. It's just like the air that scratches on the water, and like the water goes up, and like it's a very local phenomena, and it's very that has very specific interaction between humidity, wind, and temperature. that cause the charges to go down a cloud and then fall down. So that means that you need, and on top of that, the kind of conditions that make this happen super fast. So I guess with AI for weather, we do have a shot on this kind of phenomena because we can have high resolution and we can be very reactive compared to like traditional methods. But this is typically a huge problem. And on top of that, there is not one thunder, like one lightning. Sorry, there's not one lightning. Like you can different type of lightning in the way that the conditions to get lightning are not all the same. So it's, again, we're not done solving lightnings yet. This being said, if you can do that beyond the safety for infrastructures and people and so on, if you can capture the energy in the lightning, you're going to be a rich person. And that becomes an energy source. That's quite a potential. So if you know it's going to have lightning here in like 30 minutes, you can bring, I don't know what you could do, but you know, you could start to like do some really cool stuff. Okay, so I guess, you know, climate change is also a big issue because we train on historical data. So what if it so happened that climate was changing? Then whatever you learn is just, you know, obsolete. So that's actually an issue. Because not only you get shift from historical data in medians and like in climatology and so on, but you also get like pattern changes. Like you get drastic changes in the way the weather works in a certain environment. And so, you know, it's on that there is no silver bullet, but what we would do in this kind of situation is, you know, you just stamp your data, your training data with the year so that it knows which year it is, so it knows how to, like, who to trust maybe. You can add features like CO2 particle per million, or you can add the climatology or the forecasting climatology for the year you want to forecast, and so on. So there might be some workarounds, but again, that's a big challenge for the field. Yeah, and also like, I don't know, test on most recent data to make sure you actually have performance. If you test on data from the 70s, it's not going to give you any insight on the performance of your model. And maybe train harder on recent data. It's a bit of more of an applied slide to see this kind of problem happen all the time. Like, you know, your data is biased, or I mean, your data is biased is actually a very strong usual problem, especially in biology, in which, in general, if you can have data for it, and if it was easy to get data, you would not have a job doing this model, right? So in general, if you can have data, it's because you have it through a certain method that's going to bias your data, which data you have. And so, you know, you need to be a bit witty and find some workarounds. And now, final slide, which is called the bitter lesson. So, all right, so essentially that goes a bit in the direction of the question about asking John Jumper, which was, you know, we know so much about the universe, like we know some laws and we know a lot. And so we learn everything from data. Why do we do that? And because something that's frustrating for every single machine learning engineer, you know, regardless of the field, is why do I need so much data for something that a human would need much less to understand? Like if you're Waymo and you're, or whichever other company like Zoox or, but not to draw too many companies, but or some going to those concurrent, Cruise or whichever company that does self-driving cars, you're like, why do I need 10,000 or 20,000 hours of driving, whereas it took me 20 hours, right, as a human? And so, sadly, so far, it so happens that the amount of data and the amount of training you put into your model is just very correlated with the performance. And that's the only thing that really worked over time. Like, essentially, John Jumper is right. Like, the ways architectures are really architectures are can make a strong difference between the transformer, especially since it was so parallelizable and so on. But what really makes a difference, and that's bitter because we want to believe we can be smarter and imagine better architectures, but it turns out that what really makes a difference in the end is the amount of compute you have, the amount of data you have, and maybe the quality of the data you have. So yeah, I guess that's interesting to keep this in mind. And that's it for me. Thanks for your attention. By the way, we are hiring, so if you're interested, it's a pretty cool project, so that's it. Thanks. Are there any questions? Also on Zoom, maybe? Is there any questions?
I actually had
Yeah.
a question just out of curiosity. It's not a question related to the architecture itself, but I was just thinking, especially with the temperature data, having the type of resolution that you have in the US could be really interesting for research related to like racial and socioeconomic disparities and people living in different areas of the city. And I was
Yes.
wondering whether that's something that Admiral is working on.
So I think it's a great area of research. I think it's very exciting to work on this. Yes, you see definitely some areas are more livable than others in cities. So we don't work on this currently, but I mean, I'm excited to I mean, if someone hears me and wants to work on this, please reach out.
Limiting, right? Because you only have like one airport per city, right? Like that's kind of hard, right?
So yeah, so the thing is
Like several, like, you know what I mean?
there are techniques to do high resolution forecast on places in which you don't necessarily have many weather stations, essentially. Yeah. So, but yeah, you know what's very fascinating about weather is the variety of people it impacts. It's absolutely, I mean, to me the best was this company in Virginia that called us saying, yeah, actually we need to paint outside. And you know, when it rains, we cannot paint. And so we lose so much money because of this. Can you do something? And we're like, well, yeah, we can do something about this. And you know, it's the same thing with construction work. And you know, it's also work with insurances and energy. And it's crazy to see how much in health, and it's great to see how many fields are just directly related to weather and dependent on weather. So that's one very good example. And like, it's crazy to see how many yeah. Yeah, please, Casper.
We've got a couple of questions from Zoom.
Oh, cool. Okay, cool.
So the first one came earlier during the presentation. I know you mentioned that like potentially using CO2.
Yes.
But the question is, do you consider air pollution or air composition in your models?
It's a good question. I mean, the thing is that the greenhouse effect is just, I would say just short answer is, I'm trying to give as much data as I can to my model. I think CO2 ppm is a valuable data regarding global warming. To my understanding, what really matters is the global concentration of CO2. So that to have an estimation of the greenhouse effect. Now, like, there are some models that are modeling the air quality and then would be very interested into doing more local CO2 concentration or nanoparticles or whichever that is, or microparticles. But at that moment, we don't work on this currently. Yeah, it's also field of research. But yeah, essentially the answer is, I would say just global ppm concentration to give your model an understanding of the global warming. Yeah, Pierre, or yeah, maybe another question from the audience.
Yeah, there's another one. It says, how do you weight each of the channels that you mentioned?
Oh, that's a great question. Okay, so actually it depends on what you're interested in, right? Let's say you deliver a model for, people who are really interested into flying planes, like an airplane, let's say you deliver a model for an airport. What they're really interested in is the wind, right? At essentially 2 meters above ground level, maybe 50, 100, and then 1 kilometer above. So this is what they want. So then you should weight the channel in a way that's going to in a way that's going to essentially sacrifice everything to the wind at this level. Right? It can also work for location if you want to forecast a specific location. So, and that's what's great about machine learning, is that it's just going to optimize for one specific outcome. And so you can just tune the outcome you want. And so if you want wind, go for wind. If you want temperature, go for temperature. If you want to make a model that's going to forecast extreme temperature in the US, penalize your model super hard when it misses a hard temperature, right? And don't if it doesn't. This is really the whole beauty of this art, is that you have such freedom, essentially.
That's
Go for the
Alright, so we have one more from Zoom. Abel is asking, the partial differential equations you mentioned are for each channel, like temperature, wind speed, it's better, etc. So they're asking if they understand correctly, essentially you're calculating the change in one of the variables with respect to the others. Is that
Well,
right?
not exactly. So the set of partial differential equation, I mean, the wind is not independent from the temperature. Temperature is not independent from the pressure, and it just works as a set of these five diagnostic variables. And so the equations, therefore, have multiple variables. That's what makes it hard. Actually, otherwise it's called ordinary differential equation. If you have only one variable if you have only one variable in the equation, it's an ordinary differential equation. And the fact that you have multiple variables makes it partial and makes it also harder. So no, it's a partial differential equation in the way that you have many variables, and that's what makes it hard, actually. Yeah.
That's
That's
all
it.
the questions.
I guess that's it for today.